Because it is for the election.
Yeah, yeah.
I was kind of sick for confidence. When you then begin as a little bit, and now I think that the technical conference, I find your like on the program. It's like this. And they won't come on time.
Welcome to the International Conference on Statistics and ICSTC 2025. So we are beginning the So we are starting the 4-day conference of ICSTC 2025 with the inaugural session today. So let's start today's program with the national anthem followed by prayer.
पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलति तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे
Mic.
one of them if they can hear and then decide, otherwise they'll be sitting.
Or maybe we can keep it. It's good. So once again, good morning, one and all of you. So my duty now is to welcome the gathering and to welcome the chief guests, the great professors and academicians and statisticians. Academia in what you call improving the spread of statistics to support the research in statistics across the globe. It's a trust that had been formed with many such intentions, and Icstc is hosting these conferences for the past many years. As you will be knowing, this year's Icstc 2025 that we are having, and apart from Icstc 2025, we are having international conferences in the online mode every year in June, which is called the WSTA. So all along these years, many programs have been conducted, many awards have been in. Who is the chairman of Icstc, who is the chairman of Icstc, who is, as you all know, a well-renowned statistician, the former head of the Department of Statistics, and currently he's heading the School of Physical and Mathematical Sciences. And he's actually the brain, the energy, and what you call the motivation behind all of these ventures. These are his idea, and he has got a strong supporting team who believe in his efforts, who have got great trust in his vision, and it is through his direction, his his mentorship that we are able to conduct these programs. So he is the chair of today's inaugural session, and with great respect, I'd like to welcome you, sir, to this program. Every year, we are lucky enough to get great professors to be part of this conferences, all these conference series. And this year also, we are extremely privileged to have a great professor with us, Professor Nalini Ravishankar, who is the President-elect of International Statistical Institute and a professor in the University of Connecticut, USA. Ma'am, I think in the international scenario, ma'am doesn't need a very an elaborate introduction because she is well known across various parts of the globe. Her research work is very much appreciated around the globe. But still, I would like to say a few words about her so that you will get an idea of whom or whose words you are about to listen. So, Professor Nalini Ravishankar is an Indian-American statistician, best known for her works in time series analysis and its applications in finance, insurance, transportation, and biomedical sciences. Her research spans Bayesian dynamic modeling, signal processing, and predictive inference, and she has got more than 150 peer-reviewed international publications, and she has produced more than 20 theses. 20 research scholars have completed their research under her guidance. She is a fellow of the American Statistical Association and the American Association for Advancement of Science, and is the elected member of the International Statistical Institute. She's actually currently the president-elect of ISI for the year 2025 to 27, and she will serve as the president from 27 to 2029. She's also the co-author and the author and editor-in-chief of many internationally reputed journals like the International Statistical Review, the Applied Stochastic Models in Business and Industry, and as I have already told you, her name is well renowned in the statistical academia. So with great respect and happiness, we find it a privilege to have you with us to inaugurate our conference, ma'am. On behalf of ISF as well as the University of Kerala, I extend a hearty welcome. We have got a great number of professors who have been our well-wishers, who have been with us all through these years, supporting our various activities, delivering their talks, acting as judging panel conveners, such as judging panel members for the various competitions that we take up, being invited speakers, session organizers, and these names, I can't name them one by one because the number is so high, and the support and cooperation that you have all extended to us. The great professors that have joined us online and those who will be joining us offline also. We are indebted to their support. We are indebted to their encouragement that they are giving us through their presence, through their words, and through the various activities they are willing to conduct along with us. And specifically, we have got our former professors, Yagin Thomas sir and Kanyana Raman sir, who are here with us as always to bless our event, because their blessing is of great importance. They are our gurus, and as the Indian tradition goes, a guru is equivalent to God. So they are with us this year also to give their words of blessing. And we have got Asha Gopalakrishnan ma'am. I call her Asha Cheji because she was there when I did my PG. She's from the Cochin University of Science and Technology, and she's there with us this session. So I welcome all of you on behalf of ISF and on behalf of the University of Kerala and on behalf of each and every one of us here. Welcome you all to the function. Then we have our dear teachers. We have got Riaz, who is an assistant professor here, as well as he's the treasurer of ISF. We have got the executive committee members of ISF. We have got other professors and other teachers, and so many of you have come from around India to be a part of it, whether it is online or offline. So on behalf of ISF and the University of Kerala, I would like to extend each and every one of you a very hearty welcome. Thank you. And then there is a great number of faces who lie within. We see for every act that is performed on stage, there are even more number of people who put in their effort off stage. Here, these faces are actually, maybe they might be teachers, they might be students of the university, they might be former students of the university. So great many of them are here, behind the scene, on the scene. So I wish to welcome each and every one of you for the program, and thank you for the efforts that you're all putting in to make all our programs a great success. Now I think I will stop my words here and we'll go on to the next program. I'd like to invite Sati sir for the presidential address. Over to you, sir. Thank you.
A very warm greetings to all. Good morning, good afternoon, and good evening. We have a lot of people are there in the online platform as well as offline platform. And if I good morning, good afternoon, good day. Good day, yes. At the outset, let us respectfully remember and pay tribute to our former faculty members and the distinguished professors of this department, whose dedicated efforts laid the strong foundation of this prestigious institution and whose blessings continue to lead us. It gives me immense pleasure and deep sense of responsibility as the chairman of the conference, International Conference, to welcome and to the 11th International Conference on Statistics for 21st Century 2025, Icstc 2025 in short, held in conjunction with the sixth annual convention of the ISF. This prestigious academic event is organized by the Department of Statistics, School of Physical and Mathematical Sciences, University of Kerala, in association with the American Statistical Association, Indian Society for Probability and Statistics, Kerala Statistical Association. Today marks a truly significant moment as we bring together an exceptional assembly of scholars, scientists, and practitioners from across the world. Over the next few days, this conference will serve as a vibrant platform for intellectual exchange, collaboration, and innovation, facilitated through a thoughtfully designed hybrid mode, enabling participation beyond geographical boundaries. I take this opportunity to respectfully acknowledge and extend my sincere gratitude to the distinguished dignitaries and eminent scholars who have graciously joined us today, among them Professor Babisi Arno, Professor Nandini Devishankar, Professor of University of Connecticut, USA, and the present President of International Statistical Institute, the Netherlands, Professor Dietrich von Rosen, Linköping University, Sweden, and Chief Editor of the Journal of Multivariate Analysis, Professor Ron Wasserstein, Executive Director, ASA, Professor Ashish Gupta, Professor Thomas Kusubolsky from University of Nevada, Professor Thomas Martin, University of Maryland, Professor Malay Kosh from University of Florida, Peter Lohmatter, Sweden, Professor Sakupta from University of North Carolina, Professor T.J. Rao from ISI, former Professor of ISI at C.R. Rao Institute of Mathematics, Statistics and Computer Science, Professor Vikas Sinha from ISI Kolkata, Professor Gawad Basar, Rahul Troy, Elizabeth from ISI, and Professor Nadaraya, Elizabeth Nadaraya from Georgia, Professor Rajiv Bhaskaran from ISI, our beloved Professor Hirata Ramsar here, Professor Professor Ram Tribadi is here. Professor. And then several others in this group itself. And also Professor P.C. Mohan, the chairman of the State Statistical Commission and former chairman of National Statistical Commission. Professor, and then several professors are there from various parts of the country, not concerned from the various parts of the globe. We are also honored by the presence of several distinguished participants from premier institutions like ISI, IITs, ISA, IIST, etc. I sincerely regret my inability to acknowledge every distinguished participant individually due to time short. In fact, Icstc 2025 stands out as a truly mega-institutional academic event, featuring over 20 keynote talks and plenary talks, more than 80 invited talks, and over 100 contributory research presentations, including special invited lectures by leading scientists. Each session has been carefully structured to encourage meaningful dialogue, foster disciplinary collaboration, and stimulate innovative thinking. The detailed program is available on the conference website, as well as we will send some program charts that will review. The academic deliberations commenced with a pre-conference workshop during 14-15 December, which proved to be immensely beneficial particularly for young researchers. And the workshop featured enriching interactions with the distinguished scholars such as Professor Dietrich von Rosen, Professor Thomas Kuslovsky, Professor Nalini Ravishankar, and Professor Muralidharan. It is a matter of great pride and privilege that Professor Nalini Ravishankar has graciously consented to inaugurate this international conference. She holds the historic distinction of being the first woman, I hope, not the president of the international
India, perhaps.
from India, yeah, the first lady president of the International Statistical Institute, Netherlands, and distinguished scholar from University of Connecticut. Her work exemplifies excellence at the confluence of statistical theory, computation, and the real-world applications. Her decades-long contributions to research, teaching, and leadership have left an indelible mark on the global statistical community. As a mentor and visionary leader, she continues to inspire generations of statisticians worldwide. Sharing this platform with her itself is not merely a personal honor for a person like me, but a moment of profound academic significance. Her life and work exemplifies the boundless potential of human intellect, guided by perseverance, integrity, and an unwavering commitment to excellence. I am also pleased to highlight our Department of Statistics, the second oldest department in India, commenced its postgraduate program in 1945. This year marks as the 80th anniversary of the department. To commemorate this significant milestone, we have instituted two endowment lectures under the on behalf of the International Statistical Fraternity, with the generous support from our esteemed and our great professor, Professor K. Kalyanaraman. In his honor, we also instituted a Best Project Presentation Award among the graduate students across the country, beginning from this year. These initiatives, also there are Best Thesis Award and several things are there. And this year always the Best Thesis Award goes to both mathematics, physics and statistics. These initiatives underscore the enduring value of academic integrity, ethical scholarship, and unwavering commitment to knowledge creation. I strongly encourage all participants, especially students and young researchers, to fully engage into these sessions, interact with the fellow researchers, and take advantage of this unique opportunity to broaden your academic horizons. In conclusion, I extend my heartfelt gratitude to all members of the organizing committee, all collaborators of this conference, sponsors, speakers, delegates, and volunteers whose dedication and cooperation have made this event.
Now I'd like to welcome our dear Chief Guest, Representative Nalini Ravishankar, for his presentation. Thank you.
Hello everyone here. Hello everyone that is online. It is my hello. It is for me a huge honor and pleasure to join you all in inaugurating the 11th International Conference on Statistics for the 21st Century. The acronym is very, very apt, and I like the 21st century because that is where we are, and we need to do as much as possible to make this a success for the statistical community. the statistical community is indeed grateful to the Federation, the International Statistics Fraternity, and the University of Kerala for organizing this exciting event. The event itself runs from December 16th to 19th, and we are here for a huge treat as we hear a lot of people from India and around the world. This was preceded by a pre-conference for 2 days, like Professor Satish said, and it is pre-conference workshops like this that I think are extremely beneficial to the next generation of statisticians. So it is wonderful that a lot of you participated, and I think many, many more should participate both in person and online in these pre-conference workshops. This year, I'm very, very pleased to participate in person and in this beautiful city, Trivandrum in Kerala. I joined the online version. It was called the WSTA. I joined it in 2025, and again I was very impressed by the huge number of speakers that Professor Satish was able to bring on, and the talks were of very, very high quality, and there was a very nice Q&A timing that was allowed when we could ask questions and interact with the speakers. I look forward, therefore, to joining many, many more of both the in-person, if possible, and definitely the online conferences, and I encourage all of you here and abroad to please do the same. At this point, I would like to thank Professor Satish Kumar. It's also wonderful, as I see the program, it's wonderful to see leading researchers from around the world talking on various aspects of probability, statistics, data science, along with dozens of junior and mid-career academics, as well as graduate students presenting their research. This is indeed a wonderful thing, and we definitely need more forums like this, where we can hear research that is being conducted by the next generation, as I mentioned before. As the president-elect of ISI, the International Statistical Institute, I would like to say that this indeed is the mandate of ISI as well, because ISI is determined to promote capacity development and the growth of statistics in this modern era, helping to make all the transitions that we must do in order to move seamlessly from theory methods, which is very, very important, to applications, and do a handshake with data science and AI. So you all must have heard of terms like probabilistic machine learning and uncertainty quantification, and I think the mandate is on people like us to carry that forward and to make sure that we move into the 21st century in a seamless manner. I'll say a couple of words about the International Statistical Institute. Many of you may know about it. It is an organization that was founded in 1885. It is housed in the Netherlands, in The Hague, but it has a very, very wide reach. And I believe that we would have elected members as well as regular members from all over the world. And at this point, if there are ways in which one can become an affiliate member of ISI as well. I think it is a very nice way to do handshakes with existing programs like this, so that together our goal is to make statistics develop and prosper, and to train a whole new generation of young people who will carry the torch forward. So I will say that I'm also very impressed by the presentations by grad students, as I said, and I think today we will hear about the award winners. So advance congratulations to all of you. And even if you did not win an award, congratulations to you all for carrying out the research and writing successful PhD theses. I wish you all the best in in being able to publish your thesis in very good places. But please be one word of suggestion, if I may. Yes, we are all comfortable in our comfort zones of what we have been taught and what we did for our PhD thesis. But today is the time when, with all the online interactions possible, you can be adventurous and take steps to learn new things. The world is moving very, very fast, and we can join forces both with domain experts from different interdisciplinary areas, as well as people in computer science, if you will, in order to make statistics stay relevant in this 21st century as well. So once again, a very warm welcome on my behalf to this conference, to everybody present here and everybody online, and I hope we all have a very good time at this conference. Thank you.
Invite the lamp. Thank you, dear Professor, for inaugurating the session. Now it's time for felicitations. We have
Mrs. Ron Wasserstein, Executive Director of the American Statistical Association.
Hi Ron, can you wait a minute? We are trying to see if we
It's a
can reach
video.
you.
It's a video. Yes,
Oh, you sent a video.
Yes,
I see. Okay, okay.
So I think he has there.
When you said hi Ron,
That's why.
can you say okay?
So now it's time for felicitations, and we have got our dear professors with us. Professor Kalyana Raman sir, who is actually the person who introduced computational statistics into Kerala, we should say, not just the University of Kerala, but to the state of Kerala. Sir has always been with us. His words were always an inspiration, and his blessings mean a lot to us. So, dear Professor Kalyana Raman sir, I request you to say a few words. Professor, I hope. Sir? Extremely sorry for the inconvenience caused. I think we'll continue with the session. So we have got our dear Professor Kalyana Raman sir online. Sir, we are waiting for your words. Kalyana Raman, yeah. Sir, sir, we can see you. No, it's not muted. What is it?
certification for the civil department, either in person or through online, and there's a wonderful interaction between students and others. So, then the same thing will continue for some more years, and everyone now also you need to participate, but in love, I wish the first, all success and care to those ones best wishes. Thank you. Yes, over to.
Professors and participants to please mute. Kalyan Ram sir, please continue. You are on mute, sir, right now. Please mute the mic, sir. Sir. Sir, you're on mute.
Yes, I did.
Kalyan Ram sir, please unmute. They're not able to hear you. Sir, can you hear me? Kalyan Ram sir? No, sir is saying it was mute. No, I'm not able to see him also. Kalyan Ram sir, we are not able to hear you, sir. You're on mute. So, thank you, sir, for your words of motivation. Now we have with us Professor Yagin Thomas, who was a former HOD of the Department of Statistics, the campus UGC Emeritus Professor, and he is also a continuous presence, a continuous motivation to all our efforts. Yagin sir, we are waiting for your words of wisdom. Yagin sir, over to you, sir.
Okay, shall I start?
Sir, please.
Professor C. Satish Kumar, President of this inaugural system. Professor Nalini, Commissioner of International Scientific Institute. My colleague Professor Kalyan Raman sir, other dignitaries, eminent professors of various statistical principles, giving life to all conducted experiments involving comparison of several papers. This thoroughly refers to the scientific studies in biology, medicine, agriculture, veterinary sciences, and so on. Before the investigation of these principles, the accuracy and efficiency of the studies were more or less much slowed, and hence the results are less reliable. A lot in the Green Revolution and the Red Revolution also. Invention of these some tests so that it helps the management of the industry to devise ways to correct the material form of sorrow in the quality of the product. Statistical principles for optimization is again helpful for maximization of the profit of industries. Similarly, investigate the problems and give us tools to tackle those problems. Moreover, the young group of people attending these conference and the students, it will be a great exposure to them about the way that they have to move in their assets. In such a platform, you should also share your ideas and become a part of the model approach of statistics. At this time, I'd like to mention the story to my young students. All of you know about the world famous sculptor Michelangelo. I will read this story of his survival days. When he was in a small child, he had another younger sister in the family. She was inside in a state. When the mother of the house, she looked at siblings in the house after feeding the infant daughter and she stayed in sin. She also died not able to lift up visually amazing temper. The boy later they took a charcoal piece and dragged the photo of the infant sister. When the man returned home and he was told for mother about the species of his and when she was seated, immediately the mother took the boy by the hands and kissed on the cheek and said to her, but the figure was just a circle and some lines with no trace of the infant sister. But Michelangelo in his later days said that the kiss of his mother when he saw the first figure by charcoal piece on the wall made wonderful things in his life. Actually, that allows this thinker and the probability of being a good sculptor. Like this Mariana Pons here, you draw your first figure by making use of the statistical ideas which are helpful for to shape the statistical strategies for becoming surgery. Now, I'd like to wish you all a nice meeting throughout the conference and make it successful in your future career also. On behalf of this Department of Statistics, I greet you all with my best wishes and carry on. You have a nice day. God bless you all.
University. He was the jury
Dr. Satish Kumar, Dr. Nalini, the President-elected International Circle, and all the delegates, experts on the line and offline. See, there were 12 candidates for Best Paper Award, and all were equally good in all regards. It was very difficult to select who the awardee. And for me, I think all the four are winners, but somehow I'm just declaring to coalition to only the I think all the four. Yeah. First, US Nile Best Panel Award. Hello.
Professor, which is not able to read.
Okay, thank you. So this paper award 125 goes to Subhadar from IIT Kharagpur. After this, Aliaba got this paper award 2025 goes to Mr. Sarat Sindhu Mukhopadhyay from ISI Bangalore. The DK Ghosh Best Paper Award 2025 goes to Ratu Dev from IIT Kharagpur. Dr. David Hegel Best Paper Award 2025 goes to Vinita Selrao of Public Health, Manipal Academy of Higher Education, Manipal. So thank you and congratulations to all the four awards. Thank you, Dr. Satish.
Thank you, dear Professor. So, I'll repeat this once more. So, the Professor Yuvaj Nair Best Paper Award goes to Shubha Hamdan, IIT Kharagpur. Professor Miss Alia George Best Paper Award goes to Sharat Sindhu Mukhopadhyay, ISI Bangalore. Professor D.K. Ghosh Best Paper Award goes to Rajadev, IIT Kharagpur. And Professor David Hanigal Best Paper Award goes to Vinita Serraro, Prasanna School of Public Health, Manipal Academy of Higher Education, Manipal. She is with us. So congratulations to this we'll go to our next session, which is distribution of awards. So we'll be distributing the awards for the year 2020-24. So the first one is Professor A. Mathai Best PhD Thesis Award for the year 2020. Very big congratulations to you. As you all will be knowing, it's a national level competition. So winning it is actually a great achievement. So once again, congratulations. The next award that we are giving out is the Professor T.S.K. Mothar Young Statistician Award for the year 2024. The award goes to Dr. Dada Saheb G. Godse, who is an assistant professor in the new college, Kolhapur. Is he present? No. So, yes, so on all of our the next award is a Professor C.R. Rao and Bhargavi Rao Gold Medal, which is given to the first rank holder of MSc Statistics in the 2025 pass out batch of the University of Kerala. The award goes to Mr. Akshay Paul. Because that's your So, congratulations, Paul. Yeah. We hope to see you in many more award functions like this with your future working statistics. Congratulations and all the best. So next is the Professor K. Kalyanaraman's gold, silver and bronze medals to the first, second and third rank holders of MSc Applied Statistics and Data Analytics for the 2025 pass out. The gold medal goes to Ms. Parvati M.J. So she's the first rank holder. Congratulations, Parvati. So the silver award, silver medal goes to Ms. Nitya Susan, who is the second rank holder. Congratulations. The bronze medal goes to, there are two, yeah, the third rank has been shared by two people. One is Miss Anishwara AC and Miss Archana V. I hope both of you are there. Anishwara is not there, so Archana is there. Oh, you are Anishwara. Okay. Please stand. Archana is also there. Please stand. Then the next award is Professor Brinda Devi Tampran Silver Medal to the second rank holder of MSc Statistics. Rai sir, happy to have you with us. I request you sir to please hand over. The awardee is Miss Anina Vijay. Anina Vijay, second rank holder. She's not there. Yeah, yeah. Please receive it on behalf of Anina. She's the second rank holder of MSc Statistics. And the next award is Professor G. Lesita Bronze Medal Award given to the third rank holder of MSc Statistics, Miss Rutina S. So, Paul, can you please come once more and receive it on behalf of Rutina? So, yeah, anyone can, but.
And Icstc 2025, I express my sincere gratitude to the professors, Asha teacher, Romeo sir, and Rajan sir to participate in this program. Now, on behalf of the organizing committee and the Department of Statistics, I express my sincere gratitude to my dear professor, Sadiq sir. Now, I express my sincere gratitude to Sugar teacher also, and I express my sincere thanks and all the congratulations to all the award winners of my dear students. And now I express my sincere gratitude to all the research scholars and MSc students and the faculty members of our department, especially Dr. Sumi Aya and the office staff of our department. And once again, thank you all. And finally, I express my sincere gratitude to the dignitaries present here from various colleges and various universities, those who are participating this event. And I express all the online participants also. So thank you all.
Thank you, Ria. I request you all to break for tea 5 minutes and be fast because we are running late. Okay. Be very, very fast. 5 minutes, please be back in. You can take your tea and bring it in here, okay? You can have your tea here itself.
അനൗൺസ് ചെയ്യിച്ചു പറഞ്ഞാൽ മതി. ഇപ്പം 5 minutes ടീ ബ്രേക്ക് ആയിട്ട് സാറിന് അനൗൺസ്മെന്റ് ആണ് പറയാം.
Professor Kalyanaraman, that brought his presentation award 2025. I request Professor Loganathan sir, Central University, Tamil Nadu, speak this library. Over to you, Professor.
Am I audible now? Am I audible? About 2025, because the final demarcation is going to be done tomorrow evening, and I am invited to announce the names of the teams. The teams are first team, Anjan district is by the types of the project is title of the project is integrated special line. That is service station of the this is premium prediction using NFHS data in Telangana. So these are the three things going to participate in the final round for Professor K. Kalyanaraman plus project presentation award for 2025. Fellow jurists are Professor K. Banu of Institute of Science, Nagpur, and David Kumar. Thank you. Over to the organizers.
To the convener for the competition, and congratulations to all the winners. So, yes, sir. Shortlisted engineers with eight researchers and projects and some background papers. And a third and now we'll be going into the technical session of today, the first technical session of the conference. We'll be starting in 1 minute.
Good morning, everyone. We are moving on the first technical session of Icstc 2025, which is US Nair Endowment Lecture that shall be chaired by Professor Nalini Ravishankar. Dr. Nalini Ravishankar is a professor of statistics at the University of Connecticut, USA, with over 2 decades of academic and research experience. Her research interests include time series analysis, Bayesian dynamic modeling, and predictive inference for data science, with strong interdisciplinary applications across engineering, biomedical science, and finance. She held several leadership roles in international statistical societies and has served on the editorial boards of leading journals. She is a fellow of the American Statistical Association and the American Association for the Advancement of Science. The keynote speaker of the first technical session is Professor Dietrich von Rosen, a distinguished statistician from Linköping University, Sweden. So, with great pleasure, I cordially invite you, Professor Nalini Ravishankar, to chair the session. Over to you, ma'am.
who will speak to us for 40 minutes, leaving the last 5 minutes for Q&A. Thank you, and Professor Rosen.
Yeah, thank you very much. First of all, do you hear me? Okay, because I don't hear you so well. Introduction. Okay, but let's go on. And yeah, first of all, thank you very much for inviting me. And it's really a pity I couldn't be there in person. It was really visa issues. So everything was booked and everything. So I look forward to it. But then for some bureaucracy and whatever, it didn't work out. So yeah, okay, thank you. So yeah, first of all, I would say it's a great honor to introduce or be the first speaker of this conference, which yeah, it's just a bit I'm not there. So today, the talk is about the growth curve model and some application of the growth curve model. So I have a bit continued with this, and now we talk about the bilinear models, and this has many names. For example, the growth curve model. So what I'm going to do is it's a very quick introduction, and then I will look into what one can work on. Also, it's not completely new what I'm going to present to you, but it's still, I think there are often questions around it. And not just technical questions, they're more of principal interest. And I also can say, since I hear pretty bad what you're doing, you're always welcome to write an email or contact me in any other way if you want to have things clarified. And the fact is also that I don't read many references now, but all these statements they are more or less backed up by published papers. Some by me, but also by many others. So, let me give a quick introduction, and then we go deep into what I call high dimensional, where you have more variables than independent observations. And in fact, the growth curve model is here very well suited, and yeah, one can do and really think about what are we doing here today, because there is a problem, I think, with our subject today, that we are relying so much on computers and algorithms, whereas the base we lose a bit of classical knowledge, statistical knowledge on the way, and I think one should discuss this. And then I will also say something today about a bit special when we have a rank restrictions on the parameter space. So you can still hear me?
Yes, please go ahead.
Okay, good. Yeah, then. So basic growth curve model. I write this equation with X equals to A, B, C plus E. So we should see X is a matrix, a P by M matrix, and it corresponds to the observation. It's a random matrix in the model. So it corresponds to the observation, and in this setting here, we have n independent columns, and they are placed side by side. So there is the P by M. And then we have a mean structure, ABC, where P is an unknown parameter matrix, where A and C are known design matrix. See, the C matrix is, we call it between individuals design matrix. It's like when we have different treatment groups, we have, when you have independent observations, you want to model in some way. You do it with the C matrix. It's exactly the same design matrix as in univariate direction or even in multivariate direction. The A matrix is also known as the within individual design matrix. And there you model the structure of repeated measurements or the structure of yeah, say just repeated measurements. And it can be a regression over time, but there can be more complicated structures. But the important is that there is a structure of the dependent observation. Because in the X matrix, each column is normally distributed. If they are non-normal. It's not a trivial thing to go from a normal to a non-normal, a normal to a non-normal. And it's based, and you will not see it, that it's about how to generalize the inverse of sums of squares matrix. If you have normal distributed variables, sums of squares matrix which are distributed, and then we know the inverse which are also the inverse which are distribution. But if it's not normal, the inverse of the sums of squares matrix is, we don't have it today. So then we have just to rely on asymptotics. But in some way, we don't, often the application of the model is in a pretty narrow mind. We don't have so many observations. So it's like mostly, I think there are designed experiments behind it. Also, we can apply it when you just have observational studies, but it's not so informative. I can also say that this model belongs to the third exponential family. So it means, in fact, that we don't have sufficient and complete statistics here. But the interesting part of the model is that we can find explicit maximum likelihood estimators. And then we can discuss this. And this is, yeah, it's some kind of a very interesting model. And there are still open questions. Also, the model has been available for 40 or since mid-60s, so it must be 40 years at least, or 50. Okay, and just to show you some of that it's not a trivial thing to estimate parameters here in the model. I have here you can see two normal equations. The first equation is obtained when you differentiate the likelihood with respect to B, and the other equation obtained when you differentiate the likelihood with respect to sigma, or to be more precise, the upper triangle of sigma, but it doesn't matter. But you can see the equations here, and of course, this equation, I will not, in order to show that this is really the maximum likelihood or likelihood estimates which you get, we should do something more. We cannot just rest on these equations, but they show some interesting parts. So first of all, you can see that it appears in the first equation, and we have sigma in the second equation, and sigma in the second equation is a function of B, and B is also shown in the first equation. It means that we have a very, it is really a non-linear equation system. So, and it's a bit surprising that you can find an explicit estimator to these equations. And the estimators are given here. And I just write up the linear combinations or bilinear combinations with A, B, C. I can also say I call it bilinear because we have A and C before. There are models today where in some it's vice versa, A and C are unknown parameters. But now we do it simple and say that A and C are known parameters. And we have these bilinear combinations which are unique. And therefore I'm writing up the unique. And they are given here with this, in fact, that's a projections on observation space. So we give this, so what you can see here, or the reason why I not present the B have this is yes, and then I need some assumption about the design matrix that they are a full rank. But this is always available and it's unique. And sigma is the matrix given here, and it's also unique. And sigma is always unique, doesn't depend on any. What you see in this expression is also a generalized inverse here, and we don't have to worry about it because in fact this expression is a projection, the first part, and it doesn't depend on the choice of generalized inverse. But it is an arbitrary generalized inverse here. And I think when you're working with linear models, you should always aim to have not results which depend on choices of generalized inverses. Okay, so now you can see the estimators here are not linear. The last part corresponds to the mean and the first is something else, but in this inside, that's some kind of estimated inner product. You see the sums of squares matrix here, and the sums of squares matrix is Wishart distributed. So we are weighting the MLEs with Wishart distributed, say, Wishart distributed weights. And therefore the distribution of such an expression here is more or less unknown. You can write up a distribution function or density function even, but it's difficult to use it. It's difficult to interpret it. It's just an integral. So already here we can see that we need some kind of approximation of the distribution. And it's available. It's available like through Edward expansion. Very good Edward expansion exists. But the dispersion matrix estimate is even more complicated, and I will not cover it. Okay, the picture I really like to produce is in some way to show the difference between the manual and it's about in some ways a tensor space. And I divided the interested spaces here in 4 squares. So we have a mean structure in this space, and then we have some kind of residual space. And then you see that the column space, we have an orthogonal column, orthogonal complementary column space here, and then we have a column space of A, but for these A models is the dependent structure. Then we have some kind of inner product defined by sigma. So if you go to estimate here, then we should estimate the inner product. But you can see in MANOVA, then we fill the whole space here, and then we don't have to think about the inner product. But the other spaces are the same. And here we have the city space, we have mean space, and estimates are obtained by projecting on this mean space. So what happens here is that we have here our residuals. I have 3 residuals here. I will not discuss them very much, but we have the starting point here, and then the first step is we estimate the sigma as an inner product, and this is done by the sums of squares matrix S. And the sums of squares matrix is defined by not all residuals, but 2 residuals. And you see this definition here at the end of this S. And once you have replaced sigma by this sums of squares matrix, then it's just more or less like a linear model that you project your observation on the mean space. And this is what they can see in the estimates.
Dietrich, can I ask you a question?
Yes.
In the previous slides, what was being had? I'm sorry,
Oh, it's a
maybe
maximum.
you missed what we had first.
Oh, sorry, no. Yeah, I'm talking too much about this model. So this, we have is a maximum likelihood estimator.
Which is obtained again using the normal equations.
Yeah, this is one way of doing it. But the problem is, of course, with normal equation that you have to see that it's complete for the whole space. So what one is doing is that one is looking at the inequalities of the likelihood. But I think I just wanted to illustrate here the non-linearity in the estimation problem.
Yeah, okay, all right, thank you.
Yeah, and thank you very much for it. Please interrupt me more times, just to clarify. I'm happy with it.
Thank you.
So, here we have, by the way, the estimates of the or maximum likelihood estimated. And then you can see the projection. This is an idempotent matrix here first. So this is projection of it. And here's another projection on the other side. And this has to do with this tensor structure. So there are two projections involved instead of one. Or you can put them together. It's just that the inner product here, if sigma would be known, you would have a sigma instead of s here. But now we are happy that we can replace s by, or sigma by s. Or it doesn't matter if something should be s by m, but it cancels out this m, the number of observations. Okay. Yeah, here we were. Let's continue. I just want to show you a bit what happens here, how one can think about these figures here. Suppose we have some restriction on the meaning. It can be like a priori information, when you want to test hypotheses. So we have bilinear restrictions here. And what happens is the fact that when we have a model with these bilinear restrictions, we turn to this situation where some part is cut out. And this is important to see that what will remain under the, say, null-hypothesis. We have to talk a bit about the extension now. Now we leave the Gaussian model and look at, I call it, extended Gaussian model. Can extend even or EDR, everything is extended by linear regression model. And we have two types here. So first of all, the mean structure is a sum of, say, profiles. You can call each, sometimes in literature you see that it's AIBICI is a profile. And you have it here also for the second one. But the difference is that we need a nested column space relation. So we need an estimate either on the design matrix, the C design matrix, or on the A matrix, which is another. And in some way, the models are equivalent, that you can't count from one model to another, but the interpretation of parameters is much better to distinguish these two cases. So if you know that you can estimate the parameter C, you know that you can estimate the parameter C and vice versa. But maybe the interpretation here is not the same as here. So there are different meanings of the parameters. And this is good to remember. And with this nestedness, when we have such a model as involved, it always it gives us a stair structure. And the stair structure indicates that we can estimate the parameters by certain projection. But it's pretty it's messy in some way, but once you have a look through the math, then it's pretty, it's structured, and you can present the result. And the spaces here are, I will not leave here. We have to look. So when we look at the extended growth on, then we have several steps involved. Not the growth curve, just one, but the steps here. Some way what we understood is that the first 3 profiles to reduce it two profiles but with some projections. And then you end up with the growth curve model by another step, another projections, and then we know what the estimate should be. And this is how it goes on. But on the way there are technical issues with the estimation of the inner product. So if you look at the final result here, what is when we have three profiles, it's messy. It's extremely messy here to see it, but everything, there are projections. There are projections, Q1 is a projection, and Q1 and Q2 are projections. But these are the kinds of actual estimates, and then you can put, and I write down them now here, I don't know if you can call them estimate, because the step matrices here are unknown quantities. So if you want to talk about the estimated thing, you need to put some conditions on the design matrix, so that you get unique estimates and then these terms happen. Actually, over here, it's just in the matrix generating the orthogonal complement to A1 plus 4C and C1 here. So these are just representation of basis in certain spaces. And if you have certain conditions, also these matrices cancel out. And it's the same. So, and if you want to look at a bit more narrow to these quantities, then these Q's, where they have these are orthogonal projections. So if the orthogonal projection on the column space of A1 with an estimated inner product Q2, then we have made a projection on the space of the orthogonal complement to Q1, and we have projected A2, and then we look at the orthogonal complement to this quantity here. And this is Q2. I might go on with Q3 also, but I see it. And then we have our sums of squares matrices here. But remember that Q1 and Q2, they are the random matrices. So they are all involved here in this estimate. So they are pretty complicated from a stochastic point of view. But the interesting thing is that we can calculate moments even on these estimates here, and explicit moments. And we need somewhere then the Wishan knowledge about Wishan moments, about the inverse Wishan moments, and the normal moments. By combining them, we can find explicit estimates or explicit moments. And then we can use Edwards expansion, for example, to approximate that. And the Edwards expansion are in fact which is very unusual. We get two terms in the Edwards expansion, we get the field approximate density. It's not common for Edwards expansion. Okay, there is a special concept here. In Manova which I'm going to talk about. And this is, we have Imanova, the Yorkshire part here, and then we have the Manova part here. And you can combine this as you can think about this as covariance, to some kind of profile, which is very interesting. But you can also do it vice versa. You have a Manova situation, and then you have this here, some kind of background information, which you want to take care of. And this is a special case of the extended growth model. And the picture is here. Here's a Manova part, and here is the Yorkshire part. And you can see that the whole thing is a bit simpler than with the stair structure, because you have a full space here due to the Manova. And we can estimate time. You will see why I use this model specifically. So now I'm going to a bit, non-conservative treatment of the neural or application of the neural. One is when we have more relevant observations. So if the covariance matrix is P by P, and we have less observation, and this is called a high dimensional part. So what can we expect to do in high dimension? No, we can expect to do tests of hypothesis in some way. Also, you cannot define likelihood ratio test, but other things can. Because the test quantity is a one-dimensional quantity. So even if we have more observation or more dependent variables, independent observation, we still have to form, or we can form the one-dimensional quantity, which reflects what we are expecting. And another way is popular today is to shrink parameters what you shrink estimation. Estimation equations or estimation functions, let's say. So you reach Lasso and whatever. And it's not really clear what Lasso is back here for the Johnson model. But I can do it. Reach we know pretty well. The Lasso, because you cannot differentiate Lasso or the channelize like the Lasso channelization, the L1 model. There are some problems, but it works. Or we can rely on either put some structures on the covariance matrix, or we just estimate certain functions. So if you look here first of all in the Manova case, and we have a P which is larger than M. We have a structure of this type. We have a beta here, or a beta which is P by Q, the parameter, is unknown. And then you can see immediately that we have a problem here. That if P becomes large, we have logs in a certain way, the number of parameters. So one should be careful when one talks about high dimension. One should be very careful about asymptotic set, because I think most approaches they are set P and M goes to infinity. But this is not clear what it means when you have two quantities going to infinity. You need to be more specific about it. And this, how you specify that, it will affect your estimates, or should at least do it. So one should be really critical to the literature which is published today. And but then if you look at the Grossman model now, we have this A matrix here. And A matrix means that we have a P by Q. P is fixed, but this Q means that we have fixed parameters. The Q which should be here in the Grossman model will always be fixed. And you can think about the regression. You can observe, you have a regression, you have a slope, and you have an intercept. But then you maybe have many observations over time. But you still have the same parameter space. So what will happen here now is that you will have a sigma which is treated with the size of the parameters. And so you will have infinite number or infinite sigma space. And we can think about sigma this as nuisance parameter. So the general topic is in some way to estimate parameters with infinite number of nuisance parameters. And there, I will show you quickly what can be done here, but there are many other things also. So here's one approach. If you start with sufficient statistics, we have a sum of squares matrix, and this is a mean, the projective. And what we're going to do is to see what happens when we have a so-called when we have a large observation, and we're going to suppose that P over N returns to a constant, sometimes called Kolmogorov asymptotics, or high dimensional asymptotics, or whatever. So, but we base our signal on sufficient statistics. And if you look at the sufficient statistics, we can see that the exponent in the normal distribution can be factored, or it consists of two terms. This is one term which is called the mean structure, and there's another term which is called sigma. Here is also sigma, but this term is free of the mean parameters. So we're going to apply some kind of restricted maximum likelihood. First, we estimate sigma from this part, and then that estimate is included here.
Dietrich, you have 7 more minutes.
Yes, thank you. Time is running. I will show you something about this year that we stopped. Also, I could talk about the month for some hours. No, but we have this other topic, P of n goes to constant, and the constant is known. So, as usual is high method, when you really apply it, what one is doing is just approximation. You really go out to the limit, because it's not clear what the limit is, and in particular, if you let both P and N go to infinity, not at least from theoretical point of view, it goes to C. Good, no constant. And the approach is a bit different what happens often in statistics, or has happened. At first, one, by intuition more or less, one starts to start with the sums of squares matrix often in this high dimension. And then we see the effect of sums of squares matrix, and then we start to interpret. Even though it's bit different, that we still let the parameters be into this T1 and T2. And then first we let the asymptotics, applied asymptotics, and then we estimate the parameters. Not that we estimate the parameters first and then go to asymptotics. So if you look at T1, and T1 is a complex square distribution. If you look at here, S is wish out, but if you take the trace here, it will be chi-square distribution. If you look at the characteristic types of the chi-square, we see that it's of this way, and we're going to utilize here now this relation, the P of N is equal to constant. And then we can see that if we expand the characteristic function, that we only need, in fact, 2 terms. The rest is equal to 0 when P over N goes to the constant. You see it already here that we have N and P here in the numerator, and the numerator we have P3. So this will go to towards 0. So we approximate the characteristic function or the logarithm of a cumulative generated function in this way. And then we can identify that this corresponds to a normal distribution. So what we have here is that if we standardize it a bit, that this quantity here goes to a normal distribution. So this was the first part. So we can, this A is just that it's asymptotic equivalent, and asymptotic important is called for asymptotic. If you look at the E square here, it's a bit different, because here we can see that if we square it, V transpose, then we have a fixed, it doesn't, the Gaussian distribution doesn't depend on the number of observations, independent observations. Because the degrees of freedom here is always corresponds to the reactor C. So this is fixed, this part in some way. So then, if we do the asymptotics, we have to rescale this T2 a bit, and we rescale to the square root of T. And then we get that this type of relation, that is also, that this relation is also asymptotic normal distribution. The nice thing is also, I'm going to tell you, that this T1 and T2 are independent of each other. It's like the T 2 is about the mean, Icstc. Whereas in the T1 we have the sums of squares matrix. And the sums of squares matrix under normality is they are independent. So here we can see also that normality is very important. So what we here is summarizing about the asymptotics, but then we form some kind of asymptotic likelihood here. And using this, we want to estimate our parameters. This is just the exponent of this normal distribution with the standardized version, and we see that we have it's a sum of 2 parts, but this is still complicated. So then the strategy will be to estimate sigma here and insert it in this place. But what is important here, we can never estimate all sigma, the whole sigma. It is natural. But when p goes to infinity, you just cannot do it. There are too many parameters, so you cannot do it in a good way. So we are going to, and the fact is we don't need all parameters in sigma. We just need those some, which some are related to the A matrix. So let's first see one problem here. If you want to maximize this part here, then we can see that we can always maximize it by choosing a generalized inverse of S. And we know that the generalized inverse of S is not the unique quantity. There are many. So that's the first problem. Which one should we choose? And it's not so clear. I put up this condition here, that the column space of this generalized inverse should equal the column space of S. It means in some way that we can estimate the same number of parameters sigma and sigma inverse. So that is pretty natural. That's and it turns out that this condition, in fact, if we have a column space of S inverse equal the column space of S, then it will be the more Penrose inverse, which is a unique estimate. And then we also have that the same number of parameters of sigma inverse and sigma can be estimated. So now we have an inverse, or we have an estimate of sigma. We insert this in the second equation, and then we get estimation equation of this type, where we have replaced sigma by its more Penrose inverse of S. This first part can always be shown to be non-linear, so and it's a scalar, so we can just cancel out or show the probability 1. So then we have this equation here. It's given here at the bottom, and this is a linear equation indeed. And this linear equation is consistent under some mild condition, so we should show that this A column space of A transpose the more Penrose inverse equals this here, and this one can show. So the general estimate of B in this high dimensional setup is given here. And the only difference with say the usual maximum likelihood is that we replace the S inverse with the more Penrose inverse, which is still nice in that way that this estimate reduces to the usual one. Of course, people have done this before, but it's not so clear why one should replace sigma inverse by S inverse. So now I will just show you one more slide, and then we can stop. And this is about if you see, this is the estimator of this full record condition on C and A. And then we should find the distribution. We know, or we cannot find the distribution of this quantity. And the pity is that we cannot even find moments here of this. or the expectation, we can show that this is, has an expectation which is equal to B, which is an unbiased estimator, using the dependence between the mean and sums of squares matrix, under full recognition of Icstc, you see that it's unbiased. But if you look at the dispersion, which that one should use, this becomes complicated. So here is the dispersion matrix, and then we have an expectation on this here. If we would have S inverse here, we would be able to have it. But with more methods, sorry?
Just one minute, please, to wind up.
Yes, it will be perfect for this. So if I want to use expectation here, the fact is we don't even know the expectation of the more Petrus inverse. So the only thing we know is, or when we have a sigma, we know that the expectation is the dispersion when sigma would be an identity. Then one can use some arguments about the orthogonality. So, so this is an open question. The only thing we can know is that we can find an upper bound for the dispersion. This is possible. We can find upper bounds for this S plus, and also lower bounds for this dispersion. So no, but these bounds we don't know how sharp they are. They're based on eigenvalues. So I think I stop here. So I have much more material, of course, as usual. But thank you very much for your attention, and feel free to approach me with any question anytime, including now also. So thank you very much.
Thank you very much for an excellent talk, Patrick. Any questions from the audience, either in person or online? Let me ask you one, save time. I was very intrigued by two things you mentioned. One is you mentioned the hypothesis. So I was curious in the broader context, what hypothesis are you thinking about?
Or you can choose different, say you have two treatment groups. If you just are interested in these treatment groups, then you just write B and F. But if you say you want to test, you have the repeated measurements, it's a regression over the repeated measurements, with an intercept and a slope. And if you say want to test that for one of the groups, that is just that the slope is a constant, no slope. Then you would have an estimated for F, or you want to have designated F and G. So FBG would equal 0 then. And this is, and then you can extend all the things.
So you're only thinking of a one rank hypothesis.
No, I can do more complicated. I can do more complicated as long as you always keep the stair structure. When you keep the stair structure under restrictions, you can do it. You know, what I told you, I have an old book with Colo and me. We wrote it around 20 years ago. No, I have a newer, that's maybe more explicit on bilinear regression models from 18. I can give you references like that. Then we have a number of different hypotheses. But the stair structure is essential. Otherwise, if you don't have the stair structure, you are in the model classes for seemingly unrelated regression. A multivariate seemingly unrelated regression. And then you incorporate knowledge from there. Which will not be maximum likelihood estimate. It's just because of maximum likelihood estimate when it's the stair structure. And you can, if you have other estimates, then you can have other hypotheses, definitely.
topics perhaps for young researchers here. You have mentioned something about regularizing and in context of likelihood, regularizing the likelihood function. I wonder if it's easier to do something in a quasi-likelihood framework. We have done something with the Godampe-Durbin estimating equations and regularizing it using a tag NLP. I wonder what your thoughts are on that.
There's often things. But you know, I have a bit different idea, or I was working with Finch for a while. And in my view, what we did there, we have in this paper, is instead of penalizing the estimation function, to think about restrictions on the pattern. So if you have quadratic restrictions on the parameters, but there should be no. This is the difference with usual ridge regression. So if you have known inequality restrictions on the parameters, then show some results. And what turns out then, which is a bit interesting, that it's not always advantage to penalize. So if you have this restriction and you have maximum likelihood estimate with full finger restrictions, then it's not penalized. So the idea is, yeah. So but it's of course you have to know what type of restrictions you have. You need that detailed information. And but if you have a small design, then you know approximately what the effect should be. And then it's possible to put up the restriction. But people today, they say sparsity and all the things. But anyhow, I think the area is open.
Pick something up and follow it. Thank you very much.
I'm sure they can. Oh, thank you very much, sir. Bye. Thank you.
Next time, we can meet together and will be here with us. Thank you so much for your good time endowment lecture. Even in the difficulties, you agree to that is online. Very useful now. Thanks a lot.
Yeah, thank you also for inviting me. So, yeah, hopefully see you in person.
Yeah,
bye bye.
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 Conclude this session. Now we are moving to the second session of Icstc 2020 area with the area that shall be chaired by Professor Kalyan. Professor Kalyan is the expert of statistics and research at the University of Cambridge in 2001 being the critics for the social statistics. He connected to fellow of the Kerala Academy of Sciences, the Commission to Innovation and Knowledge Sharing, and arrival leadership.
Speaker for the President of Spain from time to we look forward to over to you.
Because here, it is now it is okay, just to say from this, and can start this. Start? Yeah, that means waiting.
Shall we start?
Yeah, that's it. Yeah, okay, okay.
So, my God, I think this guy was not going to write them and take your word and go back. I'm very happy. I belong to the same institution from which you are coming. That is University in Madras, long back, 1964. So the whole history of association with radio state started with Department of Radio 6, University in Madras, somewhere in 1950. Now with about 55 years association with university. So, happy that I had to do. Effect of those of area Majas, perhaps many people here may not know the capability of area Majas may not be academically very right. But she was a great litigant. The sense that the entire department of statistics had one during that time 52%. Not an ordinary kind of capability of that. with the computer based. That is 1956 itself, they gave a computer very much, which we were using when we started coming in. After that, she associated lots of projects daily. There was 44 big projects. Control not well for the department. After retirement, I'm just getting so happened that I could see from the advertisement that he belongs to the same company. So that I to the happy. You are referring to the I'm saying okay. It's wonderful topic. We are expecting. Yes, I have. We do all the fabric university, the university area, which is the standard. As to now, this Sadhir Kumar is really wonderful.
Thank you. Thank you very much.
Glad for giving it. Yeah. Thank you. One second. Late.
for, should I, can people online hear me? I'm very pleased to give this talk here today. It's a talk on time series analysis, aligned with data science ideas and interacting with business. So all my information, I was just told by Professor Kalyan Raman that she was a very, very strong educator, and that is also close to my heart, because if you heard me from Professor George also introduced this PD program in demography, and this and similar activities are amazing for a pioneering female statistician. I see a lot of young women in the audience today, and I see these kinds of visionaries started their work in a difficult time when there were not many women in these professions. And so today, it's all the more, the onus is on you guys to do well and shine in your careers. And we look to people like this. And we have a few role models like this in the United States as well that we often look to for their contributions in these times. So let me talk about this problem. I'm going to go a little fast because I want to keep to the time. I'll give you an introduction to the title. Let me look at the title again. The title is Assessing Intervention Impact in Time Series Using Classes of Gaussian Process Models. So the title itself talks about many, many things. It says there is an intervention. First of all, there is a time series, and in the time series there is an intervention, and apparently it has an impact on the time series. But then one, as a statistician, must assess the impact, correct? And then, in order to assess the impact, we need to train the time series prior to the intervention well. Everybody knows about fitting models. You know about training data and test data these days. And you know the importance of training the training data correctly in order to get good results. Otherwise, you put garbage in, garbage out. Everybody knows that, right? So now we are saying we want to select a class of models which is flexible. It can handle a variety of dependencies, nonlinear, linear, etc. And I'm going to propose the GP prior process. We call it GP models, but it's Gaussian process. Gaussian prior process models. Okay, so all of these things are going to be going on. So for those of you that are looking to for a project or for a topic or something, there is so many things in which one can expand. So just take a look and maybe think about if I give one example about this particular collaboration, there again and again I emphasize that these are very, very generic ideas. So it's very easy for you to adapt them to something you are thinking of in a domain that you are working with. All right, please keep that in mind. So once again, let me thank Satish for inviting me, and I look forward to sharing my ideas with you. So I'll talk about the introduction to this whole thing. Then I will talk about something called pseudo-causal impact analysis. Causal analysis is something that you all probably are learning in some advanced course these days. It's a very, very hot topic these days in the globally. But I'm going to say something about pseudo-causal. So you will say why that is. And then I'll briefly tell you what this Gaussian process model is. But because I'm in a time series framework, I am going to construct a Gaussian process state space model, which is very, very peculiar to time series. But I know there are people here doing spatiotemporal. You can also build these models for spatiotemporal data as well. So any dependence, if there is, right? I can build a kind of model. And I call that the GPSSM. SSM is state space model. So GP is Gaussian prior process. So I am going to build a Gaussian prior process state space model, which can be used for time series analysis, all right, in a very flexible way. Then we all know what robustification means. Okay, there are lots of data with very, very anomalous data points, and that can happen without warning. And so maybe Gaussian is not enough, right? Then we have to go beyond Gaussian, and I'll talk about something else we tried but was very, very slow, and we ended up with Gaussian robust GPSSM. That is one. And then I'll talk very quickly about the example itself, which is an implementation of this whole thing for the IoT sensor time series data, which is the collaborative work we did with a company near us. So this is joint work with all the PhD students, please know. Patrick Toman was my PhD student. He did this work jointly with this company, and they created a position to hire him, which is really good. That means he really shone, right, in his work. And Nathan Lally is our strong collaborator, and he is from the Hartford Steam Boiler, which is the company that we worked with. Am I doing something? Then, this is another thing that I alluded to during my inaugural talk. Please notice that Raj, we call him Raj, he is the head of the Department of Computer Science and Engineering in UConn. So everybody here has possibly heard that when you talk about data science today, people are talking about this as a tripod. You think of statistics as one leg, as two with three legs. Statistics is one leg, computer science is a second leg, and a domain discipline is a third leg. So if you think about this as a tripod, I suggested that statisticians, in order to stay relevant and respected, we look outward. Yes, we have to be training ourselves in all the math, stat, and prob. I'm not saying no, we should continue to do that, but we should also look for examples outwards. We should be willing to collaborate with different domains, and we should do a handshake with CS. No point in fighting. So I think more is to be gained by working together. And I will tell you that contrary to all the things people say that computer science people don't respect us, etc., Raj and I work perfectly well together. And he is very, very willing to listen and see why uncertainty quantification is very, very important in a lot of the things we do. Okay, so please keep this in mind, youngsters, when you do your work. So introduction, IoT data is very, very common. I don't have to tell you everything, so you can read the first two sentences. Basically what they do is they install sensors in different places. The sensors all talk to one another, and they can all send data to a central location through a network, so that you can get a rich collection of data, and then you can analyze the data in one place, right? And so there is a growing interest among insurance companies also. And I live in a state where there are a lot of insurance companies, and therefore they wanted to come to us with a problem. They approached me with a question on how to do this particular problem. And here is the problem. They do real-time monitoring. They have an alert system to reduce costly adverse events, right? Everybody knows insurance companies handle risk. And so they wanted to come with a problem about that. So what is the problem? There are many, many buildings in the United States, and in some of those buildings who are clients of this company, they contracted to install sensor, just a sensor, which will record temperature. That's it, internal temperature. So they will come and put a sensor in the kitchen near the sink or something. They'll put another temperature in the bathroom, one in the utility area, wherever, you know, there is water possibility, pipes going, water pipes. And remember, places are very, very cold, so you can go below freezing point. And therefore, these temperature sensors will send data saying, haha, the temperature is going below 32 degrees Fahrenheit, it's going down, it's going down. And then this company, the Hartford Steam Boiler, wishes to alert the client, who is the building manager or the owner, hey, the temperature is dropping, your pipes might burst and you might have tremendous water damage. So risk of pipe freeze hazard. That is what they wanted to do. And why is it high frequency time series? It is high frequency time series because every 15 minutes a data value about an internal temperature is pinged. So it's collected. So it is high frequency in the sense of every 15 minutes time series, recorded by thousands of sensors that are situated all around the country. And these time series, if you start plotting them and observing them, they have very, very complex dependencies. There will be lots of missing values, there will be lots of anomalous, suddenly you'll have strange patterns. That is the nature of real data. So there are thousands of such sensors giving us all kinds of patterns in the time series. So nonlinear dynamics, heavy tail behavior, interventions, anomalies, etc. So the goal is, even although I'm talking about this domain, you work in a domain where you have such rich data with all kinds of complexities. You need flexible models, definitely, to handle everything. And you also need computationally feasible models, right? You cannot be sitting and running a model for 20 days. People will want an alert generation, and knowing something all happens in a matter of hours. So you must be able to do all of these things in a matter of a few minutes or maybe a short period of time. So that is the goal of this paper. So I'll just say, I said all this, but I'll just say this one more time, just a few points. So basically, temperature monitoring is done within buildings owned by end customers and which are susceptible to pipe freeze hazard. What is the goal? The goal is to automate the process of detecting. You want to detect that something is going to happen and addressing the adverse events. Adverse event is pipe freeze loss. Then understand, this is the important part where we came in. So I told you that all the temperature data is pinged to this company. So the engineer is sitting there trying to figure out. The engineer sees the temperature dropping. So they have like a rule-based algorithm. Before statisticians came on, they had a rule-based algorithm which says, aha, an alert should be sent. So they pick up the phone or they text or whatever they do to tell the customer, hey, there is a risk. Whether the customer is sleeping or out somewhere having a good time, whatever it is, they don't answer back. It's not as if the client calls and says, thank you, I'll fix it. No. So there is no feedback from the customer. Nevertheless, they said to me, you're a time series person, can you look at the data that is keeping on coming? The data keeps streaming. Can you look at the patterns in that data and tell me whether or not the customer took action? Is everybody with me? So we need to infer remedial action by the customer to an alert that is being sent from here. So that is the goal here. That is what we are saying here, whether they took remedial action. So this was given to us, and it was a team of statistics faculty member, my CS faculty member, and 2 graduate students. We worked with scientists and engineers from the Hartford steam boiler. Now the very first thing that we did, and I'm not going to talk about it, is that we modified their alert generation mechanism. I told you they were using a rule-based mechanism. They were not happy with it because it gave a lot of false positives. We all know the story of the child who cried wolf, right? You keep on saying alert is coming, alert is coming. Next time a real alert comes, nobody will pay attention to you. So nobody wanted, they wanted to reduce the number of false positives, and they said, can we use a statistical method, like it's actually machine learning, statistical, whatever you want to call it, method, to say when an alert should be sent. I'm not going to talk about this, but if people are interested in that kind of thing, you may have studied tree-based decision trees, random forest. I don't know if people are, you're taught that in applied statistics, but there are tree-based classification method. It's called random forest. Leo Bryman's work, and there is a specific type of random forest which is called isolation forest. So instead of classifying into groups, one of the groups is this anomalous data which is you're trying to identify. You're isolating something that is anomalous. So we started with the isolation forest, but that did not give us good accuracy. So we wrote another paper where we modified that isolation forest. So this was the first paper we published as a joint group in data science. Here is an example of the alert event. So very quickly, if you look at the page, you see 2 graphs, right? You see a graph on the top, which is the internal temperature that a sensor is recording. So this is, and then the green line or the blue line below it is the outside temperature that they got from some other data source and merged. So all of that stuff students have to learn how to do. Yeah. So now you notice that the outside temperature is definitely much lower point to point than the internal temperature, and that makes sense because every building is insulated. So you would expect the internal temperature to be higher, and also maybe we are running heat and stuff like that in winter. So this all makes sense. But now look at the red dotted line. The red dotted line, so anyway, the x-axis is time and the y-axis is the temperature. And notice that there is one little thing here. I said temperature imputed, and that is a lot of data processing must be done by students. And we teach our students to do that very, very systematically when they start doing research in my university and everywhere. You not only have to be a statistician these days, you need to know data engineering as well, because when you go for jobs in companies, they are expecting you to do what data engineers were doing before. So we teach them in R, Python, Julia, whatever they use, all kinds of merging, subsetting, all things they learn data manipulation very, very well. So in this case, they had to impute. Patrick had to do a lot of pre-processing. He had to impute the missing data which was all there and so on. So that is why I say imputed on the y-axis. The red dotted line is the time in which the company, let's say, sent an alert. Why did they send an alert? It is because the green line they are seeing is dipping, and they applied their rule-based algorithm, let's say, and the rule-based algorithm says you should alert. There is a risk of pipe freeze, so they sent an alert to the customer. Now notice that along with the green, the orange is also dropping, right? Because as the temperature outside drops, it's reflected by the inside as well. But then, this is the time at which alert was sent. Notice that the green keeps dropping, and then it of course stabilizes somewhere. I'm just talking only in the vicinity of the red dotted line. Right after the red dotted line, the green keeps dipping still, whereas notice what the orange did. The orange seems to have shot up after the alert. Remember what the question was? The question was, did the customer do something? So if somebody looked at this one sensor in this one time period, we think the customer took alert. But remember, there are thousands of sensors and many time segments like this. Nobody can keep looking at each one and so on. Hence the automation. We need to come up with a procedure that is model-based, that is accurate, can run very fast, and can be automated, so that once all of this work is done, the company runs the code and we don't have to be involved at all. That is how a project-based modeling and stuff like that works. Is this page clear, guys? And this is going to be the basis of everything we do. The whole point is, can I as a statistician tell HSB that at this particular alert, the customer took action or the customer did not take action? And there is no suspense. I'll tell you exactly right now in words what we do. But it did not happen. That is a counterfactual. I do not have that data, correct? But I'm supposing that that is what might have happened. But what really happened was going up. So as long as I build a very good time series model to this pre-alert training data, and I forecast in time series, that's all we spend our time doing, forecasting. So we forecast, let us say, the next 12 hours or something. And we want to see whether the actually observed data falls within a confidence interval, a prediction interval. In Bayesian words, we call it a credible interval, but think of it as a prediction interval. If this guy, does it fall within a prediction interval that I want? If yes, I can determine whether a customer took action or not. Fine? That's the whole story really. But then I'm going to show you some of the details and talk about all the GP models and so on. Okay? So this is, I said all this, but let's just quickly, I'll give you some time to look at all of this. But this is basically what I said in the first two paragraphs. Now I will say, then you say, okay, what kind of a model can I fit to the training data? Time series is a very, very rich area. And I'm sure I was told by Professor Satish that there is a time series class that's being offered here. Please take it. The whole world, data comes in time, right? Lots and lots and lots of time. So you won't lose if you take a time series class. So usually time series models are linear time series models, which means that the relationship between today and the past can be written as a linear function. That's what a linear time series model means. So classic examples of linear time series models, and they will teach this in an intro class, are autoregressive moving average models or something's called dynamic linear models. If you've heard of the word Kalman filtering, dynamic linear models are associated, they're Gaussian with Kalman filtering. And then there is Bayesian structural time series models. By that we mean you can say the time series has trend, some periodic behavior, etc., etc., and you can build a model for that. Okay, so these are the common linear time series models, and obviously we were in the Bayesian framework, so number 2 or 3 would be ideal for us. So obviously we tried these two things. That's what Patrick did first. All of these are very, very easy to use R packages. So just use R packages, put the data through it and see whether you get the accurate results. But none of these works. Who can tell me why? When will a linear time series models, where I'm saying that the temporal dynamics are linear functions, right? So I can write tomorrow as a linear function of today, yesterday, etc. So, students, when would I go beyond the linear time series models, do you think? When the what did I say in the very first slide? Not first slide, third slide or whatever. The next one. Remember I said that this particular time series, and therefore many, many time series that are coming out of realistic situations these days, have very highly nonlinear temporal dynamics. Therefore, if you fit a linear time series model to them, you're going to miss some information. Obviously, then your prediction will be wrong, and therefore you will be making the wrong decision. Therefore, the linear time series models will not be working. Now let us say, what should the model, the good model should have what properties? So we said any model that we use and that is relevant should be capable of handling diverse and complex time series behavior. Anything that you throw at me, I should be able to model. And it should be able to give me probabilistic forecasts, right? So if I say I want a 95% interval, 99% interval, I should easily get all those. And then allow automated model building. Remember I said Nalini is not going to be sitting in the Hartford steam boiler looking at everyone. We just give them the model and the code and then they run it. So it must be capable of automation very easily. And it must be resistant to false positives, and that is something we have to keep in mind. Remember, the original tenet was less false positives. So throughout the project, we carried that in our mind whenever we fit some. Okay? If you have any questions, you can just raise your hand and ask. No problem. This is a casual discussion. So I'm going to talk about how this pseudo-causal impact analysis is written, which is like the way to assess whether somebody took action or not. So this is a Bayesian inference framework for measuring the impact of an alert due to deliberate customer action. And we did not invent this idea. This was discussed in an Annals of Applied Statistics by Brodersen et al. Very nice paper, easy to read paper. If you know Bayesian analysis framework, you will understand this. So here is the setup. Suppose I denote by YT a month long, let's say, or I can do week long, 15-minute frequency sensor time series prior to an alert being sent at t equals n. So that red dotted line I call the time point n, and I am looking at the training data prior to that. In that particular case, with 1 month data, n was 2688. So it is there that I must train a suitable model. What is the next step? Then I look at the post-alert period. If you look at the post-alert period, how long you should look depends upon the problem. So we asked the HSP people, how long do you want to monitor whether or not customer took action? They said, I would like to look at a 12-hour window. after this alert was set. Okay, so we therefore said every 15 minutes, therefore my forecast horizon in the time series context is 48. H equals 48 is the forecast horizon. So now I'm looking at data 1 to 2688 for training, 2689 to 2736 for the impact analysis detection. Now, some of these words may not make sense to you if you are a non-Bayesian, but we decided to do this in the Bayesian framework, and it was not analytically tractable posterior. So every Bayesian framework is essentially like likelihood framework, except instead of maximizing the likelihood function, you maximize the posterior distribution, which is proportional to the product of the likelihood and the prior distribution. So if you want to estimate some parameters, you don't go in blind. You say, I am coming in with some prior information about the parameters. We call that, it's a proper distribution. It's a probability distribution that you give, normal, gamma, uniform, whatever it is you want. And then you say the posterior distribution of the parameters given the data is proportional to the product of the likelihood and the prior. You maximize that gap. That's the difference, right? So in that context, if the posterior distribution is not analytically tractable, we use some Markov chain Monte Carlo methods, approximate Bayesian methods, right? So then you generate samples from this posterior predictive distribution using MCMC methods, and this is going to be for the unknown 48 time points afterwards. So now, I'm now generating samples, which means I'm predicting. Let me call these predictions as y tilde t. So now let's go back to this picture. In this picture, remember I said that suppose this customer had not taken action, maybe the orange line will go down, and that is how I might predict it. So this supposed prediction will be y tilde t. Everyone is with me? Yt is the observed data. So observed data I observe, I have it. This y tilde t is going somewhere here, I think. That is called the predicted thing from my model. Obviously, why is the fitted model important? In order to get good y tilde t, I better have a good training model. Otherwise, it will be nonsense, right? Y tilde t could not be a good prediction. So those are the things that are very important. So now that you have this y tilde t, and when I say tau, it is that in the MCMC procedure, I can generate 5,000 such samples and so on. So suppose I generate using some MCMC procedure, capital B equals 5,000. That is indexed by tau. Tau goes from 1 to 5,000. So I have this. Then what I'm going to do is I look at, yeah. That has all been incorporated in this. I'm generating samples from the posterior. So I'm not telling you all the details. And this is just the broad stroke. I'll tell you later what we did. So we chose a prior. We first need a model. You need to know what parameters are in the model. Then you have to put suitable priors on. All that is being done. So let us assume all that has been done. And now I'm just talking broad strokes. You have data, you have samples from a posterior predictor, and then you compare, right? So this is what is being done. This is the observed actual data. Then we are going to construct an estimator. As I said before, most logical. Take the difference. See whether the difference is close or not, right? That's essentially what we are doing. So we calculate this Pt tau for each tau. Then we calculate a delta tau because this is a time series and I have 48 data points. So I aggregate across all of them, right? And then this will compute the posterior post-intervention effect. Then I say I will construct a 95% credible interval. And if the lower bound of this is greater than 0, right, we conclude an effect. That is because it is not two-sided. You can say, why are you not doing two-sided? It is because I don't care if the temperature goes up. The pipe is only going to freeze if I go down, right? So I'm only focusing on the lower limit. Again, depending on your own application, you might choose to do two-sided if you want. Is everybody with me? So it's a very straightforward idea. And you can say, should I do Bayesian? No. You could have fit any other frequentist approach and calculated something like the delta hat. All I need is a delta or not. So I'm technically doing a hypothesis test to see whether the true parameter supports the customer having taken action, or the true parameter does not support the customer taking action. I think it's a very nice idea, and this is in the Brodersen et al. Paper. This is what they said. But they used Bayesian structural time series analysis, which was a linear time series model, and therefore it did not suit our data. So we borrowed the idea of pseudo-causal impact analysis from Brodersen et al. But then we cannot use their model structure because it was too simplistic for the kind of complex data we have. Okay? So I'm just going to, everything here I basically told you. Some details, you can take these slides and write to me if you want. Therefore, Patrick said, why don't we use GP prior process models? Because we all know what it is and it can handle it. It is quite possible that this also may not have done a good job, and then we might have had to hunt for something else. But as it happened, this is rich enough and flexible enough that this was enough for the kind of work that we had to do. Is everybody with me? Like, no model is correct, true, right? You know George Fox is saying there is nothing like the correct model. You just choose the best you can given the data. All right. So we are going to talk about Gaussian process. It's a non-parametric regression model. It is, I'm going to talk about Gaussian prior process and then student T prior process, because remember I have heavy tail data behavior, so I want to be robust to that. And because that was very, very slow, I decided to do robust Gaussian in order to speed up the process. So once again, once I decided to do in the class of GP prior process models, you start always with Gaussian. If it works, great, right? Because it's so fast, it's the queen of our distributions, we all know. So there's no harm in starting any project with a GP prior process, just in the hope that it runs very well. Now, if the GP prior process, the Gaussian assumption is not sufficient, and there was heavy tail behavior, which is shown by how any kind of heavy tail behavior will be caught in the residuals, right? Residuals are your y minus y hat. So if you do y minus y hat, you will catch the residuals. The residuals will show you whether there is a possibility of outliers that you have missed. Then you start searching for distributions, and we thought we would use the student T distribution, but that was very slow. So Patrick said, why don't we try a scale mixture of normals, which is another way of robustifying, and that is what is being automated, I believe, in the company. Yeah? Or they will automate it very soon. Okay, so why are GP models? If people have never seen GP models, please Google it and read about GP models. They have very flexible non-parametric forms. They are very, very useful in a lot of areas. And the way we do this is to specify a prior. So I will talk to you after I show you the next slide. Okay, YT is my observed time series. For me, that is the internal temperature at a sensor, single sensor. I'm only talking about a single sensor now. And XT in a state space model is an unobserved latent state. The way I like to explain this, even if it takes another 3 minutes, to my students is the following. You can understand the state space model in some sense very easily by first looking at the observation equation. In the observation equation, I'm saying YT is a time series, therefore there are temporal correlations. Therefore, I would expect to see some YT minus 1, YT minus 2, etc. on the right hand side. Right? If you think today depends on yesterday, day before, etc., I would expect to see yesterday, day before's values on the right hand side. But in a state space model, you will not see it. Because in the observation equation, I'm only writing YT as a function of some vector or scalar valued quantity, which I'm calling XT. Then there is some error, okay, which we call observation error. So imagine something like this. Imagine that the ground, and then above the ground you're seeing YT. Yeah, so the YT is what we observe above the ground. But the reason why at time t takes the value, like, I don't know, 65.6, the reason it is 65.6 is because below the ground there is an unobserved stochastic process. Agreed? A stochastic process means dependence over time, correct? So there is an unobserved stochastic process which depends on the past. Let us call this unobserved stochastic process as xt. You never see it, it's latent. But xt becomes xt because of xt minus 1, x whatever. Everybody is with me? That is a state space process. So the observed time series value is determined through some function g as a function of unobserved below the ground stochastic process xt plus some error. So the error comes because of kicking up, let's say, right? Then I do need stochastic evolution. That's the whole point in time series analysis. The past history must inform me to go forward in time. So please look at what we call the state equation. In the state equation, this under the ground x at time t is modified by the same x at time t minus 1 through some other function f. And some error is happening, which is another bold wt. Is everybody with me? This is the state space model, guys. So if I talk about a dynamic linear model or a state space model, there will be two equations minimally. Observation equation, state equation. The role of the observation equation is to connect your observed time series with something on the right. And what it connects to is some function of an under the ground stochastic latent process xt. All the time evolution is happening in the latent process. And in this particular case, it is Markovian, right? Because xt only depends on xt minus 1. Now, g and f can be whatever functions. They can be linear functions, non-linear functions. Then you get different types of state space models. And now, that is just state space modeling. And you notice that I gave a reference of Durbin and Koopman. It is not Gaussian process. It's not a GP prior process. This is just state space definition. And Durbin, Koopman are standard books, literature on this thing. Now, what I am going to do in a GP process is to place a prior over this f function in the state equation. Remember, we want to allow this f to be completely non-parametric. So I am not going to say xt is xt minus 1 plus wt. I am not going to make f an identity function. I am not going to make it an auto-regression, nothing. I am going to make it a non-parametric flexible thing. So that is what we meant when I said we can specify a prior over the distribution of functions. The function that I am talking about is the f function in the state equation in a state space model. Okay? Now I'll show you some details. I mean, there's a lot of details which you may or may not comprehend now. So this general form for a state space model of Durbin and Koopman included linear models, Bayesian structural time models, as well as models governed by nonlinear dynamics. That framework is good enough for us. So in the HSB example, let me remind you, Yt is the internal temperature, remember? And then in the xt, I can put, remember, under the ground stochastic process, that can just be a scalar process xt. Then I can add all kinds of exogenous predictors I want. For example, I'm showing you, we added just the time and we added the outdoor temperature, the ambient temperature. In different the domains, you can do different things. Fine? So now this is what, again, I'm showing you the process. The GP state space model is defined by placing a GP prior over the state transition function f. It's the same model that I showed you before, and I'm just reminding you that that is what I mean. Now it starts getting technical, and I don't know, nobody can grasp all this in one shot because my students spend days doing this, obviously. So this is how this will look. This is how a GP process will look. So generative model that f function we say follows a GP prior process. Gaussian means it is enough to give the mean and covariance. Everybody agrees? It's governed by the first two moments. So I am going to give a mean process, which is a function of this underlying latent, and a covariance. That we all know, right? It's like a multivariate normal. Give me mean, give me covariance. Instead, we are saying the mean is a function of xt and the covariance is a function of xt prime. Once I do that, this is just the conditional property of a multivariate normal. We know this, right? Xt given f xt minus 1 is normal again. And I know how to write this thing. Agreed? Now remember the dimension of a yt. Yt's dimension was 2688 by 1. 2688 by 1. So this sigma x is really what? 2688 by 26. Okay, keep that in mind. Okay? So a GP prior process has two components. One is the mean function and one is called the covariance kernel. Now we have to, the mean is not that important, but we have to make a lot of effort to define suitable. What time should I stop?
Yeah, we can now please take the 3 minutes of time.
Oh, really? Okay. Some about 140. Sorry, my mistake. So you can use suitable kernels. They can be periodic kernels or RBS kernels. This all is like technical time series stuff. Okay. So you can do all this, or you can use a mixture of all these. Now the next few slides says how exactly we estimated. So that may be beyond the scope of people if you're not time series people. Therefore, if you don't mind, what I'm going to do is to make the slides available to you and then contact me if you have any questions. Alright, so we use this method by Dover et al., which is called probabilistic recurrent state space model, and all the remaining slides that I have for a few situations are all ways in which we implemented this model. Then we also tried a student tree that I said, and then we tried a robust Gaussian SSM. Same idea, the implementation steps will become more and more complex. I just have to explain that. There is one small thing that I want to say, and that is, remember Professor Dietrich was also talking about sparsity inducing. If the time series length is 2688, and I have to invert a 2688 by 2688 matrix, I might as well go to sleep, right? It's not going to work very fast. Therefore, this guy Dover et al. Said, let me select a small number. M is much smaller than n. That is a sparsity inducing step. Therefore, instead of 2688, if my student chose 250 or 300 for M, much easier to invert. Then of course you have to select the best M and so on, okay? That is one more step that is done here. But apart from all that, these are all the men. You see, there is a lot of formula that he had to work out. And the reason I showed this is because students should not be afraid of doing the math stuff. This is necessary even in a data science problem that we were handling. One had to do all kinds of mathematical calculations. Okay? So I will just say that, and then I will move to the this step I wanted to show you, because we used PyTorch and GPyTorch. Anybody using Python here? So we use these functions here, and then we have a set. This is the step that you have to give somebody to automate. You have to lay out things in steps so that the company can automate it. And this is how they automated it. So if you take a single time series sensor, so you have this, he changed the color here. So you have the blue as the internal and orange as the external. We trained the model. We built the pseudo-causal impact analysis, and then we built the prediction interval. So let me show you the prediction interval from two ways. The left-hand side, okay, it's right here, but everybody sees why this is the Gaussian. And do you expect the robust Gaussian to be wider? Yes? No? There's an extra scale parameter on which in a scale mixture of normals. So we are saying that this model covers all the blue values, which means nothing is out of bounds. Whereas in the Gaussian, some of the values are outside, which means it can be out of bounds. So that was our reason for saying, let us use the robust Gaussian, but you have to do something, right? So we wrote all of this, and like I said, there are lots of results. The results themselves are not as important because I think each of us does a different domain. For you guys, I think it is the method that goes stepwise from taking a problem and analyzing that is important. So I'll just leave this slide for all of you to see. In particular, I want to make students and other young professionals aware of a society that the International Statistical Institute has started in India. There is a chapter, it's called the Icstc India Interest Group. And there are two people that one can contact in order to become affiliates. They run a lot of webinars and they're going to do a lot of mentoring activities. So, any questions? Anything I could have done better in my model? Any thoughts? No? You can always write to me later. We just selected 1 month of data. But actually for the last thing, it was 1 week of data. We just need to know how much I need in order to capture the behavior. The more data I choose, it's okay, I guess, but I spend more time calculating.
So that intervention effect, does it go into the latent process model I have? So it will be in static, which depends on how you say it. Yeah, definitely. And then that effect can be seen in my observed process.
One would hope, right? But remember, it's not as if the latent process is just going by itself. In a Bayesian framework, suppose at time 0 you start at some x0, then you move to x1. Then the y1 once it comes will help you go to x2. It is not as if they are independently evolving. No. So this will go. Then once x1's posterior is obtained, y1 will come and inform x. Then you move to x2. x2 kicks up and tells about y2. That is how it keeps going. So absolutely. Oh, yeah. I don't know who is monitoring. Let's see the chat. Are there any questions from the online participants? Maybe chat.
Yes, no quick comments.
Okay, maybe no, maybe. Done? Okay, thank you very much.
On behalf of the organizing committee of Icstc 2025, I extend my sincere gratitude to Professor K. Kalyana for graciously sharing this session and for sharing his invaluable expertise. I also express my heartfelt thanks to our distinguished speaker, Professor Nalini Devashankar, whose presentation greatly enriched the session by offering valuable insights and perspectives. Finally, I would like to thank the audience for their active participation and engagement. Now, I invite Professor Satish Kumar to hand over a token of love and gratitude to Professor Nalini Devashankar. We will now have a lunch break for 45 minutes and resume the next session at 2:15 p.m. Lunch break for 30 minutes and resume the next session.
Best University Manager.
No, that's fine. On the phone. Oh, yeah. And
You would have left it there. Yeah, we'll check the. Yeah, most probably it will be there.
Rather put it here.
Maybe here.
Yeah, this is here. This is silent mode.
Thank you. Just don't. Yeah.
So you want to? That's correct. After this session, I need to share. You are the speaker. We can go with it.
അത് കുഴപ്പമില്ല ഒന്നും ലാസ്റ്റ് നല്ല ചേച്ചി ചീട്ട് വെച്ചാൽ മതി.
എന്തായാലും 5 മണി എത്ര മണി വരെ ഉണ്ടല്ലോ കുഴപ്പമില്ല ഡ്രസ്സ് മാറണ്ടേ നിനക്ക്
അതപ്പൊ
Wait, one minute. Somehow my first, my title page is vanished. What happened? I don't see anything. Well, if it starts from basic, then my title page. Just hold on. Okay, first page and the question. It's okay. That's okay.
No problem. No problem. You can just say something. whatever.
I don't know what happened. Even in my PDF, the first page simply vanished. It happens, isn't it? Okay.
Online participants also can. ഞാൻ ടീച്ചറോട് ഇവിടെ വെച്ചോ പ്രിൻസിപ്പാളിന്റെ ചാർജസ് പോയില്ല പവർ ബാങ്ക് പോയിന്റർ കണക്ട് ചെയ്യാം പോയിന്റർ ഉണ്ടല്ലോ
Page.
Okay, okay.
Good afternoon, everyone. A very warm welcome to all of you to this plenary session of the 11th International Conference on Statistics for the 21st Century 2025. Today, we have with us Professor Aparsh Roy as the chair of this plenary session. Dr. Aparsh Roy is an esteemed academician, philosopher, and motivational speaker. He is an associate professor at Christ University, Bangalore. Several research scholars have been awarded PhD degrees under his supervision. He is a member of research advisory committees and research evaluation panels. Now, I am delighted to introduce our speakers for the session. Our first speaker is Dr. Asha Gopalakrishna from the Department of Statistics, CUSAT, Kerala, a dedicated academician and researcher with strong expertise in statistical research and higher education. Joining her is Dr. Divya Kapara, a postdoctoral researcher in the Department of Mathematics at IIT Mumbai, who has published in reputed journals and actively contributes to academic research and seminars. With these introductions, I now respectfully invite our chair, Professor Aparsh Roy, to guide us through the session. Over to you, sir.
afternoon, everyone. Okay, welcome back. Post-lunch session, I can understand that post-lunch sessions are a little bit tough, right? Yeah, and trust me, our speakers who are there, like Asha ma'am is there, Asha Gopal Krishnan. She gave me a very interesting topic, like the topic I can see that Bayesian estimation of cure rate in non-homogeneous Poisson distribution, Poisson process, cure rate model. So I think that like every one of you are nowadays working on some model and some application-based thing. So ma'am came with exactly the same. So I think that, however, it is a post-lunch session, but still you can enjoy the session. So over to you, ma'am.
Or you can place a computer here, then I can press. If I press, it goes, right? Just solve this by then I will just start the day. Okay? Good afternoon, all of you. I'll be speaking on non-homogeneous Poisson process cure rate model and Bayesian estimate of its parameters.
If online participants are there, yes, we should use the mic.
Online panel. Are they there? Online?
So that you have to stay somewhere there.
Oh,
so they can see.
Good afternoon. I'll be speaking on non-homogeneous Poisson process cure rate models and the Bayesian estimation of its parameters. So I outlined my talk. I'm surprised that the first slide simply vanished. I don't know how. And I'm running it again and again. That doesn't just come. I don't know how. So please forgive me. So the title of my talk is Bayesian Estimation of Non-Homogeneous Poisson process cure rate model. This is a joint work with Surya CS, my student, and Professor Anup Divanji from ISI Kolkata. Surya has already got her PhD and now she is with Novartis. And in this talk, in this paper, what we did is we actually introduced a non-homogeneous Poisson process, and then we talk about the Bayesian estimation. Normally in survival, medical experiments, you would have a continuation of that experiment, because there is an experiment done on some medication for a certain period of time, and that if that is like working, what you do is you continue that experiment for another period of time. So this is a right scenario for taking up a Bayesian type of analysis, because you already have some book how you can work with a power prior, and a power prior has a parameter. It actually weighs the historical data, and I will show you how we have done an adaptive borrowing and how much importance we have given to the historical data given the present data to estimate the parameters. So that is the abstract of this work. So initially the outline of the work would be, I would go to the basics. I will introduce the non-homogeneous Poisson process cure rate model, and then I will come to the estimation.
Can you move the slides? Can you move the slides?
Okay. It doesn't work.
Yeah. No. Okay. It's coming. But at least.
Okay. So the next slide. So let's look into the basics first. The next slide. I think you can move it.
That's moving? What moving? Next.
Oh. Can't you do it to them? I have transferred it. Okay. Okay. Looking at the driving hybrid.
This laptop.
This laptop. This is that one. Oh, it's not that one.
So let me give you, if you can manually do this. Yes. What is the time to event variable? So time to event variable is time until a participant has experienced an event of interest. This could be either death, heart attack, or goes to a cancer remission, anything. So you are observing times. And statistical analysis of this variable is called time to event analysis or survival analysis. Statistical analysis of time to event variables, it requires different techniques because it has some unique features.
Not moving? Not moving.
Data from survival analysis has some unique features because most probably you don't get the full data. You have always partial information. There's a challenge of partial information. For example, somebody would enter into a study today and then he or she would experience the event. Next. Yes. He or she would experience the event. For example, let us look at this, MI. MI is my event. So if you look at the second person, he or she has entered the study and he or she has experienced the event at this standpoint. But if you look at the first person, he entered at this standpoint and he left and he has not experienced the event during the whole study. So there are dropouts. And look at this. This person has also not experienced the event. So we don't know what is happening after this standpoint, whether he experiences the event or not. So normally in survival analysis, you face the challenge of censoring. So there are many types of censoring, and a simple method, or the most simplest of it is the right censor data. Common and popular is the right censor data. So there are a lot of censoring schemes. You can actually look into N. Balakrishnin's work. He has done a lot of different censoring schemes. So you will have left censor data, right censor data, progressive data. So those are the challenges that comes in survival analysis, and that is why we need special techniques to handle, or else we will be overestimating or underestimating our parameters. There is also a challenge when it comes to design of your experiment. There you might actually truncate your population. So then you have to use truncated distributions. So including all this in your analysis is very important, and you have to develop methods including these. Next. So let me come to some notations. I denote P as a random variable representing time. The hazard rate is represented as HT. HT is defined as the ratio of probability of an event happening in a small period of time delta t with limit delta t going to 0. It is the rate, it's a hazard rate. And why this is important in survival analysis is, this would be easy to estimate, or we would be estimating the time to event and estimating HT, which in turn takes us to the underlying survival distribution. You have a cumulative distribution function corresponding to ST. I denote it as FT. And here I assume T is absolutely continuous. So I have a probability density function FT. So these are going to be my notations. So let us take an example. The Eastern Cooperative Oncology Group, it conducted phase 3 clinical trials, and it is known as the E1684 and E1690 using, this is a medication, interferon alpha 2B. This is for melanoma cancer. In these studies, participants were randomly assigned to receive high dose of interferon or undergo just observation without additional treatment. The initial trial was a 2-arm clinical study that compared high dose of interferon to observation. The study enrolled a total of 286 patients between 1984 and 1990. The observed time ranges from 0.0328 to 9.6 years and refers to time in years until a patient's death or censoring time. The percentage of censored observation was 31%. Now, this same study was repeated, we will see that later on, and that is known as the E1690. So now, we are going to trying to estimate or model this data, that is E1690, and we will use E1684 as the historical data. Next. So when you model the E1684 data, you just put a simple Kaplan-Meier. Kaplan-Meier is nothing but an empirical distribution for censored data. When you put that, you see that you're getting a non-parametric estimate of your survival function. And this survival function, as t tends to 0, typically should go to 0. But you will see here that it tapers off to a value. Somewhere to say 0.3 or say 0.2 point something. 0.2 something it is going on, and this is the red line. Right? So you can see that this ST is not going to 0. That means that there is a probability that there are some people who survive the disease, right? So if I use ST as a proper distribution, that is limit as t tends to infinity ST equal to 0, then I will have a bias in my estimation. I need to account for this. If you look into this, as t tends to infinity, it is going to some constant, right? Not equal to 0. So these models are what you call the cure rate models. So cure rate models are very popular in survival analysis. It is also popular in finance, sociology, criminology, economics, reliability studies. All these you can see these models have been used. Analyzing the survival data from such trials using standard survival models do not take the fraction of cured patients into account and will lead to a biased estimate and waste the information on that in the data. So, cure rate models refer to a class of survival models that deal with censored survival data with a surviving fraction. And they are also known as cure rate models or long-term survival models. The next one. The first cure rate model. The first cure rate model was actually introduced way back by Bong in 1949 and Bergson and Gage in 1952, where they actually studied cancer patients and they took a time period of 5 years. They looked into how many of cancer patients survived 5 years or so. And the model that they introduced was the mixture model. So these are, next one. The mixture model. So the mixture model looks something like this. The mixture cure rate model. That is, suppose I let T to be the time to event and Y denotes the cure indicator. Y is 1 if the subject is not here and 0 if subject is sensor. Then if I look into unconditional distribution of probability, the survival function model. This part is known as the incidence part, and this is sometimes called the latent part. So normally in survival analysis, you will have a lot of covariates. So the question now comes, how do I incorporate covariates into my model? You can actually incorporate it through your incidence parameter or your latent parameter, or both, of course, if you want. So this gives rise to many cure rate models. So I'll just go through it. So if X is the set of covariates, and beta is the corresponding regression covariates, then you have a lot of parametric incidence submodel. You have the logit length function, complementary log length function, probit, box transform. All this you can put it in place of pi, and you can get different cure rate models, general cure rate models. Next one. Suppose you choose to put it through the latency part, then you have the parametric pH latency submodel, parametric AFT latency submodel, you have the parametric AH latency submodel, parametric PO latency submodel. All these models come out of this parametric latency submodel where you put the covariate through the latency part. Now as an alternative to mixture models, there were models proposed based on tumor activation scheme and promotion time cure rate models. Now let me tell you how this is derived. Suppose an individual is assumed to have N carcinogenic cells left active after an initial treatment. Now Zj is the time until the jth carcinogenic cell produce an observable cancer mask. So we all have carcinogenic cells, but as it grows, it becomes cancerous. So Zj is the time until one cell grows to be produce an observable cancer mass. Zj are assumed to be independent, identically distributed with some distribution function Ft equal to 1 minus St. And the time to relapse of cancer can be defined as the minimum of Zj for j varying from 1 to n. So T is now minimum of this. So now probability of survival is, next one. Assuming your N to be a Poisson distribution with mean lambda, the survival function is probability that no observable cancer cell by the time T. So either you should have N equal to 0, or if you, in case you have a carcinogenic cell, you should have your Zs not observable, or they should be greater than T. So now since it's a Poisson distribution, it is e raised to minus lambda with this expression, and you get the survival function as e raised to minus lambda Ft. So now if you look into this, this is called the promotion time cure rate model. So this is also known as bounded cumulative hazard model. I'll tell you why. This is also called the proportional hazards cure rate model because this resembles a proportional hazards model. That's it. And now if you look into the hazard rate of this, it is always bounded, and that is why it's also called the bounded cumulative hazard model. If you take limit as t tends to infinity, you can see that it is e raised to minus lambda, and this once again is a pure rate model. So these are the different names with which pH pure model is called. So the next one. Now when you have T to be binomial, we are observing T. Now when you have your N to be Bernoulli, your N to be binomial, N to be geometric, you get your mix. For this Bernoulli you get a mixture model and you get different models. So in fact mixture model and all turns out to be special cases of this BCH model. I didn't include it here. There is a paper wherein N is taken as composon, and then you will get a whole huge class of cure rate model which covers almost many cure rates discussed in literature. Next one. Now, biological interpretation based on tumor activation scheme may not be appropriate because tumor cells can proliferate or die spontaneously, and a simple Poisson model may be inappropriate to describe the kinetics. So taking this consideration, we propose N to be a function of time. And hence we propose the non-homogeneous Poisson process cure rate. So here we let NT be the number of carcinogenic cells present at time t, and we assume that NT has a non-homogeneous Poisson process with intensity lambda t. The mean value of the function is integral 0 to t lambda u. And here now Sj I define as a time to inception of the jth carcinogenic cell, and Wj denotes the time since inception at time Sj required by the jth carcinogenic cell to develop into a detectable cancer mass or clone. And now I define the response function Yt minus Sj Wj as 0 if Wj is greater than T minus Sj or 1 otherwise. Now, I give a distribution for my Wj as St, and Wj is the time since Sj for it to grow into a mass, and here we give a probability for it not to grow into a mass. So you can have your limit t tends to infinity St equal to theta, 0 less than theta less than. In short, the St over here is also a cure rate model if you go that way. Now probability of Yt minus Sj Wj equal to 0 is equal to S T minus Sj, and if Zt is the total number of diagnosed carcinogenic clone at time t, Zt is nothing but the sum j equal to 1 to nt of this response function, and this is nothing but the filtered non-homogeneous Poisson process given in past. So this is the characteristic function, and it implies that Zt follows a Poisson distribution with mean expectation of Zt given by this expression in 10. So now if I take t to denote the disease-free time of an individual, then survival function of t denoted by S pop t is given as probability of t greater than t, or there is no carcinogenic cell, probability of Zt equal to 0, which is e raised to minus 0 to t lambda s f of t minus s ds. So when does this qualify as a cure rate model? This is discussed in theorem 4.1. So for a given baseline distribution Ft or equivalent baseline survival distribution St with limit of t tending to infinity St equal to theta, where theta can take the value 0 but it is less than 1, then limit of t tends to infinity S of t is equal to 0 implies that this your mean limit of the cumulative mean, that is capital lambda t, is infinity, is equal to infinity. So if your intensity rate is like finite, then you expect a cure rate, right? So this is a very intuitive result. So if you look into this, if it is infinite, if your intensity, your cumulative intensity infinity, e raised to minus 1 by theta alpha. Theta, you recall, it is limit t tends to infinity st equal to theta, that is the baseline. This is what I call the baseline parameter. So your cure rate now has like contributions from your baseline distribution as well as from your intensity. The bound of the intensity, is alpha. The limit of your intensity function is alpha. So both your intensity and baseline contributes to the cure rate in this model. Now this is the probability distribution function, and this is the failure rate involved with the non-homogeneous boson process. I don't think it's interesting. Now, this is also very intuitive. The non-homogeneous boson process, it reduces to the BCH model. It also reduces to the mixture model. Because initially you are having censored observations also. So this model is generally not identifiable. It is not identifiable, and we have to form conditions for it to be identified. So we have given a deep study on this issue, and this a paper in 2022 discusses the conditions for this model to be identified. And this is based on results of Hannon and Huang in 2014, who have given general conditions for cure rate models to be identified. So we now give examples of distributions belonging to this class which are identified. The table. No, next one. Yeah, examples. Okay, I'll be using this example, that is the exponential non-homogeneous boson cure rate model. That is why I put the slide over here. Here you use the baseline exponential and the intensity function also of this form, the exponentiated form. And this is known as the exponential non-homogeneous boson cure rate model. We have been able to show that this is identifiable. I will be using this distribution for my analysis. No, you can skip this. Now these are certain examples of the identifiable distributions. For the exponentiated intensity, you have these different baselines give you an identifiable non-homogeneous boson process models. Next one, I change the intensity function. I use the linear intensity function, and for these also I am able to get identifiable non-homogeneous cure rate models. I am not discussing it that way. So we come to model estimation. Model estimation is quite straightforward if you are doing a non-Bayesian. The likelihood estimate is like quite direct. You write the likelihood estimation and you just estimate the parameters. So we go for Bayesian analysis also. So let me give the notations. Suppose we have n individuals and yi denote the disease-free time of the ith individual. Yi is right censored. That is what I have assumed over here. Ci be the censoring time of the subject I, and we observe T1, T2, Tn, where Ti is minimum of Yi, Ci. The censoring indicator is delta. So you know that whether the first observation is like censored or not is given by delta, where delta I equals 1 if Yi is disease-free time and 0 if it is a censored time. And X denotes the P plus 1 by one vector of covariates and beta the corresponding coefficients. We introduce a covariate effect through the intensity function lambda t, and now the observed data is n t delta x. Let theta naught be the parameter of the baseline survival s. So now theta, that is theta naught and beta, be the vector of parameters for the NHPP model which we have to estimate. So theta naught involves the baseline parameter and beta the regression coefficients. The data is independently and identically distributed and come from an NHPP model with density function f of t and survival s of t, whatever we have seen earlier. So it is quite direct. You can do a maximization, and simulation studies have shown that this works quite well. A direct maximization works well. So next we go into, suppose we have suppose we have historical data, like data of what I showed you initially. Then we use the prior, we give a prior to the parameters. And how do I elicit the prior? So here, prior elicitation is vital in Bayesian inference. It is easy to use non-informative priors, but if you use non-informative priors, the posteriors may not be very easy. You will have convergence problem if like you don't have a closed form. And moreover, there's you get unstable posterior estimates. And informative priors incorporate genuine prior knowledge derived from historical data similar to past studies and are especially valuable when earlier research involves comparable treatments or covariates. So this is where this earlier is, we have data which have a continued study, that is you have earlier research with same comparable treatments and same covariates. But as I told you, their sample size may differ, their periods may differ, many things may differ. So that made, I'm sorry about this, this is Ibrahim, Chen and Sinha. The power prior proposed by Ibrahim, Chen and Sinha has been widely used as an informative prior when historical data is available. So now, let me talk about the historical data. So in the example, you had the E1684 study and you had the E1690 study. So the earlier one is the historical data, and now I'm going to analyze my E1694 data. So N0 denote the sample size of the historical data, T0 be the vector of observed times in the historical data, delta naught is the, the normal one, it is the censoring indicators, X naught is the covariates, and D naught is the, D naught denotes the historical data. So the posterior distribution of theta based on observed data is normally given like this. That is, you have a posterior distribution, likelihood, given the data, observed data, and this is pi theta. Pi theta is your prior. Initial prior, before the historical data, D naught is utilized. The power prior distribution of theta for current study is now defined as pi theta D naught A naught L theta given the historical data raised to A naught. So your A naught is like a weighting parameter type of a thing. How much weight you should like give to the historical data. And then pi naught theta is your prior of theta. So now the prior distribution of theta is defined as in 25. Here you have an extra parameter, A naught, right? The posterior distribution of theta in 24 using power prior in 25 now reduces to this one. So this is your present data which you have observed and the likelihood associated present, and now this becomes your prior. This becomes your prior. So in short, you are you're borrowing some information from the earlier study which has already been done. If you think that there is a lot of variation as far as covariates are concerned, as far as sample size is concerned, accordingly you adjust on this A naught. So when A naught is 0, you can see that it reduces to your normal Asian estimate. So here we use the, next. I use the exponential distribution and I carry out the analysis. I have given appropriate priors for my baseline and my intensity function. And let me tell you how this A naught is calculated. We don't know about A naught, right? So I'll just tell you how this A naught is calculated. So this is the normal thing. The posterior density is intractable, so we do this in CMC methods. So in simulation, what we did is, we took samples of 25, 50, 100 and 500. We use the exponential baseline distribution using power prior, using the power prior. Okay. So here, what we did over here is, we did the simulation for different sample size, 25, 50, 100 and 500. This is the present data sample size. And then we estimated A naught. So if you see that A naught, you see that as your sample size increases, the weight on the historical data is less. So taking a coup from this, we now fix our A naught value, and this is the adaptive borrowing that we have done, and we now fix the A naught according to this. Yeah, this is for 40% censoring. Also, we observe the same pattern when we estimate A naught as a parameter. So now we fix A naught as, for a sample size of 25, we fix it at 0.9, 0.9, 0.6 and 1 and estimate the parameters. So this adaptive borrowing is executed and the parameters estimated seem to be good. Next. So it can be observed from table 3 and table 4 that the optimal borrowing extent of prior information reflected through the estimate of A naught is 0.95, 0.90, 0.59 and 0.1, corresponding to n equal to 25, 50, 100 and 50. So, as the value of A naught reduces as sample size increases, or equivalently when the current data information weighs more on the posterior, the sample size of 100 to 500 is enough that we weigh the prior information for historical data with A naught equal to a value less than 0.5. Based on this, we were able to get the estimates, and that was shown in table 6. The next image. we applied this study? We applied this study in the Eastern Oncology Group data set. So we have our the study of a two-arm clinical trial involving melanoma patients randomized to one of the two treatment arms. The two treatments were high dose of interferon or observation by the Eastern Oncology Group. Study was repeated in different years. The first study was started in 1974 to, I forget, I written earlier, 1986 something, I forget. And the second one is 1996. Oh no, this is the one we have. These studies were done. You had a 1974, that is E1673, you had E1684, and you had E1690. So we now analyze this data using my historical data as the E1684 study. So this data is available in the SMCure package of our software. Patients with deep primary melanoma of Breslow depth greater than 4 mm, primary melanoma of any tumor stage with N1 regional lymph node or regional lymph node recurrence at any time following proper surgery of primer melanoma of any depth are chosen for study. These are very technical. What I understand is a certain mm was required to be included in the study. The study includes patients with various stages of melanoma and indicates the number of carcinogenic cells in each person varies with time. So these were the variables. You had the control group, you had the treatment group. Then we observed the relapse-free time, whether it is censored, and the two covariates we take is age and sex. The observed time ranges from 0.03 to 96, and the percentage of censored observation was 31%. So this was the maximum likelihood estimation, but we go to the patient. Next. So to illustrate the effect of covariates on cure rate, we consider treatment group IFN treatment group and control group X1, X2, and gender male, female. So this is what we get, stratified by treatment groups. Okay, so now, based on the positive results of E1684, ECOG initiated a second trial, E1690 in 1991, to confirm the results that initially enrolled patients from 1991 to 1995 and observed up to 1998 with a median follow-up time of 4.3 years. The study considered relapse-free survival time, which is observed time in the data set, and refers to the number of years until relapse or the patient's death or the censoring period, and it ranges from 0.0081 to 6.9 years. Here we, so once again, if you look at the A naughts, you can see that the A naughts were estimated at for different values. Here we gave different values of A naught, and you can see that the overall fit is given by EBIC and DIC, but LPML gives the predictive capability of the model, and we observe that this model works the best, that is A naught equal to 0.1 works the best. So we use that for a given model. Using the historical data, we estimate this. The next slide. Next slide. And we do a bootstrap estimate for the NHPP cure rate model to obtain the credible interval. The CPO-I values also show a random, that is the predictive. Log likelihood pseudo, I'm sorry. The CPO-I also shows randomness, that shows that the residuals also are okay, the predictive capability of the model is also good. Next one. So for given values of A0, the Bayesian estimates of the parameter with corresponding standard error, we did a bootstrap, and the corresponding credible intervals under the NHPP with exponentiated intensity and exponential baseline are presented. The fixed values of A0 are borrowed from table 9, which gives adaptive borrowing of historical data through estimates of A0 given the current data. So we observe that the model estimates are more or less consistent and not much sensitive to the value of A0. In all the cases, we see that credible intervals of the regression coefficients beta 1, beta 2, beta 3 include 0. That this is one thing that we saw, that is the, this part is still under investigation. Just take that previous. Okay. This part is still under investigation. And the work is still going on. So we are still working on this adaptive power and trying to fine-tune the model for different values of A. And look why we are getting this beta 0, beta 1, beta 2, having a 0 in the regression, while earlier studies show some they show to be significant. So that is one thing that we are doing. So yeah, these are just conclusion of my model. So we have an, no, that's fine. That's fine. That should be.
Okay, so can we go for the question? Okay, the hall is now open for discussions. You may ask any of the question, any of the doubt if you have, directly to ma'am. Please check if you have any online questions.
Yeah, online display was no.
Okay, no problem.
So if the likelihood method is really easy and fast, why should we do Bayesian?
Well, you have information.
But it doesn't have to be brought in through the parameters. We can try to bring it in some other way.
Like
you had, for example, in your previous thing, you had the entire data and the entire formulation. But oftentimes, information from the past only comes through meta-analysis. And this whole Prabal prior and all that stuff is only if you have the entire L, theta, etc. for the data. And you're saying it is very difficult to estimate AC. I don't know why.
No, it's not difficult.
But why are you then adapting? Why cannot you just put it as a parameter?
Yeah, we put it as a parameter.
But then why are you doing the simulation-based adaptation or whatever?
No. In the simulation, we estimated A0 to see how much
for different sample sizes.
Yeah, for different sample sizes, and we observed that.
That is fine.
Yeah. So then
how do you use that information in the real data analysis?
So in the real data analysis, we actually, for higher sample sizes, or whatever sample sizes we have, for example, sample sizes greater than 100, it was enough that you have A0 within 0.5 or something.
But why are you doing that? You should let that data decide. See, that is what I'm saying, as a very two-step or whatever. From simulation, you're learning something.
Yeah.
Then you're trying to put that. I'm asking why in the posterior distribution are you not able to generate, get A0 estimation? You can't write down the complete conditional and estimate.
A0 for the data.
It is not a data, it is a parameter for the
for the data.
For the in your posterior. I think this is a very roundabout and I don't know, I would not. Since you're still working on it, I'm just suggesting. Why not estimate the A naught as another parameter? It's not
Yeah, we did that in simulation, looked into the pattern. And
why
then
not do that in the data?
Yeah. Yeah, that I think I can do. Perhaps then I will not get a contradictory result.
That's what I'm saying. Maybe there is something wrong. You're putting something inside, right?
Any more questions? Okay. Thank you.
Okay, thank you so much. It's wonderful presentation and the work approach is really nice and the results are interesting. But as ma'am said, really this is the thing why you are going for this after simulating you are going for this event. Let the data talk.
Oh.
Right? Yeah, it's very good suggestion indeed. And hopefully students got a little bit of encouragement on that and they can try this approach and they can contact you for further progress of this work definitely. And in this, I'd like to ask everyone please big round of applause for the speaker. Thank you so much. And now we'll be going for another good topic, another good talk from our Divya ma'am. So Divya ma'am coming all the way from she's currently doing a PhD postdoc fellowship in IIT Bombay, but she's also teaching in teaching assistant. You said okay.
In the
Yes. So she's also teaching. So she will be sharing her research with you. So let's look at the research properly, and whenever you have any valuable suggestions, please give. And if you want to extend the work, that will be very much beneficial, because the purpose of such kind of conferences are to share our work with you, and your suggestions we can incorporate into our work, or else you can extend the work. So that is the main purpose. So please actively participate and give good suggestions. Okay, and especially I'd like to have a big applause for the audience, because they are really very nice. After post lunch also, you are so patient and you are like listening all those things properly. So really, a big round of applause for the audience. Okay, ma'am, over to you.
Hello everyone, I'm Divya Kappara. I first of all like to thank the organizers and Dr. Satish Kumar sir for this wonderful opportunity to present my work here. So I have recently, not recently, 2 years back I've completed my PhD. So my research interests are mainly in spatial statistics and spatiotemporal modeling. So as a part of my postdoctoral work, for 1 year I worked with the project National Disease Modeling Consortium, which is anchored at IIT Bombay. So it's a national effect of modeling various infectious diseases. So I, from a statistics background, I tried to learn and apply various statistical methods that can answer interesting questions in disease modeling. This work is an effort as a part of that. So this is an ongoing work with my advisor there, Professor Shweli Mukhopadhyay, and her PhD student who has recently graduated, Dr. Shubham Nipalikar. So I would also like to thank Professor Nalini Ravishankar for introducing the count data yesterday in the workshop. So mostly we have seen the distributions that are used, the parameter estimation, and we have looked at the count time series data. So my focus in this talk will mostly be on spatial count data, which could be of the form, if you imagine that you are interested in studying some dynamics of a random variable in the space of interest. It could be like country India or a state, even Kerala, and you have 14 districts. So in each of the district you observe the random variable, which could be some disease count. It can be say TB data or measles counts you want to observe, and here I have plotted dengue count. So this I have just put so that you have a clear picture of how the spatial count data looks like. So all the dots here are the centers of the districts. So you have the data on the counts of the disease over all the centers, and say you do not observe some data like in disease modeling. For some diseases the surveillance is very rich, so that you collect the data or the data is available from all the areas of interest. But there are some regions due to some policy restrictions or something, sometimes the data is limited and sparse, so you don't know the data in some places where you would like to predict. So our motive of this work is to predict the disease counts where if there is any missing data or something, provided that there is some spatial correlation in the data that is observed, which can be again tested using some wonderful spatial statistics methods like Morenci, and there are other tests. So given that there is some spatial correlation in the data that you have observed, and also you know some other information on the covariates that are related to that disease, so you would like to use that information and then also the spatial correlation that is present and predict the disease counts at the areas where it is not sampled or you are interested. So that is the main objective of this work, spatial prediction. And then another thing, like when you are working with disease data, one other important thing you need to consider is like when you are comparing two regions, you have count in say for the districts of Kerala, you have some count of the dengue case in Trivandrum, and you have a count in a separate district which has comparatively less population. So you just do not compare the counts directly. You try to first scale this with the population, say divide the count by the corresponding population, and then the districts are comparable in terms of the rate of the disease. So in our model, we also try to incorporate this population scaling that is required. So this is mostly the overview of the data that we'll be working at. And objectives mostly I have explained. We want to predict, and also based on the predictions obtained, we want to look at some other inferences that I will come to later. And another problem we have initially now just started addressing is that say you have data on some 30 regions and you are interested to predict in some other 5 regions where you don't have data. So it might not always be important or necessary to use the complete 30 regions data to predict the regions where you do not observe. Maybe sometimes a small sample of 30 regions is enough to predict even in a better way, and that sample can be obtained using the covariate information you have or any other data that is related to the disease. So that is one more thing that we will be focusing on. And this kind of work is of importance in ideally identifying the regions where there is high risk and where the policy makers are interested to make some intervention. Say in diseases, it could be if they are planning to provide a vaccination campaign, where to provide. So it's of interest to identify such high risk areas, and also then similarly the informed resource allocation and intervention strategies.
Is the rating plan public data or is it?
Yes, that's the public data. Yeah. So here that is just an example that I've put. I will not be working with that data because dengue has the temporal dependence as well. This is a purely spatial model. So that is the objectives of my data. So like ma'am was mentioning, sometimes there are other techniques where we do not need to assume any distribution of the counts. You can just directly work with the 2 moments of the counts that you consider. So in our modeling approach, we so far do not assume any distribution for the count data that we have. Instead, we assume that there is a latent process, say epsilon s, which is second order stationary, which means the mean is constant. Here there is further another assumption over mean, that the mean of epsilon s will be 1. That is to ensure that the random variable ys, which is the counts at the region s, the moments of that do not depend on the moment of the latent process that we have. And then we assume that the spatial dependence in ys is due to the latent process epsilon s, and that dependence is characterized by the covariance function
of covariance of epsilon Si Sj, those two regions that we consider, and it is a function of the covariance function that we assume. So this is also again we can estimate from the data what kind of covariance structure that I'll talk later. And so using this latent process epsilon s, we write the conditional moments of the count random variable ys as expectation of ys given the latent process will be the mean, the GLM mean that you all know. And now that we only include the scaling factor, that is the population that I was talking about. So now the mean is actually scaled by the region's population as well. And the conditional variance is also given as this. And one other assumption here that we assume that the conditional mean and conditional variance are same. This assumption, actually this model has been used in many papers. Some interesting papers are by Scott Zeger, where he has used it for count time series data. So the assumption of this conditional mean and conditional variance, they explain very well. This in turn brings in a very this in turn brings in a way to write the marginal moments of bias so that it accounts for the over dispersion and also the spatial correlation that is observed in the data. So using some simple algebra on the relation between conditional moments and the marginal moments, we can obtain the marginal moments of bias as follows. So now the marginal covariance between YSI and YSJ will include the spatial correlation function that is in the latent process, and thus account for the spatial dependence in the count data that we have. So this is mostly the information about the model that we use. So coming to some examples of the this covariance function, I said the latent process is spatially correlated. So that spatial correlation is modeled using some theoretical covariance functions. Some examples could be an exponential covariance function. So these covariance functions are such that the correlation between two regions is mainly depending on the distance between them, and they ensure that with increasing distance this correlation decreases, and this parameter alpha here accounts for the rate at which the correlation decreases between the two regions.
Can I ask a simple clarification question? Are you working with aerial data or point reference data? You said districts, but then you are looking at the center of the district.
Yes.
So you're geolocating it with lat long.
Yes.
So now you're actually working with point reference data.
So when I'm saying DIJ,
Why
it
wouldn't
will
you
be
work? Okay, we'll ask the question later. But this is point reference.
Yes. So when I'm saying DIJ, it will be the distance between the centroid of
The centers of those things,
yeah.
right?
Yes. Centroid between the two
Centers.
Yes. And yeah, this is one example of the covariance function. There are many other examples like Gaussian and Matter family of covariance functions, etc. So the marginal variance covariance matrix of bias in matrix notation can be written like this. And here the diagonal entries are the covariance of YSJ, and diagonal entries will be the variance terms. And yeah, mostly I explained. Alpha is the spatial dependence parameter that we would like to estimate. Now from the model, we see that there are totally the parameters that are to be estimated are the P model coefficients that refer to the fixed effects that are there due to the covariance, and we have the variance parameter sigma square and the spatial dependence parameter alpha. So here to estimate these parameters, we use the very famous generalized estimating equation approach by Zeger 1988. Here they have clearly explained how the estimation works. And so the parameter estimates of beta can be solved like we do in this quiz by solving the score equation this. But there are other two estimators that account for the over dispersion and spatial dependence. So here the estimation is done iteratively. It's like you start with an initial estimator of beta. So you choose an initial beta, then you get some consistent estimators of the sigma square and alpha to start with, update beta, and then continue until convergence. So here firstly to start with some consistent estimators of sigma square and alpha, one can use the method of moments estimators using the expressions for variance and covariance that we have, or else in spatial statistics one very famous technique of estimating the spatial dependence and variance is a semi-variogram analysis, which does nothing but it kind of fits the theoretical covariance functions that are there to the empirical data covariance that we observe in the data,
and chooses a theoretical covariance function which best fits the data. So this fitting can be either done using the methods like least squares or MLE. There is a complete separate literature on how to fit these kind of things to estimate the spatial dependence parameters. So we use a semi-variogram analysis to get the initial estimates of sigma square and alpha, and then to update beta in the iterative estimation that I talked about. We have, so first we rewrite the score equations using an initial estimates of alpha and sigma square, and this will be the update step for updating beta. And again, this estimation is well known since this mu that is involved in the update state, it's a non-linear function. Now we have a GLM kind of structure. To make it much simpler, we transform it to a weighted least squares kind of problem in this way, and then write an different set of score equations that will involve the linear x beta instead of any non-linear function that is involved, and then use it as an update step. So overall, as I mentioned, this will be the estimation algorithm. So with initial beta, you get the initial estimates of sigma square and alpha using the semi-variogram analysis, update beta, and then iteratively update until convergence. So now coming to a main problem, once we have the parameter estimates that we have, we would like to predict the response at an unsampled region. So if we were in a Gaussian setup, there is a complete very rich literature on this prediction problem, which is referred to as Kriging. So it is now slightly different. So Kriging is like the form of a predictor will be similar, and it is nothing but the conditional mean that we have in multivariate Gaussian. Here the form of the predictor will be similar, but it involves much more algebra. So here the predictor expression is obtained by using the Taylor series around the nonlinear link function that we have, and then assuming that the estimated beta hat that we have is close to the true beta star. So there are some assumptions and some algebra that is involved to obtain the predictor in a count data kind of structure. So this was discussed in the paper on Godway and Cressy and Godway-Stoke. These are the references that discuss this prediction. And the nonlinear link function and also these weights that are there to Kriging. So we have tried that. So another way we thought of getting a prediction distribution is using bootstrap. So that I will explain later. So now, since there are so many master's statistics students here, so bootstrap, if you're not familiar with, it is kind of a way to get a it's a resampling technique. So if you think of a simple linear regression, say y is x beta plus epsilon star, and you think of a residual bootstrap, like we have a vector of residuals, every time you get a sample with replacement of the residuals and get y star, and that will help you to derive the beta hat bootstrap distribution of beta hat. The idea is similar. Now if you look at the predictor expression here, this term at the end, y minus mu hat basically, is kind of a residual, and if you consider that and link to the residual bootstrap, so there is a paper by again Moulton and Ziegler, where bootstrapping in GLM models that use the update step for beta that I have shown, and there, so if I just go back, so here for bootstrapping in GLM, this Moulton and Ziegler paper discusses the way to use this y minus mu as the residuals, and then get a bootstrap estimate beta hat star, and then follow any inference that is needed for bootstrap. Only thing is that in that paper it was discussed for the independent case. Now note that our residuals here, since y is dependent spatially, even the residuals will be dependent. So to tackle that, a way of bootstrapping for linear spatial models was available. There what they do is just decorrelate the residual first by using a Kolesky factor. I'm sorry if I haven't mentioned it here. So get a bootstrap out of it from the decorrelated residuals, and then add the correlation back by post multiplying the variance structure that is there. So that's what we combine the bootstrap way of getting a bootstrap for GLM for independent case, and then the decorrelation in that process to get the bootstrap distribution of this y naught hat. So now, mostly I have discussed that in this slide. So now using that we can get a bootstrap sample of y naught hat star, and once you have this you can get it for b times and then infer on any interesting factors that you want to study about the prediction, like getting an interval. So we have compared
compared to the asymptotic normal approximation, the bootstrap was better in terms of coverage probability as well as the width of the intervals. And one other thing that we wanted to infer from the predictions is that like one interesting thing in disease modeling is that one wants to know, given the disease data and some threshold based on whatever disease information they have. Say for measles, it's like if the cases are greater than 5 or 20, in some places they consider it as an outbreak. So given some information on tau, which is, I'm talking about that count, where they consider it as an outbreak, and using the bootstrap prediction distribution that we have, we tried to form a way of kind of estimating the odds of an outbreak in a given region once we have the predictor. So the odds of any event will be as a ratio of the probability of that event happening versus not happening. So here we define the probability of an outbreak as that probability of the prediction being greater than tau divided by the probability, like it's not being greater than tau basically. And this estimate we obtain by using the bootstrap distribution for the y0 hat that we have. So it will be the empirical CDF. So we get an estimate of the odds here of an outbreak for any disease of interest. And to again obtain an interval around this odds, we can use the very nice asymptotic properties of empirical CDF that we have. So we use that to get an interval also. So we have applied this, all of this to some liver cancer data. I'll show that results. But before that, to summarize, this is what we have done so far. So we have a model to model the spatial counts that are over dispersed and spatially correlated. We have the parameter way to estimate the parameters that are in the model and the spatial correlation. Of course, we obtain predictions at the unobserved regions and got the bootstrap prediction distribution of the y0 hat that is there, and also we have an expression to estimate odds of an outbreak, which is nothing but the prediction crossing some threshold of interest. So we have applied all these methods.
Prediction of what crossing a threshold?
Say the y0 hat.
So the y0 hats that you predict should be counts or no? You're doing expected prediction,
yes,
expected counts.
Yes.
That's why it's real man.
Yes. Otherwise also we could also work with the rate as well. So y0 hat the thing divided by their population. Then also that could be another way to do it. So we have applied all the things we have to the liver cancer data. The main reason is that here the temporal progression is little slower. So this example we wanted to use as a training data set. We have planned to apply to the real data as well. So this is a very standard example in spatial statistics. It is a liver cancer counts in 56 districts of Scotland. So it also has some information on covariates such as the population in each district of the Scotland and also the percentage of workforce that are exposed to sun, which is given as a workforce that work in agriculture, fishery and forestry. That is considered as one covariate to liver cancer. And also it has spatial information on the centroids of the districts as well. So for this data, we know the case counts in the 56 regions. So we first tried to get an initial simple random sample of 30 regions. So like firstly we have fixed 10 regions where we want to predict. So that fixing we have done using the local correlation like LISA. So we tried to include the ones that are high, low and all kind of mixture. And then from the remaining 46 we choose a sample of 30 regions to predict those 10 regions, and these are the parameter estimates that are obtained. And so this was the total original data. This is the sampled y, the 30 regions that I am saying that are used to predict, and these are the regions that where the predictions are obtained. And also the root prediction mean square error using the theoretical expression that I have shown earlier. And then mostly we have seen that here it might not be much visible. The pattern of high and low has been captured well in the prediction that we have done. So then we have estimated the log odds. As I mentioned, the threshold tau here we have taken it to be the median of the y that we have. It is a very general threshold. And then the probability of that y0 hat greater than tau will just be 1 minus the empirical CDF from the bootstrap distribution. Those probabilities we have matched with the actual cases where y in those 10 regions, if it is actually greater than tau or less than tau. So it is observed that mostly 8 out of 10 regions have matched in sense that where actual y was greater than tau, the probability, the bootstrap probability that we have estimated, that is also greater than tau. That is also higher, sorry. So how much time do I have?
Go ahead.
So this is another thing. So earlier we have just initially taken a simple random sample of 30 from 46 I said. So we have further tried to get a better way of getting a sample from that. We are still actually we are working on. There are much more sampling methods in spatial statistics like importance sampling and other things. We have not been there as well. So the other 3 things we have tried is just we wanted to again the SRS is here because based on LHS the maximum of 16 we could get a sample. So we tried to fix the n to be 16 between SRS, LHS and stratified. But one interesting thing is that in stratification, we use the covariate information that we have, which is the AFF. So we have stratified the regions based on the quantiles of AFF, so that if it is an important factor, we'll have the sample from different levels of AFF that is there. So we observed that, of course, the stratification has the minimum PMS of those 10 regions compared to other 2 samples here. So further, first the predictions based on the stratified sample, we have estimated the log odds and the interval around the log odds using the frequency here. So mostly these are the results. So if we do it for a real data, this kind of representation will give us in which region there are higher odds of the predictions or the real actual disease crossing the threshold, given that we have the actual information on the covariates that are related to that disease and also the spatial correlation. And we are further developing this work. One interesting application we see that is effectively choosing a design, or by which I mean the sampling method to get an initial sample to get more effective predictions. That we are working on, and other than that, we are also working on applying this to other data sets. One is TB, is of high interest now. We're using the covariate information and the disease epidemiology that we know. And then we are also thinking like with varying threshold how this application would change. That is also something we're working on. These are some references. Thank you. Happy to take questions.
Okay, the house is now open for discussion. You may ask your questions directly to Madam. Any inputs, any suggestions, any doubts that may help?
First of all, very, very nice. Excellent. Couple of questions. This is district level data, aerial data, right? It's actually aerial data because it's usually disease counts and all we count at a district level.
Yes, yes.
So that is like
a total sum.
It's a sum across a district you aggregate. So it's aerial data.
Yes.
Why are you treating it as a point reference data?
So this is like this one particular data is at the district level, but there are some diseases where we have actual latitude and longitude of the patients, so not the total sum as in, and I see what you're saying.
Because especially because you mentioned to me dynamic modeling. If you go into the aerial spatial analysis, there are many nice models that exist, which are like car type models.
Yes.
That could be, not that this is wrong, but I'm just saying it's kind of, the analysis is fine. But the initial assumption of positioning it in the center of a district and saying why, it's usually not done this way, that's all. But maybe it's okay, people do it. But generally they treat it as aerial data and they put models that are relevant for aerial data.
So could you, do you suggest there are any examples that can be, so we are looking at the application. So far this methodology for such point reference data.
The conditional AR, hard models
yes.
are generally used, right, for aerial data.
Yes.
Without any dynamic. Here there is no dynamic. So you can just use a car model as a starting point if you want to do it in an aerial way.
One other thing is like we want to involve the covariate information.
Like card models, you can create. You can do all that. I'm just saying sometimes the aerial spatial analysis is richer. You will find a lot of papers, many more papers there than in the
So not in this
geostatistical.
work, but in other modeling work that I'm doing, there I'm using a card prior. So here the idea was totally from count time series to count spatial. So it's kind of fits in the initial stages.
It's all very nice, but sometimes a referee might question, why are you taking district specific data and then locate? You might be criticized, that's all. And you should have a valid answer for doing it. Otherwise they will say, why don't you get a aerial station?
Thank you.
Any further queries, online inquiries?
I have one more suggestion.
Yes.
Yeah, please.
Why are you selecting 30, 16 and all? First of all, that sigma YY in all your gear, that is dimension of location, right?
10%.
10%. That's what, 50 or something.
Yes.
Why do you want to select 30? I didn't understand the reason for subsampling.
So subsampling reason like we are trying to, so my advisor, Professor Shwari Mukhopadhyay, she works a lot in design of experiments. So we were trying to connect the design part to it because there are some surveys, like there is an open question on some diseases also conduct surveys. So it is about choosing an initial sample there. So the idea of choosing an initial sample is to connect to that example.
However, then let me point you to the research of my colleague. His name is Hein Wong. He and I have done some work, but he is an expert on subsampling. You can use lots of things. He extended it to time series. You can try and look up his papers and extend it to spatial. Random sampling, those are all old ways, right? That is a very new idea. You might as well be one of the first people to try it in spatial. Hein Wong, I can give you some references.
Yes, okay. Thank you.
Okay, any further questions? Okay, you may clap for the speaker. And very good suggestions, and it's truly like one thing I would like to add on that. So what are the questions you got? Either you may defend, like you have proper justification for that, or you need to work, try, negate them. Like that. It's good advices.
These are good suggestions.
Yeah, very good suggestions. And thank you all for listening patiently. That's it. Thank you, ma'am.
On behalf of the organizing committee of the 11th International Conference on Statistics for the 21st Century 2025, I extend my sincere gratitude to our session chair, Professor Akash Roy, for his excellent leadership and moderation. I also thank Dr. Asha Gopalakrishna and Dr. Divya Kapara for sharing their valuable thinking and research. I once again thank each one of you for your valuable time and presence. Now I invite Professor Akash Roy to kindly present a small token of gratitude to Dr. Asha Gopalakrishna. Next, I invite Dr. Divya Kapara to receive a memento as an appreciation. Now I invite Professor C. Satish Kumar to kindly present a small token of gratitude to Professor Akash Roy. Thank you, sir. With this, we come to the end of the session. We will now have a tea break for 15 minutes and resume the next session at
We are delaying, right? First day it happens.
4 o'clock.
4 o'clock you start.
4 o'clock.
The first day it will happen. Nearby this or Thamma or something. Okay. So nearby same address. You have tea and there. Yeah.
ലാസ്റ്റ് സെഷനിൽ ഓൺലൈൻ സമയം നമുക്ക് ഈ സെഷൻ കഴിഞ്ഞുള്ളത് ഇവരുടെ സെഷൻ കഴിഞ്ഞു അതിൻ്റെ ആക്ച്വലി ആ ടൈം കറക്റ്റ് ടൈമിൽ അങ്ങ് നടത്തുന്നതായിരുന്നു കാരണം അവർ ISC എന്നുള്ളൊരു പാർട്ടിയാണ് സ്റ്റാഫിട്ട് ഇതൊരു ടിനാൻ കിഞ്ഞാ ചെയ്തു എന്താ പറയുന്നത് ഓൺലൈൻ ചെയ്താൽ മതി അതെന്തായാലും ഇതായോണ്ട് കുഴപ്പമില്ല സത്യനാരായണ അവരുടെ ടീമിൻ്റെ അവരുടെ മാനേജ് ചെയ്തു ടീച്ചറിക്കാണ് ടീച്ചർ
ഞാനൊന്ന് പോട്ടെ ഇൻ കേസ് ഐ നീഡ് എ ലെറ്റർ ഒന്ന് അയക്കോ അപ്പൊ സർട്ടിഫിക്കറ്റ് കാണിച്ചു കൊടുക്കാം പക്ഷെ അവരിപ്പോ ലെറ്റർ അതാ ഒരു ഫോട്ടോ എടുത്തിട്ട്
ബാഗിൽ
അത് വേറെ
What do you say? Tea first or photo first, then tea? Yeah.
Okay, madam, the bag over it down.
So,
we have to take.
but I thought they said don't leave because it has computer. Oh, that bag. Oh, I'll come back here. Oh, that is it. It's over. Or?
Not over.
No, I'm coming back. It's just that my computer is.
What time you have to?
You tell me. What time should I leave?
Inside 5 or 5.
But flight is at what? 7:20, right?
7:20. 2 hours
It's
before.
7:15.
So 5:20 is better. After reach there. So you have to move from here 4:30.
4:30.
Because you have to go to the techno park.
Quickly. I'll only take 2 minutes. Drag my luggage.
So there is security sometimes in case.
4:30.
4:30.
Leave here at 4:30.
You leave here at 4:30. But 4:30 will come here.
നേരത്തെ ഇറങ്ങിയേക്കും ഇപ്പോൾ ഫോട്ടോ എടുക്കണമെങ്കിൽ ഇഫ് യു വാണ്ട് ടു ടേക്ക് ഫോട്ടോസ് വി ക്യാൻ മൂവ് നൗ ഇറ്റ്സെൽഫ് ആൻഡ് ജസ്റ്റ് ഫോട്ടോ സം വി ക്യാൻ ടേക്ക് യു ടു ദി ക്യാമ്പസ് സം പ്ലേസസ് ഇഫ് യു
Is there a talk or what happens after tea?
after tea there is a talk there is the Satyanarayana and the Manipal people they are about to be this talk.
It's already 4 o'clock, isn't it?
I think it's time for ma'am to leave. I think we have to take your things from the
Once you attend, you will have to.
Yeah.
Usually you have to be calculated.
Get my bag, Rasha. No, Rasha.
Should be enclosed in the top.
Yeah, I didn't realize it was 4 o'clock already. Okay.
I'll
write to you. Write to me. There are 2 nice things you can do. Because with sigma over inverse, then once your number proves your stuff.
You can take tea and
yeah. Sorry. Keep it. Yeah. Thank you. I didn't realize it was 4 o'clock. I hate leaving in the middle.
സംസാരിക്കുന്നു ഇതിൻ്റെ മൈക്കോ ഇവിടെ ഓഫാണ് ഓഫ് ചെയ്ത് വെച്ചേക്കോ ഓക്കെ പിന്നെ ഇവിടുത്തെ ക്യാമറ ഓണാണ് ഓക്കെ അത് കുഴപ്പമില്ല അത് മതി ഇവിടെ നിന്ന് വേണം ഷെയർ ചെയ്യാം അപ്പോൾ അവരുടെ പ്രസൻറ്റേഷൻ ICSTC 2022 അയക്കാൻ ഓപ്പൺ ആണ് അതിൽ നിന്ന് ഡൗൺലോഡ് ചെയ്യണ്ട വെറുതെ ഓപ്പൺ ചെയ്യും പ്രസൻറ്റ് ചെയ്യുക ഇങ്ങോട്ട് ഇവിടെ ഒന്നുകൂടെ പറയാം
അടുത്ത് പറയേണ്ടത്
ഇവിടെ പ്രസൻറ്റേഷൻ മെയിലോട്ട് അയക്കാൻ ICSTC 2022
അടുത്ത പ്രസന്റ് ചെയ്യുന്ന ആളുടെ ഇപ്പൊ മെയിലോട്ട് നമ്മൾ വാങ്ങിക്കാം
അയക്കാൻ പോവാ
ഒരു സെഷൻ
You know to use these things?
No. Exam.
Unfortunately.
Don't know. Yeah. എന്നിട്ട് അപ്പോൾ ഇതിലോട്ട് അയക്കാൻ പറയാം ഇപ്പോൾ ഒരു എക്സാമ്പിൾ എഴുതുന്നത് ഇതൊരു സ്ലൈഡാണ് ഓക്കെ ഇത് ഓൺ ചെയ്യുക ഓപ്പണിംഗ് ന്യൂ ടാബ് ഇത് എടുക്കുക ഇത് ഷെയർ കൊടുക്കുക ഇത് ഷെയർ കൊടുക്കുക ഓക്കെ ഇനി തിരിച്ച് ഇവിടെ കൊണ്ടുവന്ന് ഫുൾ സ്ക്രീൻ ആക്കി കഴിഞ്ഞാൽ തീർന്നു
വേണം സെക്കൻഡ് ഡേയ്സിലായിട്ടില്ല
We are going together to the airport.
Huh?
We are going together to the airport.
Where?
You are going to.
Yeah, I'm going to drop her in the airport.
We go together.
Oh, are you coming?
Yeah, we go together.
Okay.
That's why.
അല്ല എനിക്ക് സമയം കുറവാണ്
വേറെ ആരെങ്കിലും എനിക്ക് പോകണമെന്ന് എനിക്ക്
എന്നാ വേറെ ആരെങ്കിലും
എന്നോട് പറഞ്ഞ് ക്യാമറ അഡ്ജസ്റ്റ് ചെയ്താൽ മാത്രം നിന്ന് പറഞ്ഞു
Where's Prince? Prince is the expert.
I can't find anybody here.
Actually, during the conference like this, they should hire an expert.
Maybe not. I see. But last time I checked, there was something like that. Just check. Okay, otherwise we'll mail you. Both. I will open this and show this. Okay. No, slide more into the right. It was there. Share this button. Window. This slide. Interesting. Window. This slide. Share. That's fine. And you have to switch on here. This here mic. Okay. Here. This mic. This mic. So you can hear. Okay. Now it's off. Right? Now it's off. Okay. You see. And this audio button is off. Speaker button. So someone speaks from there, you will hear. That's because if someone it will echo. That's why I put it like that.
This is actually something that's PPP.
Yeah, that's. Yeah, you can.
Like, no.
You can use the phone.
No, this is halfway. Halfway.
That's happening with the
Department, ಅಲ್ಲ ಇದು ಪಿ ಡಿ ಎಫ್ ಓಪನ್ ಮಾಡಿದ್ದೆ ಇದು ಬೇಡ
ಅದೇ ಪಿ ಡಿ ಎಫ್
ಕನ್ವರ್ಟ್ ಮಾಡಿಲ್ವಾ
ಇಲ್ಲ
ಸೇವ್ ಎಸ್ ಪಿ
ಈಗ ಪಿಪಿಟಿಯಲ್ಲಿ ಮಾತಾಡ್ತು ಇಲ್ಲೇ ಇಲ್ಲಿದೆ what to do?
PDF file? Projector remote.
ಇದು
Each talk is 25 minutes. 25 minutes.
Each talk is how much time?
Sorry. First talk is
25 minutes. They are having 15.
So how much time?
No, I need 15 minutes. So they will take 13 minutes. Already finished. 1 hour. That's what we planned already.
Yes, sir.
We are from the same institute. That's it. I'll come. Yeah, last book. Yes. She's a student of Asham. She's doing PhD on Asham.
Can we start?
She's also doing under accounting. In Mangalore University. Okay, see.
I'll call you.
Okay. No, you'll take the. We try with PPT, it's not the full screen. That's why we convert it to the.
Using your laptop or?
No, this one. No.
You say share the slides.
No, yeah, take it.
ಶೇರ್ ವಿಂಡೋ ಅಲ್ಲ ಸರ್ ಅವ್ರು ಹೇಳಿದ್ದು ವಿಂಡೋ ಹೇಳಿದವರು ಎಂಟರ್ ಸ್ಕ್ರೀನ್ ಹೇಳಿಲ್ಲ ವಿಂಡೋ ಮಾತ್ರ ಶೇರ್ ಮಾಡಿ ನಿಮ್ಮ ಪಿ ಪಿ ಟಿ ಓಪನ್ ಮಾಡಿರಬೇಕು
ಅದನ್ನು ಆಫ್ ಮಾಡ್ಕೋತೀರ ಇಲ್ಲ ಬಟ್ ಹಾಫ್ ಇದು ವಿಂಡೋ ಹಾಫ್ ಸ್ಲೈಡ್ ಮೂವ್ ಮಾಡು ಸ್ಲೈಡ್ ಮೂವ್ ಮಾಡಿ ಇಲ್ಲ ಸರ್ ಸಣ್ಣ ಈ ಸ್ಲೈಡ್ ಮೂವ್ ಮಾಡ್ತೀರಾ ಸ್ಲೈಡ್ ಮೂವ್ ಮಾಡಿ ಅಲ್ಲ ನಾನು ಮಾಡ್ತೀನಿ ಇಷ್ಟೇ ಕೆಳಗಡೆ ಇರ್ತೈತಲ್ಲ ಡಿಶನ್ ಕೆಳಗಡೆ ಬಿಡ್ಬೋದು ಓಕೆ ಇದರಿಂದ ಅಲ್ಲ ಇರಲಿ ಹಾಗೆ ಇರಲಿ
Good evening, everyone. A very warm welcome to all of you to this invited session of Icstc 2025. We are deeply honored to be joined by an excellent panel of experts today. To commence the session, it is my privilege to introduce our chair of the session, the eminent and esteemed Dr. Divya Kapara. Dr. Divya Kapara is a postdoctoral researcher in the Department of Mathematics at IIT Mumbai. Her research interest lies in spatial temporal modeling and statistical methods for complex data with applications in areas such as disease modeling. She has published in reputed journals and actively contributes to academic research and seminars. We are pleased to have Dr. Divya Kapara as the session chair for this session. Under her guidance, we are privileged to have three distinguished speakers, Professor Satyanarayana, Mr. Sachin Acharya and Ms. Vashaki. I now respectfully invite our chair, Dr. Divya Kapara, to guide us through the session. Over to you, ma'am.
Thank you for the introduction. So, opening the session, we are honored to have Dr. Satyanarayana, an SD professor at Department of Applied Statistics and Data Science at Prasanna School of Public Health, Manipal Academy for Higher Education. It's a pleasure to have him with us. And the title of his talk would be Performance of Empirical Likelihood Ratio Classifier under Distributional Deviations and Outlier Contamination. Let's all welcome our speaker.
Good afternoon. My research topic is performance of empirical likelihood ratio classifier under distribution deviation and outlier contamination. I think this will be a easy topic if you are UG and PG students. Most of the concepts are based on the PG topic only. So we know that the problem of classifying individual into any one of the two population is one of the most common problem. Suppose it is health science data, often we have to classify whether the individual is having some disease or not. Suppose I have considered the anthropology, I have to identify the gender, either male or female based on the skeleton information, and we have many other applications also. So we know that the classical statistical theory will give a fundamental or easiest optimal solution when there is a parametric distribution assumption, especially the normality assumption will be there. And we know that if the means are well separated and we have the common variance, the optimal solution is in terms of linear. Whereas, if the means are separated and the variances are not same, variances are unequal, usually the decision boundary become non-linear and we'll have the quadratic classification rule to solve this problem. But the major question lies whether this classical theory will work if you deviate from the normality assumption. So that's why there are cases where when we deal with the real life situation, when we collect the data may contain outlier, there is a deviation of the distribution assumption also. Now the important question is whether the classical procedure is robust to the deviation from the normality. So there are many studies, Tiku, Balakrishna et al. Has shown that this classical classifier will not work when you deviate from the normality. That's why they have introduced a new method known as modified method of maximum likelihood estimator. So suppose, and then later in 1991, Balakrishna theoretically has proven or extended this work to the univariate case as well as the multivariate classification. They have called this method as robust linear classification method. And the performance under normal, non-normal model has shown that this modified maximum likelihood, instead of using usual maximum likelihood, if you go for modified maximum likelihood, it will be both efficient and robust to the deviation from the normality. On the other hand, in 1980, Owen has introduced a new likelihood method, that is empirical likelihood method, and we have worked few papers based on empirical likelihood. We started our work in 2019. We have introduced empirical likelihood ratio test for Bering-Fisher problem, where we compare with the usual 5 tests. In 2024, I have introduced 2. One is empirical likelihood ratio test for presence of autocorrelation in your linear regression model, and I have introduced empirical likelihood ratio test for testing the equality of variance among the several population, for which I have received the best paper award in the morning. So in the 2025, we have introduced empirical likelihood ratio test to confirm whether that particular time series follows AR1 or not. For that, we have developed an empirical likelihood ratio test. So based on the literature review, we came to know that the decision boundary of the linear classifier is heavily dependent on the parametric assumption. So to overcome this, in this paper we have introduced a non-parametric empirical likelihood ratio test has been proposed, and we have carried out extensive simulation study to compare our proposed estimator with classical, robust as well as the many non-parametric classical procedure to see whether it will be effective or not. So coming back to the methodology, suppose you are dealing with the classical linear classifier. Suppose I have a N1 observation from the group 1, N2 observation from group 2, and assumption is that both of them are come from the normal distribution with the common variance. So our usual question is, suppose I have a new observation for which class label is unknown, I have to classify whether it to pi 1 or pi 2. So according to the linear classification procedure, if you computed the V based on the sample mean, if this V value is greater than 0, we classify it to pi 1, otherwise it is pi 2. So second one is robust linear introduced by Balakrishnan and all. So they have replaced x1 bar, x2 bar by modified maximum likelihood estimator, and they have constructed it as VS star, they call it as robust estimator. If the greater than 0, it is pi 1, and if it is less than 0, it is pi 2. So these are the well-known theoretically established non-parametric method which will able to apply for the two binary classification problem, which is all are non-parametric method. Some of them based on kernel density, some of them are based on Wilcoxon type. So coming back to our proposed work, so we have introduced empirical likelihood ratio test for classification. The main reason is it constructs the decision rule by empirical likelihood weights rather than assuming any distribution function. So it is a data-driven likelihood construction so that new observation will be classified to the most probable class. So next, how will you construct the classification based on the empirical likelihood ratio? The first is whenever you have the new observation, first augment it to the first group observation, that is X. When you augmented the new observation, the first group, it is known as Z1I. Using the Z and Y, so based on the empirical likelihood we have to maximize this empirical likelihood subject to the two conditions. Sum of the probability should be equal to 1, and the second one is the moment condition. So once you identify that, we have theoretically shown that -2 log likelihood will leads to the equation A. So where lambda 1 is the Lagrangian multiplier solution. Now, so the new observation, previously we have augmented to the group 1 observation, now you augmented it to the group 2 observation to see that what is the likelihood that it has come from the group 2. Once you augmented the second group x0 to the second group observation, again we are computing the likelihood and we are maximizing. So once you derive the two component, that is minus log likelihood where the probability of it belongs to the group 1 and group 2, once you consider this ratio, if this ratio is greater than 1, if the ratio is greater than 1, that indicates that numerator is small. So what is the meaning that? We have computed the -2 log of empirical, which says that it is a degree of incompatibility. That means if the values are very large, it is not from the particular group of observation. So therefore EL classifier will assign the observation to the class for which after adding the observation, there is the least reduction in the empirical likelihood. Okay, that is the least reduction in the empirical likelihood. So next, what are the advantages? Even though it is not parametric, it is has the likelihood optimality characteristic is there. As I mentioned that in the literature we are having the robust linear method. So but in the robust linear method also there is a assumption regarding the location shift. There is a assumption regarding the trimmed or number of censored observation, and even it is parametric. Even though it is called as robust, but it is still parametric only. But when you apply the empirical likelihood ratio, it is completely non-parametric and it will compute the shape just based on the data only. Lights are not sure.
In the online it's not changing.
Is it joined from there?
No, sharing is fine.
This entire window. And this. Yes.
It's changed now.
Just give the height. So now coming back to the simulation study. In the simulation study, we have compared our proposed estimator with classical, robust and many non-parametric method. In the simulation study, what we plan is we need to cover variety of situations. Therefore, we have covered the various type of distribution deviation, outlier contamination, different level of mean separation as well as the sample size. These are the 10 models I have compared. And for the sample size, I have covered small, moderate and the large sample. I have covered both the balanced and unbalanced cases. If the equal sample size and unequal sample size also considered. And for the mean separation, I have considered very small value from 0.5 to 3, which indicate that too much overlapping and clear separation. That's cases also covered. And for the data generation, I have generated the data from normal distribution, uniform distribution, and I have considered one case of outlier contamination model also. Each simulation is replicated 1000 times and average is reported. Now coming back to the result, look at this. So when data is from the normal distribution with equal sample size and the delta is 1.5, that is the difference between the mean, we can see that our model will perform much better compared to the robust and the Udimoto. So compared to those 10, our method will perform little better, and those superiority will be increased when the sample size is very large. You can clearly see that empirical will outperform all other 10 classification models. This is for unequal sample size 80 and 20 and delta equal to 1. This is for 100 and 110. Then this is the case regarding the outlier contamination. Suppose the data contain outlier, how it performs. our model will performs first, second followed by the robust linear what is introduced by Balakrishna et al. This is the other scenario, unequal sample cases. Then uniform, when I generated the data from uniform, there is a clear-cut superiority of the empirical compared to the all, even the robust as well as the Udimoto, which is work based on the Wilcoxon method. So the sample size as I increases, the superiority also increases. Even for the unequal sample size also, empirical likelihood method has the highest accuracy compared to all other in terms of both class 1 accuracy as well as the class 2 accuracy. Both will matters when I deal with the classification problem. So as a real life example, so I have considered oral squamous cell carcinoma data set. We know that in the oral squamous cell carcinoma, lymph node metastasis is the important things to detect. Suppose if you detect early, we can go for the better treatment. We have to go through the literature, and literature show that neutrophil lymphocytes ratio as well as platelets to lymphocytes ratio that has been considered as one of the biomarker to identify the lymph node metastasis. So we have collected the data from our hospital based on those who are undergoing the OSCC, oral squamous cell carcinoma. The data set consists of 232 observations. Initially the data set was having platelet counts, lymphocytes count, neutrophils count. Then we have computed the ratio, PLR ratio and NLR ratio. This data is collected to answer an important question that can I use PLR ratio as well as NLR ratio to identify the metastasis status, whether N positive or N negative. What is its discriminability? Here I am not dealing with the whether it is a significant predictor or not, whether it is able to distinguish as a screening procedure. So that's why this is the sample statistics of the data what you have collected, and I check for the equality of variance or not, because if it is variance are equal, then only it is linear, otherwise I have to go for the quadratic. So first I have considered NLR ratio. Class 1 means N negative stage, class 2 means N positive stages. So based on the single NLR ratio, we are able to, you can see that class 2 is 70%. So 70% of time, the data, 70% of time, we are able to detect the class 2. So which was high compared to all other. So empirical likelihood method has the highest accuracy compared to all other methods. For class 1 and class 2 accuracy, this is based on the PLR ratio, platelet to lymphocyte ratio. Here also our proposed method outperforms remaining method. So across the method, what we have compared, PLR and NLR demonstrate a moderate discriminability. We can see that it is around 60 to 70. It is moderate discriminative only because one ratio we are able to use to distinguish the stages. Then out of all the method we have compared, empirical likelihood was the superior, and important thing is it has the highest overall classification of N positive. That means N positive in the sense that the cancer has been spread to other part. So that stages is able to detect with higher accuracy compared to the N negative. And we are able to conclude that PLR, NLR, we are also agree with some of the studies that we have compared, can be used as the relevant discriminative information as to screen the patient whether they are N positive or N negative. So overall conclusion is that in this paper we have introduced empirical likelihood ratio based classification, which is completely non-parametric compared to other density based classification or bandwidth selection. We do not rely on any kind of assumption. It is fully non-parametric, and our main aim is to whether it is robust, because sometimes it may be work for normal cases. We need to check whether it is work under non-normal cases and outlier contamination data also. Its robustness, efficiency and classification accuracy has been validated for many cases. And what the conclusion we got is, for the normal cases, what they have proposed, the robust classifier will almost equally perform along with the empirical likelihood ratio test, followed by Udimoto procedure, that is Wilcoxon test based one. But when we deal with the non-normal data and when we deal with the outlier, because empirical will construct the weight based on the data, if the data is too extreme or the outlier and all, it will assign the small weights so that it will suppress its contribution. That's why for the non-normal data, empirical likelihood has a superior power compared to the robust as well as the second one, Udimoto procedure. So overall, we are able to conclude that for irrespective of sample size, for non-normal data, if it is normal data, more than 100 samples, the proposed empirical likelihood ratio test has superior performance in terms of class 1 class 2 detection, both, because sometimes if you are not able to detect class 1, if the class 2 accuracy is 100%, there is a chance that overall accuracy may be more than 80 or 90%. But here our aim is sensitivity, specificity, both should be higher. So that's what we are aimed for, and we are able to identify that with the help of the proposed classifier, we are able to apply to the real life situation where it is able to identify its discriminant ability, which was a little higher compared to all other non-parametric approach. We are compared with the non-parametric method with the non-parametric approach only. It has the better accuracy compared to the existing method, because those are the theoretically derived approach. And this can be used so that we are in the position to now the future work will be extended to the multivariate cases, and when the variances are not equal, we have to develop it for the quadratic. And in 2019 paper we have shown that when the variances are not equal, so it does not directly follow chi-square distribution, we have to make use of scaled version. So in the variant Fisher problem we have derived the scale construction, so that a lot of work is pending regarding the quadratic form, multivariate form, and I need to compare with some of the machine learning part also. So for this I have represented only univariate cases, where I compare with those who are developed only for the univariate cases. So these are the few papers I have referred for my research. Thank you for the opportunity. Thank you for the question.
So anyone has any questions? I just have one quick question. So, is there any application you would suggest for this methodology, like any other data that?
As the result indicates that it can be applied for both normal and non-normal data. So once you check with the normal data, non-normal data, if there is an outlier, so we can apply it for the binary classification. So major thing is we need to check for the presence, we need to check for the equality of variance. So then only this is the linear form. So that if the variants are equal, then only it can be directly applied. Otherwise, we have to go for the quadratic version of the empirical likelihood ratio test.
Thank you, Dr. Satyanarayana, for the wonderful talk. Let's all thank you. Next, we have Mr. Sachin Arya, a research scholar at Manipal Academy of Higher Education. We are pleased to have him. And the title of this talk would be Performance of K-learned Classifiers in Extremely Imbalanced Multi-Class Data. I now welcome Mr. Sachin Arya.
Just check also.
PDF.
Good evening everyone, myself Sachin Arya. Today I am going to present my research work on the topic performance of classification K-learned classifiers in extremely imbalanced multi-class data, under the guidance of Dr. Asha Kamath and Dr. Satyanarayana. So multi-class classification models are widely used to predict the multiple categorical outcomes. So here the class imbalance is a common issue in classification tasks where classes are significantly, some classes are significantly underrepresented and compared with the other classes. So here the underrepresented classes are called the minority class and the other classes are called the majority classes. So this class imbalance leads to drastic impact on the performance of classification models. So we can see the real class imbalance in real life scenarios such as fraud detection, spot filtering, medical diagnosis. So class imbalance is defined based on the ratio of majority to minority class instances. So here the class is said to be imbalanced if the ratio of minority to majority is 1:4, which is defined by Kennedy et al. 2024. So here is the table which represents the definition given by the various authors on extremely imbalanced or high imbalance class based on the imbalance ratio. In our study, we are going to consider the definition given by Siddhartha and Ambalapa. So, to overcome class imbalance, data balancing techniques such as undersampling, oversampling strategies were introduced, which handles the class imbalance either by reviewing the current instances or generating new instances. So, balancing the class distribution using these methods may improve the model's performance. However, when it comes to the real life scenario, the models may so here, Yang et al. 2023 highly recommended not to use undersampling or oversampling method in large data sets. So, in real life scenario, extremely imbalanced data is commonly observed where we have very few minority class instances and large number of majority class instances. So it's a severe issue when it comes to the multi-class data. So among the distance-based classifiers, K nearest neighbors, that is KNN algorithm is widely used due to its simplicity and flexibility. So again, its performance deteriorates when we have the class imbalance noise or high within class variability. So various KNN variants were proposed in the literature to mitigate these limitations. However, the performance of these KNN variants under extremely imbalanced multi-class data have not been explored. So with this background, we defined our objective. The objective is to evaluate the performance of KNN variants in extremely imbalanced multi-class data. So for this, we have considered 5 KNN variants. So the first one is classical KNN, where it classifies the given unknown query data based on the similarity with the training data set. So here, similarity measure is considered based on the nearest neighbors. So given an unknown observation, so KNN classifier searches the pattern space for the key training data that are processed to the unknown data. So here it assigns the class to the based on the majority class that are close to the unknown data or the query data. So next is weighted k-nearest neighbor. So it is an extension to the classical KNN method. So here the data point or the neighbors that are closer to the query point contribute more to the decision than the distant one. So here more weight is given to the data point that are closer to the query point. Next, K conditional nearest neighborhood, that is KCNN, which was proposed by Gill et al. 2019. So here it computes the nearest neighbor separately for each of the classes. So here for each class, the distance to its K nearest neighbor is calculated, and class conditional distances are used to estimate the posterior class probabilities, and final classification is based on the maximum posterior probability. Next one is adaptive curvature based KNN, that is KKNN, which was proposed in 2024. So usually earlier KNN method considers global K value. So here it removes that concept and adopts neighborhood size local. So here local geometric structure of the data is considered using the curvature estimation. So here high curvature regions were given with the smaller neighborhood values, whereas the low curvature regions were given higher neighborhood values. Another one is dynamic clustering KNN, which combines dynamic clustering with the KNN algorithm. So here, each class is first partitioned into multiple subclusters. Then feature weighted distances were computed, and KNN is applied using these distances to subclusters represented. So these are the classification models that we have considered, and performance of these classification models were evaluated using accuracy of each class and geometric mean of recall. So we have conducted a simulation study based on the article by Gong and Kim in 2017, Hosmer and Hosmer et al. 2013. So here the multinomial data is generated from the multinomial logistic regression model with three classes of which one is majority and two minority classes, and independent variables are considered as 4 and 8 and are continuous and distributed. And the performance of classification models were evaluated using class accuracy, geometric mean of recall, and here we vary sample sizes from 100 to 1000, imbalance ratio from 3 to 6, which is according to the author Siddha, and the data distribution of independent variables are taken from standard normal distribution and the chi-square with 1 degree separate. So here we applied 5-fold cross filtration in order to avoid underfitting and overfitting the model. This is a hyperparameter that we have considered in the KNN. These are the results. This table represents the class accuracy for when the number of independent variables are 4 and this distribution is standard normal distribution. So the first column represents the sample size, and second that we have presented here 100 and 250, and second column represents the cases where we have the origin data representing equal proportion of samples and the imbalance cases. So here we can observe that for the balanced cases, KCNN performs better. However, when in the extreme imbalanced cases, KKNN performs better. Also, we observe that as the balance ratio increases, the accuracy of the minority classes reduces. This can be observed similarly when sample size equal to 250. So this is the result representing geometric mean for K equal to 4 and the distribution is standard normal distribution. We can observe that as the imbalance ratio increases, geometric mean of the classifiers decreases. Next, this is the case where when the K equal to 8 and the distribution is against standard normal distribution. Here also similar pattern is observed. However, we see the highly imbalanced case, that is IR equal to 6, the accuracy of the minority classes were reduced to nearly 50% when compared with the original. So this is the geometric mean plot when K equal to 8. This is the result when K equal to 4 and the distribution is chi-square with 1 degree of freedom. Here we observe that WKNN performs better when the balanced case and KKNN performs better in the imbalanced case followed by WKNN. This is the result plot. Similarly, this is the result for K equal to 8 and distribution is chi-square with 1 degree of freedom. So we have considered a real application, that is thyroid dataset, which is from the Kegel, with the number of observations 215, where the task is to identify the diagnosis of thyroid conditions based on the clinical features. So the response variable is stage, which includes 3 classes: hypothyroidism, normal, and hyperthyroidism. So here the independent variables are 5 and are all continuous, and the imbalance ratio is 1. So here we observe that KKN model performs better. To conclude, in this study we have evaluated the various KNN simulate in case of extremely imbalanced multi-class data using class accuracy and geometric mean of recall in simulation study. So my results show that at the level of class imbalance, sample size, number of variables, and data distribution impact the performance of classification models. And as the imbalance ratio increases, performance of the classifies increases, especially it's significantly in case of large number of variables. So under normal distribution, irrespective of sample size, KCNN followed by WKNN perform better both in case of small and large number of variables for the original data, whereas KKNN followed by WKNN perform better in case both in case of small and large number of variables for the imbalanced data. Under non-normal distribution, WKN performs better for small number of variables, while KCN performs in case of large number of variables, and KKN followed by WKN performs better in both in case of small and large number of variables for imbalanced data. So this is a real life example considered also justifies the same. So these are the references considered. Thank you.
Thank you, Sachin. So, are there any questions? Okay, actually, I have one question. I'm completely new to this topic and just curious. So, you have mentioned G mean is in performance comparisons. Are there any other performance comparison measures? Like one more you use is class accuracy, that also not sure. Are there any other measures as well?
There are other measures, but for the imbalanced data, geometric mean is the best measure to compute. So it is mentioned in the literature itself, so we consider that.
Okay. Also, in choosing the hyperparameter scale, are there any particular reasons to choose K4 and 8?
Based on the data set. No, K, number of variables.
K is number of variables?
Sequence.
Okay. So, simulation hyperparameters, I thought it's the number of neighbors.
Number of neighbors. It's based on the samples.
Okay. Thank you. If there are no more questions, let's thank the speaker. So our last speaker of the session will be Ms. Varsha, a research scholar from Prasanna School of Public Health, Manipal Academy of Higher Education. We are pleased to have her here today with us, and the title of her talk will be Assessing Parameter Estimation in Zero Distorted Generalized Geometric Regression for Count Data. That is of my interest. I welcome you. Yes. Is it moving? Okay.
It's more easier. Click. No.
Good evening everyone. I am Varsha, research scholar at the Department of Applied Statistics and Data Science, Prasanna School of Public Health, Manipal Academy of Higher Education, pursuing my research under Dr. Satyanarayana Pujari, and my topic of research is Assessing Parameter Estimation in Zero Distorted Generalized Geometric Regression Model for Count Data. So far we have been listening to talks suggesting how common count data is in different fields. One of the distinct features of count data is that it is characterized by so many features like over dispersion, under dispersion, zero inflation, zero deflation, others. To address these features, particularly in regression, we have different regression models like Poisson regression for equidispersion, negative binomial for over dispersion. To account for excess zeros, we have zero inflated models, hurdle models, etc. However, most of these standard count data models handle only one or two features at a time and not all features together. So that is why what is advantageous is having a model which can accommodate all these features at once, so that we need not switch models according to the data that we have. So one such framework is the Zero Distorted Generalized Geometric Regression Model. Here, this was introduced by Shastri et al. In the year 2016. The ZDGG framework provides a single modeling structure that captures zero inflation as well as deflation along with over dispersion and under dispersion. For this, we have a distortion parameter called as Q, which can handle the zero inflation or deflation. And this model is particularly useful when we have excess zeros compared to that of Poisson and negative binomial regression model. To exploit any model completely, we need to estimate its parameters. Any flexible model will be useful only if we can retain its parameters. That is what is the topic of interest here. In the ZDGG model, we make use of maximum likelihood estimation, and of course this does not provide any closed form solution for us, and we need numerical optimization methods to obtain the parameter estimates. In literature, there is no research that evaluates the parameter estimation, particularly in the ZDGG model, even though it has been introduced in 2016. What is the problem of having numerical optimization here is that we have different optimization algorithms. Literature states that different optimization algorithm can affect the parameter that we are trying to estimate. Secondly is the estimation strategy. In ZDGG model, we have to estimate two types of parameters. One is the regression coefficients and another one is the distortion parameter. While estimating these both, they can interact with one another while simultaneously estimating both, and this can affect the model parameters again. So, to understand these issues, particularly in the ZDGG model, we have conducted this research with the following research question. How effectively does the model estimate and recover the underlying parameters under combinations of different count data features like zero deflation, inflation, over dispersion and under dispersion? How does the choice of optimization algorithm affect the accuracy and stability of the parameter estimates? And finally, which estimation strategy, that is simultaneous or sequential, is more suitable for estimating the regression coefficients and the distortion parameter in this model? This here is the PMF of the ZDGG model. Here the distribution is characterized in terms of two parameters, Q and alpha. For different values of alpha, we get different combinations of zero inflation, deflation and over dispersion and under dispersion. To incorporate covariates into this distribution, the mean and variance of the distribution is reparameterized using the following equation. Alpha is equal to log theta, where theta is the mean of the distribution. 1 minus q divided by log q minus 1, and the regression is of the form theta is equal to exponential of x beta. The log likelihood function is given in equation 1, and the normal equations for this log likelihood are expressed in equation 2 and 3. In this research, what we are doing is we are conducting a simulation study by generating data from the ZDGG model, but we consider different parameters, a combination of different parameters, beta and q, to generate different types of data, which is zero inflated, combinations of zero distortion as well as over dispersion. We have kept the number of predictors for now to be 3, and predictor distribution is also changed. We have varied the sample size from 100 to 1000, covering small to large samples. Particularly, we are interested in finding the effect of optimization algorithm use. So, we have used 4 commonly inbuilt algorithms like BFGS, BHHH, CG and NF. And estimation strategy is varied as simultaneous and sequential. What I mean by simultaneous is, using the likelihood, we are estimating, in single optimization, we are estimating both regression parameters as well as distortion parameter. Whereas in sequential, we first take the distortion parameter to be observed number of zeros. An initial value is given, and only the beta coefficients are first optimized, and then using these beta coefficients, Q is estimated. This is repeated for 5 cycles, and we get the model parameter estimates. To tell about the quality of estimates that we have obtained, we have used the following metrics: bias, mean square error, standard deviation, standard error, and 95% coverage probability for the coefficients. For the ease of, this simulation was very exhaustive, it was very lengthy. For the ease of presentation, I have only presented this case where simultaneous and sequential estimation is used for over dispersion and zero inflation. From the results of all the tables, you can see that the estimates are quite close by. In all, despite of the different algorithm I have used, the estimates are quite close by. But what differs is the convergence and time taken for each of the optimization algorithm. So to simplify that, I have I have condensed it. Further slides I have condensed only in terms of time taken for the algorithm and its convergence. These are the different data scenarios I considered, and the best optimization that came based on the time as well as convergence is reported below. When we considered over dispersion and zero inflation, we also considered different proportions of over dispersion to stress test the model, that how it can handle high amounts of zeros. To condense the simulation results, we can see see that under all data generating conditions, the model can recover its pattern, the parameter. The quality of parameter estimation is similar across all optimization algorithms, given that convergence is achieved. We find that the BHHH algorithm consistently outperforms all other algorithms, for particularly in terms of fast convergence, and it does not show any convergence failures across all scenarios. The second best is the BFGS algorithm. We see that the CG algorithm also shows convergence most of the times, but it is comparatively very slow compared to these algorithms. And then we have the Nelder-Mead algorithm, which is showing lowest convergence in simultaneous estimation case, suggesting that joint estimation of parameter can in fact affect the parameter estimates that we get. When we come to sequential estimation strategy, simultaneous versus sequential, we see that even in sequential estimation also we can retain the true parameters. But sequential estimation, since we are running iterations for 5 cycles, we can see that the sequential estimation shows no convergence failures compared to simultaneous estimation. The sequential estimation, however, is substantially more computationally expensive. It takes at least as more than 2 times the time taken for the simultaneous estimation. Particularly, I would like to highlight the result that we got under dispersion and under zero deflation, both for under dispersion and over dispersion. Since it creates flatter likelihoods, many algorithms like BFGS and CG will exhibit larger bias and MSE regardless of what sample size we use. However, under this case, Nelder-Mead algorithm, which does not depend upon the which is doing independent optimization, gives better results. Coming to the effect of sample size, we see that under extreme cases like high over dispersion and zero inflation, our model, the ZDGG model that we have considered here, requires at least 500 sample sizes to get relative bias for all coefficients less than 4%. Under all other scenarios, sample size of 300 is enough to get reliable parameter estimates. To show the importance of the study, I have considered a real-life example where we have considered road traffic accident data that is collected from the following source. It's from the Brazil and for the year 2019. I have 3 independent variables: weekend, which is an indicator variable for whether it's a weekday or a weekend. I have type of accident as well as whether. My aim is to predict. My aim is to understand the dependent variable number of unharmed people by accidents based on these covariates. The distribution of response variable is as follows. When we consider the OD ratio, we see that it's near 1.33, suggesting almost equidispersion, not very highly overdispersed. And the zero proportion is 0.5922, which is slightly higher than that of the Poisson data. And then the sample size for this data is 2705. Based on the model fit, I fit different models, and along with that ZDGG is fit with the different algorithms. Based on the AIC, we can see that the ZDGG model for this data set gives the least AIC. Particularly, I would like to highlight the runtime used by different algorithms. We can see, as I suggested, the sequential algorithm is taking more time, sequential estimation strategy is taking more time, whereas simultaneous is giving quick results. And ZDGG with BHHH algorithm under simultaneous estimation strategy gives me answer within 0.21 seconds for this data set, which is comparatively very less compared to ZIP and ZIN, zero inflated models. To show that model can recover, once the convergence is achieved, to show that model can recover true parameters, I have added this example. We can see that under simultaneous as well as sequential estimation, model parameters are recovered. But particularly if we see the Nelder-Mead algorithm, we can see that it is quite very deviated from that of other algorithms that is achieved. As suggested by the simulation, that under such condition, convergence achieved by Nelder-Mead algorithm is very less. This suggests that the choice of algorithm also matters when we use maximum likelihood estimation. To conclude, in this study, we assess the parameter estimation of the ZDGG model in terms of optimization algorithm used as well as estimation strategy used. We can suggest clearly that the BHH algorithm performs better. Since all algorithms perform better under convergence, we can see that BHH performs better, particularly in terms of convergence and time taken for execution. And second best option, which is relatively used widely, is the BFGS algorithm. But in this particular case, BHH performs better. And for data, we also observed that for data showing extreme cases like over dispersion and zero inflation, we require higher sample sizes. We also, for other conditions, smaller sample size is enough to get lower bias. These are the short list of references that is used in the study. Thank you.
It was an excellent talk, Varsha, very well presented. So, are there any questions? Yes?
Thank you. Thank you for the nice presentation. I'm curious about one thing. I'm not sure if you have explained it. In your model, are there some conditions that can determine now I'm dealing with over-dispersion, under-dispersion, zero-dispersion?
Yes, the distribution has the parameter alpha. The distribution has the parameter alpha. When different conditions are satisfied, different values for alpha are satisfied, we get different combinations of zero inflation. So this model can handle zero inflation, deflation, over dispersion, under dispersion, which are majorly found in count data, commonly found.
Are there any other questions? I had two questions. So, were you there here yesterday in the workshop? No. Professor Nalini was presenting a model on zero modified model and zero truncated model. Is it comparable to that or different, or what is the?
This model can take zero deflation. That is, this cannot take zero truncation because alpha cannot take the value -1. When the value of alpha is -1, we can see that -1 plus 1, the zero part here vanishes. But this alpha cannot be -1, so this model cannot be zero truncated, but it can take zero deflation and inflation.
Okay. Here also, like I think in zero modified there was a parameter p. So here alpha plus the
Yes.
And just one other question is, like you mentioned 5 cycles in the
Yes.
Is there any particular reason for the number 5?
The convergence for these algorithms is mostly under 2 to 3. Literature suggests under 2 to 3 cycles it will converge. So 5 is a safer number so that we can tell it will surely converge and we can get the parameter estimates.
Okay. So if there are no other questions, let's thank the speaker. With this, I end this session.
Thank you. On behalf of the organizing committee of Icstc 2025, I extend my sincere gratitude to our session chair, Dr. Divya Kapara, for her excellent leadership and effective moderation of the session. I also thank Professor Satyanarayana, Mr. Sachin Acharya, and Ms. Varsha K for sharing their valuable insights and research contributions. I once again express my heartfelt thanks to each one of you for your valuable time and research. Now, I invite Dr. Divya Kapara to kindly hand over a token of love to Professor Satyanarayana. Next, I invite Mr. Sachin Acharya to receive a memento of appreciation. Next, I invite Ms. Varsha K to accept the token of appreciation. Now I invite Dr. A. Riaz to kindly present a token of gratitude to Dr. Divya Kapara. Thank you, sir. Now I invite Ms. Vinita Serraro from Manipal Academy of Higher Education to accept the certificate and cash award of Professor David Hanagal Best Paper Award 2025. With this, we conclude the session. Thank you for all your kind participation. We now move on to the next session, and I invite Ms. Nandana to kindly take over the proceedings. Thank you. Good evening, everyone. On behalf of the organizing committee, I extend a warm welcome to all delegates to this invited session of the 11th International Conference on Statistics for the 21st Century 2025. We are honored to have Professor Asha Gopalakrishnan, Cochin University of Science and Technology, as the chair of this session. Her research interests include distribution theory, modeling, and analysis of time-to-event data. We sincerely appreciate her willingness to preside over this invited session. We are privileged to host two distinguished speakers. Professor Rahul Roy from IIT Delhi will deliver his presentation titled An Introduction to the Elephant Random Walk. Professor Kimya Tinani from Sardar Patel University, Gujarat will present recognition of control chart pattern in non-normal processes using SBM and CNN approaches. We are confident that the expertise and scholarly contributions of our chair and speakers will make this session highly enriching and impactful. I now respectfully invite our chair, Professor Asha Gopalakrishnan, to guide us through the session. Over to you, ma'am.
Thank you. Thank you.
Still going on, right?
മത്സരത്തിന് ക്യാമറ ഉണ്ടോ
Can you hear me now? I think I can share.
ഓക്കെ It's him.
That's
Is anybody there from the organizing committee? I'm unable to get Nikhil or Satish on phone. Is anybody there online from the organizing committee to help Professor Roy?
I can't hear anything.
Is anybody there from the organizing committee to help Professor Roy? The person who introduced.
I can't hear. What I can do is I can send my PDF to Professor Satish Kumar and he can do it. If that is okay.
Yeah, but I'm not.
I can hear it.
Professor Satish Kumar.
That's all.
സാറിന് നമ്മളെ കാണണോ?
അല്ല, സാറിന് പ്രസന്റ് ചെയ്യാൻ എന്തോ പ്രശ്നം.
And I'll ask him to see what page.
Okay. Let me try contacting him again.
we have on that. Sorry, sir. This professor can send the document on our side.
Can you say that to him? Do you know the mail ID here?
Can സംസാരിക്കുന്നത്
English only.
How do I know? He present in there, he presents. He just read the slide. Okay? I change the slide. How do I know? Email it item. Icstc
30 minutes. Can you please continue then? So I invite you. I don't need his full name. Tinnani. Okay, I invite Dr. Tinnani for the presentation.
Good afternoon, madam. Myself Dr. Kimya Timali, working at Sardar Patel University, Vallabh. I'm sharing my screen. First of all, I am very thankful to the Professor Satish Kumar sir who has given me a chance to share my report. Is it visible, ma'am? Yes. So the title of my talk is Recognition of Control Chart Patterns in Non-Normal Processes Using HTML and CML Approach. We know that SPC is a set of statistical techniques used to monitor, control, and improve a process by identifying variation in the process over time. So it helps to distinguish between normal variation and special cause of variation, so that corrective action can be taken at the right time. So control chart pattern helps to identify special cause of variation by observing the behavior of topic points over a time. So even if all the points lies within control limits, certain non-random pattern indicate that the process may be out of control. So statistical process control is very useful in maintaining the stable and stable level of some quality characteristics. So the effectiveness of control charts lies in its ability to separate out of control data from the in control data in a process. So in the implementation of control chart, the process should be considered out of control when the points fall outside control limits, and you will find unnatural pattern in the data. So unnatural pattern in control charts can be associated with set of specific assignment calls, provided that appropriate process knowledge is available. And effectively recognizing control chart pattern can greatly narrow down the set of possible assignment, which is investigated and significantly reduce the diagnostic search. So if you see this graph, you can easily get an idea when you say process is in control and when you say it is out of control. Now there are different sample patterns, you can say, in the out of control situation. One is stratification, systematic, upward and downward shift. Now, what do you mean by stratification? So when points highly grouped in a narrow band, possibly causes maybe improper sampling measurements from only one source. And if we talk about systematic pattern of control chart refers to the non-random predictable behavior of plotted points over time. So in that case, points do not occur randomly. It is repeatedly or ordered structure is visible. Upward and downward shift. So sudden change in the level. Points move to a new mean, like 7 or more positive points on the one side of the central line. Like possible causes may be machine setting changes, new operator or raw material changes. Next is increasing decreasing trend. So train pattern is continuous increase or decrease in points. 6 or more points steadily rising or falling. Possible causes may include their temperature change, equipment deterioration, etc. Next is cyclic. So cyclic pattern is nothing but repeating up and down movement, regular interval, daily, weekly, monthly. So these are the different control chart patterns. 7 different type patterns are listed. Normal, increasing trend, decreasing trend, cyclic, upward shift, downward shift, and another thing is systematic. Now, here, control chart limits are nothing but the data set within the plus or minus 3 sigma limits, which is important to identify the unnatural patterns before they go outside control limits. So, in this study, we have considered control limits based on the control chart, individual measurement on moving range, and exponentially weighted moving average. So the control limits for moving range charts are as
follows. And exponentially weighted moving average control limits are given by this form, where lambda lies between 0 and 1, which is a smoothing constant, and as is the width of control limits. Now here we have used two machine learning techniques. One is support vector machine and another is CNN. So support vector machine is a popular supervised learning algorithm which is used for classification as well as for regression problems. Now main the goal of SVM is to create a baseline or decision boundary that can separate the n-dimensional space into classes so that we can easily get idea about new data point in a correct category in the future. So this best decision boundary is called hyperplane. So if you see different kernel in SVM, decision boundaries of linear kernel in SVC, another is decision boundary of polykernel in SVC, third one is RDF kernel, and another thing is sigmoid kernel in SVC. So, SVC was originally developed for binary classification, so vector classification, which is for binary classification task, and basically it is adapted for multi-class classification using strategies like one versus less and one versus one. So in this study, one versus one method is used. The performance of SVC model is highly dependent on the careful picking of its parameters, especially the regularization of parameters, say Cn, kernel position, gamma. Now, to achieve optimal classification accuracy, these hyperparameters are typically fine-tuned through grid search, and the range of the parameters Cn, gamma are mentioned as 0.01 to 20 and 0.031 to 5 to 2 respectively. Another machine learning technique which is convolution neural network, which is the methodology among the most widely adopted deep learning techniques. So this is employed for both feature extraction as well as classification tasks. And this approach compromises convolution layers, pooling layers and fully connected layers, collectively forming the end-to-end classification model and minimize the dependence of convolution feature engineering method. So this is architecture of CNN. Now how we have generated the data? So by multi-color simulation technique, we have simulated non-normal data. So first we have generated random data set which contains 32 observations, x1, x2, x3, where each sample contains 32 observations. So here for non-normal data, we have used Weibull distribution with parameter lambda as a shape parameter and k as a scale parameter. And for beta distribution with two shape parameters alpha and beta. The second step is we have added unnatural patterns to these data sets such as yt is equal to xt plus ct, where t is equal to time of sampling, yt is sample value at time t, and xt is common cause of variation which follow non-normal distribution, that is Weibull and beta, and dt is unnatural pattern at time t. So here, for different control chart patterns, I will discuss several different patterns. So here for two distribution, non-normal distribution, Weibull and beta, the description of equation for different patterns are shown here by taking different values of parameters with their ranges. So for normal, Weibull and beta parameter lambda and k, and beta alpha and beta range some parameter range as mentioned here. Similarly, for different patterns, training, cyclic, shift, and systematic. Now, the classification experiments were conducted on the synthetic data set generated for Weibull and beta. to represent non-normal process behavior. Now, 7 control chart patterns like normal, systematic, cyclic, increasing, upward, downward shift. The data was simulated by considering sample size 1000, 1500, 2000 and 3000 observations. Now, in training and testing, we have considered 80% data set for the training and 20% for the testing. We have applied SVM and CNN method, and the performance of the model is evaluated by the confusion matrix and classification report. So this is overall accuracy, which is given in percentage of SVM and CNN for both the distribution fiber and chart using MR and DWMA charts. So if you see here for different value sample sizes, 1000, 1500, 2000, 3000, we are seeing the accuracy for both the charts by taking by beta distributions. So this performance on DWMA charts highlights the greater ability to detect small and moderate shifts in the process mean, especially at the non-normal data condition. For most of the cases, there are often clear identification of the patterns for machine learning models. So it is recommended to use SVM model on DWMA chart for both distribution processes, as this combination provides higher classification accuracy. You see there is 93-95% of accuracy. So this is confusion matrix by where different sample size data set 1000, 1500, 2000 and 3000. So first we are this is confusion matrix for SVM model, algorithm for control data. Then this is for CNN for regular data on moving range chart with different sample size. Similarly, this is confusion matrix of SVM for data on moving range chart with different sample size. This is CNN for beta data on MR chart with different sample size. And this is for EWMA for Bible. And this is for CNN for Bible data on EWMA chart. SVM on EWMA chart with different sample size. And this is CNN for, so here we have considered two algorithms, CNN and SVM, by taking two different control charts using EWM and moving range chart for two distributions. One is for beta and another is for non-normal. So from this you can say confusion pattern recommends essential guidance for practitioners when the model predicts an increasing trend pattern. One should also investigate the possibility of assignable causes which are related to the upward shift and vice versa. Similarly, a classification of normal behavior should be considered alongside evidence for the cause leading to systematic variation, as these classes show partial statistical overlap. So non-normality affects the statistical representation of variation, leading to reduced between pattern classes and explaining the observed inconsistency in the model performance with increasing sample size. So the future of may be considered for EWMA chart parameters such as different values, smoking sample lambda and to limit L to optimize sensitivity and feature representation for machine learning models. Even we can think about application of other type of control chart like subchart, adaptive EWMA, memory-based charts. So even different machine learning algorithms are also must be tried, or we can think about hybrid modeling approach. These are the different references. Thank you.
Thank you, Professor Deepika. Any questions? Any questions? Well, if there are no questions, I was wondering that you had actually given intervals for your therapy. Yeah. What was the logic behind the report?
And actually, I have read so many research articles. So, in majority of the articles, they are defining these ranges. So, based on previous research, I have considered that range.
What happens if it is beyond?
So, actually, I have seen in that case whatever the classifications is not accurate. In that case, it is like 50%, 42%. Accuracy was very less.
Thank you, Professor. Professor Roy, are you ready now?
Yes, but they have to do the classes.
Oh, okay. So, Nikhil, can you present?
So I'll go.
Nikhil, can you present?
നമ്മളാണ് പ്രസന്റ് ചെയ്യേണ്ടത്.
So because that will be loaded on the computer there.
Professor Pilar, you can now stop presenting.
Only present ചെയ്യണം. So present stop. എല്ലാം
Anybody from the organizing committee? Please present Professor Rahul Roy's presentation. Yes, sir. So please interact with the presenting. Please interact with Professor Roy. The next slide,
I think there is some problem because did you get the full slide, the full document?
somebody from the organizing committee can interact with Professor Rahul.
Can you move to the next slide? So, this talk is on the element random walk, and it's quite different from all the talks from the morning. This will be a completely theoretical talk on stochastic processes. Okay. So, before I define the element random walk, which are called the ER, we'll discuss the simple random walk which all of us teach in classes. And simple random walk is arguably the simplest stochastic process. It has been studied for over 100 years. And its simplicity is deceptive because even after 100 years, we do not know the answers to many questions. Okay. And because of this work for over 100 years, it has given us a very rich development of probability and probability. So, before I give a formal definition of the simple random walk or the RW, let me tell a bit of the history of this. Can we move on to the next slide? So Carl Pearson, the person who is renowned for his discovery of covariance and correlation, he wrote this following letter to the weekly Nature in 1905. So he called it the problem of the random walk. And it's very simple letter. It says, can any of your readers refer me to a work wherein I should find the solution of the following problem? Of failing the knowledge of any existing solution, provide me with an original one. So I should be extremely grateful for aid in this matter. So the problem is that a man starts from a point zero and walks LDR in a straight line. He then turns through any angle, so randomly, whatever and walks another area in a straight line. He repeats this process n times, and I require the probability that after n of these stretches, means that the distance between R and R plus delta R from the starting point. So how do I, that is more than a time unit, the probability distribution. So this was the letter which Icstc wrote in 1905, so 120 years ago. Then we move on. In the very next issue of Nature, Lord Rayleigh provided the solution for large N. He pointed out that he had solved essentially the same problem 25 years ago, in 1880, in a paper which is related to sound biology. Then we move on. So the paper to which Lord Rayleigh refers is in modern language. His observation that if a person takes steps of unit length and then changes directions, then after n steps, the probability of the walk the line between x and x plus delta x or n large is the normal density, with dx being the distance. Okay. So, and this expression, the normal density is largest when x is near 0. In other words, what Lord Rayleigh is saying that he will be very close, the man who is doing this random walk will be very close to where he started. Then we move on. And in the next issue, Carl Pearson thanks Lord Rayleigh and ended by saying that the lesson of Lord Raleigh's solution is that the most probable place of finding a drunken man who is at all capable of keeping at his feet is somewhere near his starting point. So he just connects it with a random walk and dance. So this was in 1905. Then we move on. And then in 1919 and 1920, George Fourier started the systematic study of the random. In his 1990 paper, he presented a common setup of the problem as a random walker who is walking on a three-dimensional axis, and the walker moves from one vertex of the lattice to its nearest neighbor in one step, according to equal probability of these neighbors. Okay, then we move on. So in the one dimension, this is all of us known here because we were taught in is that the simple random walk is nothing but starts off with a sequence of IIT random variables which takes value class 1 later we know that the case will be equal. And Xn is nothing but x1 plus x2 plus xn. In other words, you add up all the steps, and Sn is the location of the random walker at time. And so the random walker here is the to the right will probably be and to the left will probably be. It is also a emotional mark of it, because if a given that Sn is k, then Sn plus 1 can be k plus 1 or k minus 1. Will probably be k or 1 minus k, right? So Sn plus 1 depends only on Sn and nothing else, and that is the definition of the mark of it. Can you move on? Before I move to this slide, so one thing you have noticed about the exam is that there is no question of systemic in the sense that people go back. There is no question of systemic because electronic forces are automatically there. And so there is no memory in the experiment. So what do we do? The first thing is classification and get this to last month. And you also have a selection contract for 1, 2, and the end of one is because one of the last even from the advantage. So for example, at the age, the editor remembers for age, but the editor remembers it. The next is the probability and incorrectly with the probability to 1. So that's exactly what the second equation is. So at least one of your fingers you will remember it correctly, whether it's the plus one, you remember it as plus one with probability, or you remember it with the wrong thing with probability to 1. And we move on. Sure.
So in the expect note, go to the previous slide. Please go to the previous slide.
Can you hear me? Please go to the previous slide.
Okay, that's not
value from 1 to 8. Right? Yeah. So it just won't take value from 1 to 8. So the first thing is to property 1 to 8 to value 5.
Yeah, P is independent of A. So whatever
independent from it, P is a parameter.
You studying.
So you remember with connected with probability and incorrect with probability. Okay. And so if that is the location of the element after time, but you can also see that from the calculation that probability of n plus 1 equals n plus 1 given the past. It actually a matter of particular time in group. In other words, the transition probability matrix changes with time. So it is not a homogeneous matter. And that is why it is perfectly so it is a matter of thing, but not a time homogeneous matter. It is a sense of the transition matrix changes over time. And we move on. There are now documents how to estimate the parameters. Parametric is parameter that you remember that. So there are lots of studies done on the statistical aspects of it also for estimating the parameters. Okay, can you move on? So before I again tell about the data, let me remind you of some of the data because we would need to understand these. So the first one is that remember the location of the data because it's the random locate and here are the three people. So the first is the strong law of which is affected by and the next is the central limit. There are which is affected by so these are the properties of some ideas. And the next two are the so-called law of integrated geometry. That means what Sn divided by square root of n whose not particularly and remain for the same thing would be minus. That would say the random walk is cross this property and the minus is the ingredient which is a different process indexed by time and S of NG is the square of NG which is a smaller larger integers smaller than N. So if I look at S of NG divided by as a process, then we convert to the standard transformation. So these are some of the which we know about the estimated random walk. The regular random walk as we know it's a bit completely different thing. So can we move on? Can we move on?
Please change the slide.
So the regular random walk as just remind you we have equals of minimum random variables. Actually, it should be UN plus 1. No, that is very the first variability doesn't matter is plus 1 or minus 1 or x or 1. And you see why it doesn't have because it is x or 1 in the long term. Okay. And the second step, we have to just uniform field of the first step. And remember the technique. And my intent is the location of the time. Right? This is what we have defined earlier, and I also related some and we move on. So the surprising thing is that there are three different so if between 0 and 0 is less than 0. I'll explain on in the next slide. And another one. What do I? So I'm not looking at the between people and people. So please remember it is the nobody how good it is for me. Just like the simple so we have and from the second level here, except for religious one. So it depends on which is not allowed. So you only look at people between 0 and people. But put this is something but of course you not allowed. Okay. And we also take a stand of the religious society, as in the and these 4 years are very people collecting karma and this is agreed at 27. And move on. For the functional here, it could put not brown and white. The Bubanian is completely different in predominant of the Bubanian culture, expectation of less is minus x, the x is going to be. Here it is completely different expression, which you can see from the bottom of the expectation of that would be is 1 over 3 minus 40 times. So this is and this stage is the probation, because this is bigger than the probation actually increases. It affects as the probation increases in time. So there is a loss of defense, whereas in Brownian notion the increments are always expected. So there is dependence coming in. When you move on, so 3 equal to 3 by 4 is still 3. The formula of the Sn by square root n log n. So what we need, what is the formula? How do we interpret it? The formula basically says that Sn behaves like probably the Sn is not a not 0. Here it says that Sn is minus square root n log n and plus square root n. So it is really not and it was and the where you do not normally and the thinking about the as much of and the law if you You're right. Block of blockage is much smaller. Block of blockage is very so the simulation of this model for the law of negative society is practically impossible. Okay. So these are the results by to reconciliate and collect our actual independently. Okay, now, remember, before I move on the next slide. So the
He didn't say move on. Then only I can understand.
now the bucket is the essentially divided by square root of m to the power 3 rocket. Then this one will be the so this is what a critical. When you move on. What is supercritical? Let's think of what happens in your memory is always. So suppose the first x1 you are taking to the left. Then because your memory is always correct at any sequence step, you don't always take to the left. In other words, and then it can be at one. It does depend on where the one is. For that, it would be last one. The decimal would be plus 10 because you always repeat when t equals 1 or memory is completely correct and you always repeat what you did in the earlier. So what happens is that the random walk would either go up plus infinity or go minus infinity. Will probably be one. It just depends on whether the first step was plus one or the first step was so this is what p equals to 1. Therefore, p don't equal to just expect the same. We have to get the same thing. And here are the minimum physical station at that time is greater. And what is so that will be the location at that time. And for this random variable, we know that the fourth movement converts to 0. And not only that, it will be normalized, it goes to a normal distribution. So the last value is some sort of a central limit. But of course, here, the problem of large numbers, problem of large numbers, what has to be realized? Because it is by or it might go to the here it goes to a random. Okay, so that is the then we move on. There's another thing. If I look at the simple symmetric number, as I told you, was the stock negative the basket, to consider the limit of that one, if you was plus 1, and the limit was minus 1. Therefore, it is crossing the origin into a 0 because it has to go to plus 1 and then back to minus 1. So the simple symmetric number, we know that the number of times n for which n is equal to 0 is okay. We also know that a capital P is the first time starting from the random walk as returned to the simple symmetric random walk. There is an expectation of that. So we get something completely different for the elephant random walk. But the elephant random walk, that shows that less than or equal to 3/4. The elephant returns to the origin. However, for each clear with the 3/4, it just comes to the audience at most time many times. And for people to find people like this, we will not do that. And also, the expected time of further vision is infinite for people to want more time money. And it is finite for between, sorry, for and it is finite for between 0 and 2. So the last line will be 0 and 2. It's not 3 by 4. Okay, then yeah, then move to the slide. Finally, what actually what we have was he wrote in one of the papers that if you want to use to go for a walk, let's say and those are so tough to use to go for a walk. Sometimes it's take a left, sometimes it's take a right, and they will be moving quite often. So his question was suppose that independent simplicity works, then how does it do? And then he showed that probably listening to and for implementing change is not. For the regular language model, we have the language behavioral language that for people between people and people, well, they meet for the and if the limited very strong, in other words, they don't want to so this is and before I you can make that so these methods are practically a martingale method and the next thing is the Boolean in the window and we just move on and explain quickly the last methods and then then we move on. And extended one which is recording from the recording methodology and recording and extended. So this is our then move on. I think that you are very good N plus 1 alpha n plus 1 is scientific where alpha n plus 1 is my the random variable which is remaining at high correctly the probability and theta is plus 1 is more than voltage and more than and so what you notice the feature is the extent plus 1 is good and minus extra given with probability and that can just direct by this line extent plus 1 is good alpha right so that's one and here the alpha is so you can define the exhibition of the element and the increment in this this move on. If we do that, is in other words, so the expectation of xn plus 1 condition for x1, x2, actually the like expectation of alpha n plus 1 times expectation of beta n plus 1 given the alpha n plus 1 is the corresponding probability and minus other probability 1 minus I get it to -1 from that expectation. And from the other one, people think that just one is value. Not me, but rather I is that because it's one over n plus one. So this expectation, this conditional expectation, is nothing but 1 over n. That is my probability of seeing n plus 1 as I. And some over all I we can do that. But then summation, the last summation I put from 1 to n is nothing but n. So what we have is that 2 minus 1 x, that is exactly like the original expectation of the thing. Or I can write it as it is Sn. Remembering that s of n plus 1 is nothing but Sn plus x of n plus 1. Taking this to the right, to the left, what we have is that expectation of Sn plus 1 is nothing but Ramayana times Sn plus Ramayana. And then if I look at this, the product of this drama, I get that a mixture of two karma functions, karma very interesting, karma very interesting. Can we move on? So taking E1 to E1 to E1 over that product, just replace that karma ratio the numerator goes to the denominator and the denominator goes to the numerator. And then you can see that n is actually karma n times n plus 1. And so if I write capital N times n, what we get is that the mass equals n for the filling, and that is exactly what is the so we exploit this marking which we obtain from the process to study S. Because if we know something about S, we will also get to know something about M, then we will also get to know something about S because M is not about E. So that was the martingale method. And finally, the Puglia method is a very nice way of doing. So Puglia is the new one back and daily. So there is a back and contains two colors, either red and the US are red common. How many red commons there are? That's exciting. Here is getting how many blue commons there are. But to form this, we have to first tell you what we start. So we start with that kind of one. It is after 1 red commons and more we probably get. Or more red commons than 1 we probably get. So that is why in that back, if that is only one person, it should be checked, or it should be less will probably get, and it will probably fail. And you know what? So now these words, they will be one word. The word is that word. And suppose it is there. What is the problem? And now it is created when one red one will probably or one blue one will probably do. So it because in the first side of the time people have either 2 days, it probably or 1 day and 1 blue will probably be 1 time. And if we do this, then what we can see is that the information sample position of the element at time has the same distribution, and the difference between Rn and En is at time n of the Puglia. So this is the other method used to study the element. So these are the two methods which are used, and now there are various other slight changes in the definition of the elephant animal, which makes the thing much more complicated and interesting. But this is something which has been studying over the last 20 years, and I'm sure the statistics will also get involved in this because this is, in our field, what is really, it's very difficult to get out of independence data. This is one case where people have got out of the independent sector and there is dependence on the past. But in this dependence on the past, there is enough structure to still study the parameters is very important. And I'd like to end here. Thank you.
This was a very, very interesting talk.
Thank you.
In a very natural way, many results like follows from the book. Sorry, I have a bad mood. Any
Oh, you are not in Delhi. Delhi is so beautiful. You are that close, that
No, no, after that first.
I know that's what I'm in Delhi and I'm thinking about it. Sorry, yeah, go ahead.
Any questions? So if you don't have any questions, yes.
Good evening, sir. Very interesting talk and again new talk. Sir, I wanted to ask you that when 3 lives is given more than one, we say that memory is right. Very principle. Then why is it that religion then becomes a transient state rather than being a recurrent state?
Okay, think of it. Think suppose your please, we have to please. The first step after parameter is between people.
Yeah.
So suppose your first step is dasha.
Okay.
Then what is your next step? Again dasha. Because you're perfect.
Yeah, okay.
What's your next step? Again dasha.
Okay, so the chances of returning
so when P equals 1, you will just go on to it. You will never return. So if you can say for P equals 1, this is the case, and for P near 1, also this is more or less the case, isn't it?
Yeah.
So how much is what does it mean by linear? So that's exactly something which all statisticians have been talking about, right? What do you mean by output will be a parameter? So here, three by 4, your memory is actually very good so that it guides what the first step was, and the process is driven by the first step. That's it.
Yeah, okay, sir. And just as we have in our simple random walk with barriers, do we have random walk here, ERW also with barriers?
We have nobody has checked that yet, but we are having to work on ERW and barriers. But I don't know. Yeah, I don't think anybody has done work with that yet. What I did not tell you was that there have been ERW work done. Right. But in barriers, reflecting or absorbing.
Thank you so much. Very interesting.
Any more questions? Okay, so if we have no questions, let us thank both the speakers.
Thank you.
And perhaps this could be shared with those who are interested.
Nice talk, sir. Very nice talk, sir.
Thank you. Okay, it was a very good session today.
So, thank you, sir.
Thank you. Okay. Bye.
So, what is the
On behalf of the organizing committee of the Icstc 2025, I take this opportunity to express our sincere gratitude to all those who contributed to the success of this inviting session. We extend our heartfelt thanks to the chair of the session, Professor Asha Gopalakrishna from CUSAT, for her scholarly guidance toward the session. We are deeply grateful to our distinguished speakers, Professor Rahul Roy from IIT Delhi and Professor Kimya Tinani for their valuable input. We also thank all the delegates and participants for their active presence and engagement, which make the session meaningful and interactive. Thank you so much, sir. മറ്റേ ICST 2022 മെയിലാണ് ഞാൻ സാന്ദ്രയ്ക്ക് പറഞ്ഞു
ഗൗതമി 6:30 സ്റ്റാർട്ട് ചെയ്യാം.
അതെ അതെന്റെ ചേർന്നു ചേർത്തരാത്തിനുള്ള ചേർന്നു ലീവില്ലാസമാണല്ലോ ഇവിടെ പിന്നെ ഇടയ്ക്കിടയ്ക്ക് പറയും ഞാൻ നമ്മളാദ്യം അല്ലെങ്കിൽ താഴ്ന്നതാണ് പറയാം ചേച്ചിക്ക് എന്തോ പണി കിട്ടിയെന്ന് മാത്രമേ ചേച്ചി എന്തോ അത് പറഞ്ഞു
Leo, Leo.
എല്ലാ ഫോണിലും നോട്ട്സ് ഇല്ലാതെ എന്തിന്റെ ഐഡിയ ചെയ്യാനുണ്ടോ തരാൻ ചെയ്യണോ ലൈന് വാങ്ങണോ
അത് ആശയം തന്നെ വോക്കൽസ് ഉണ്ട് വോക്കൽസ് മാത്രം മതി ഇത് വേണം ആ കരോക്കെ കിട്ടുന്നില്ല കരോക്കെ ഇല്ല അതെന്തെങ്കിലും ആക്കാൻ പറ്റുമോ അപ്പൊ അതിന് കരോക്കെ അത് നമുക്ക് മറ്റേത് റൂമിൽ നമുക്ക് കൺവേർട്ട് ചെയ്യാൻ പറ്റാറുണ്ടോ മറ്റേത് ആപ്പ് ഉണ്ടല്ലോ ആപ്പല്ല ഇതിനകത്ത് സൈറ്റിൽ അങ്ങനെ ചെയ്യാൻ പറ്റില്ല സൈറ്റിൽ അങ്ങനെ ചെയ്യാൻ പറ്റില്ല സൈറ്റിൽ ബാക്ക്ഗ്രൗണ്ട് പാട്ടുണ്ടായിരുന്നു
Especially instrumental. Yeah.
ഇതൊക്കെ അറ്റൻഡ് ചെയ്യുമ്പോൾ ബുക്കൊക്കെ പേപ്പറൊക്കെ എടുത്ത് നോട്ട് ചെയ്യും. കുറച്ചൊക്കെ നോട്ട് ചെയ്ത് ഈ നോട്ട് ചെയ്ത് വെച്ചിട്ടുണ്ടെങ്കിൽ ചില ചോദ്യങ്ങളൊക്കെ ചോദിക്കും. എക്സ്പെർട്ട് പ്രസന്റ് ചെയ്തു. മനസ്സിലായോ? നിങ്ങൾ എത്രത്തോളം ഇന്ററാക്ട് ചെയ്യുന്നു അതാണ് വേണ്ടത്. ചോദ്യം ചോദിക്കാൻ നമ്മൾ തെറ്റായിട്ട് കുഴപ്പമില്ല. ചോദ്യത്തിനകത്ത് ചോദ്യം ചോദിക്കുമ്പോൾ ചിലപ്പോൾ തെറ്റ് വരുമ്പോൾ ചോദിക്കും. മനസ്സിലായോ? സൈക്കിളിൽ ഓട്ടാൻ പഠിക്കുമ്പോൾ മതി മഞ്ഞ വിടാതെ പഠിക്കും. ചോദ്യങ്ങൾ ഞാൻ നിങ്ങളുടെ ക്ലാസ്സിലൊക്കെ ചെയ്യുന്ന അങ്ങനെ നിങ്ങളെ കുറിച്ച് നിങ്ങൾ തന്നെ ആൻസർ ചെയ്യാം. ഇവിടെ വേണം, ഇവിടെ കാണിച്ചാൽ മറ്റുള്ളവർക്ക് അത് ഇൻട്രസ്റ്റ്. ഈ വരുന്ന ആൾക്കാർ അടുത്ത് നിങ്ങൾ ചോദ്യങ്ങൾ ചോദിക്കുകയും നിങ്ങളവരായിട്ട് ഇന്ററാക്ട് ചെയ്യുകയും ഒക്കെ ചെയ്താലേ അല്ലെങ്കിൽ അവരെ ഇൻസൾട്ട് ചെയ്ത പോലെ അവരെ വിളിച്ചു വരുത്തിയിട്ട് വെറുതെ എന്തോ അവർക്ക് നമ്മൾ ആരും ഇതൊന്നുമല്ല. വളരെ സീരിയസ് ആയിട്ട് ചില കാര്യങ്ങൾ അടുത്ത ദിവസം എല്ലാവരും മാക്സിമം അറ്റൻഡ് ചെയ്യണം. ഓൺലൈൻ ആയാലും അറ്റൻഡ് ചെയ്യണം. അറ്റൻഡ് ചെയ്താൽ മാത്രം പോരാ, അറ്റൻഡ് ചെയ്യുന്ന കൂട്ടത്തിൽ ചോദ്യം ചോദിക്കും. അറ്റൻഡ് ചെയ്യുന്ന ഓരോരുത്തരും അബ്സ്ട്രാക്ട് ഒക്കെ നമ്മളിപ്പം സൈറ്റിനും നമ്മുടെ കയ്യിലൊക്കെ ഉണ്ട്. അതൊക്കെ എടുത്തിട്ട് ആ ടോപ്പിക്കായിട്ട് ബന്ധപ്പെട്ട് ചുമ്മാ ഒന്ന് നോക്കാം. ഒരു 2-3 പേര് ടീം തിരിച്ച് ഓരോ ടോപ്പിക്ക് നോക്കിയിട്ട് അതുമായിട്ട് ബന്ധപ്പെട്ട് കുറേ ചോദ്യമൊക്കെ പ്ലാൻ ചെയ്തിട്ടുണ്ട്. ഇവർ പ്രസന്റ് ചെയ്യുമ്പോൾ അതുമായിട്ട് ബന്ധപ്പെട്ട് മനസ്സിലാവാത്തതോ മനസ്സിലാകുന്നതോ ഒക്കെ നോക്കി മനസ്സിലായി. അതുണ്ടാകും പൊളൈറ്റായിട്ട് അവരെ ഹർട്ട് ചെയ്യാത്ത രീതി അങ്ങനെ ചോദിക്കുമ്പോൾ നമ്മൾ ചോദിക്കാൻ പഠിക്കണം. ചോദ്യം ചോദിക്കാൻ കഴിയുന്ന സബ്ജക്റ്റ് മനസ്സിലായിരുന്നു നമ്മൾ മനസ്സിലായിട്ടില്ല, നമ്മളുടെ ഇഗ്നറൻസ് കാണിക്കേണ്ടതെന്ന് ചോദ്യം ചോദിക്കരുത്. പക്ഷെ അവര് കുട്ടികളിൽ നിന്നുള്ള ചോദ്യം പ്രത്യേകിച്ച് കുട്ടികൾ പറഞ്ഞ സാറന്മാരായാലും കൂടുതൽ ഇവിടെ നിന്ന് അറ്റൻഡ് ചെയ്യേണ്ടതാണ്. ക്രിയേറ്റ്സ് ആൻ ഇംപ്രഷൻ. ആ ഇൻസ്റ്റിറ്റ്യൂഷനെ കുറിച്ച് ഇംപ്രഷൻ ക്രിയേറ്റ് ചെയ്യുന്നുണ്ട്. അല്ലാത്തതാണ് ഇൻസ്റ്റിറ്റ്യൂഷനെ കുറിച്ച് ഇംപ്രഷൻ ഇല്ലാതെ നമ്മളൊരാളെ വിളിച്ച് വലിയ കാര്യങ്ങൾ ചെയ്യാൻ ശ്രമിക്കുമ്പോൾ അതിൻ്റെ പോസിറ്റീവ് വരെ നെഗറ്റീവ്. നമ്മളവരോടൊക്കെ പറയും നമ്മുടെ കുട്ടികളൊക്കെ വളരെ കഷ്ടപ്പാട് വളരെ കാര്യങ്ങളൊക്കെ വരുന്ന കുട്ടികളാണ്. രാമകൃഷ്ണൻ പക്ഷെ അതൊന്നും കാര്യമില്ല. കാലത്ത് നിങ്ങൾക്ക് ഫ്യൂച്ചറിലായിട്ട് അവിടെ പോയി സക്സസ്ഫുൾ ആവണമെങ്കിൽ ഷുഡ് ബി വെരി ആക്റ്റീവ്. ആക്റ്റീവ് ആണെന്ന് കാണിക്കാൻ നമ്മൾ തപ്പം ചെയ്യും. പിന്നെ ഇവർ പ്രസന്റ് ചെയ്യുന്ന സമയത്ത് അവിടെ ഇവിടെ സംസാരിക്കുന്നത് ടോക്ക് should be silent and observe and ask questions. Silent ആയിട്ട് ഒബ്സർവ് ചെയ്ത് നമ്മൾ സൈലന്റ് ആയിട്ട് ഒബ്സർവ് ചെയ്തിട്ട് അവർ വിചാരിക്കുന്ന they are not interested. വെറുതെ പിന്നെ കവലപ്രസംഗം നടത്തുന്നവരെ പൊളിറ്റീഷ്യൻസിന്റെ സ്പീച്ച് നടത്താൻ വേണ്ടി വരുന്നതല്ല. They are not like such people. Academicians, researchers. They are serious about it. മനസ്സിലായി? സീരിയസ് ആകുമ്പോൾ ഒരു വേഗം പിടിച്ചു നിങ്ങളെ പഠിപ്പിക്കുകയോ പറയുകയും ചെയ്തു. Silently observe whatever they present, take note of that, and try to ask questions. Yes, even simple. There is no questions. There is no wrong questions. Even wrong questions have some meaning. Even if you ask a wrong question, that I will do it. That also sometimes creates a feeling in a different. So there is the wrong question saying. So please try to ask questions. And if you time build is going to future മാത്രമല്ല ഈ രീതിയിൽ ട്രൈ ചെയ്യും. പക്ഷേ ഫ്യൂച്ചറിൽ എവിടെ പോയാലും നിങ്ങൾ ആക്റ്റീവായി മനസ്സിലായോ? ഓക്കെ, please take it as a positive suggestion and try to improve your listening and grasping capacity and your approach to the peers or fellow people coming in here, whether it is virtual or physical. Whatever. Online ആണെങ്കിലും ചില ചോദ്യങ്ങളൊക്കെ you have any questions എന്ന് ചോദിക്കുമ്പോൾ കുറച്ച് സമയമുള്ളൂ, 5 മിനിറ്റ് അല്ലേ? ആരും ചോദിക്കാതിരിക്കുന്നു. Someone sir doing that way, or whether it is a different thinking in that way. Or I couldn't understand what you mean by this. Any questions? Okay. So that gives respect to them. Respect. Respect in that way. Okay. തുടങ്ങിക്കോ. നാളെ രാവിലെ 9:00 വരേണ്ടതാണ്. 9 മണിക്ക് എടുക്കണം. 9 ഫസ്റ്റ് സെഷൻ ഈസ് അറ്റ് 9:30.
Good evening, everyone. After an intellectually enriching day filled with insightful discussions and stimulating sessions at Icstc 2025, it's now time to relax and celebrate the vibrant spirit of culture and creativity.
The cultural program this evening is a humble attempt to showcase the rich diversity, talent and artistic expression of our students. We hope these performances provide a refreshing interlude and add a memorable touch to the conference experience.
Let us now begin the cultural program. Our first performance is a melodious song presented by Sony Wilson and Devika P. Ajo, students of MSc first year. May we have a big round of applause as they take the stage.
मैं तेरे घर में मेरे हाज में हूँ, मैं तेरी सांसों के सांस में हूँ, आगे झुका के सुन ले मुझे तो, मैं तेरे दिल की आवाज़ में हूँ, तो हौसला है तू ही राधा, आदि में तुझ में मुझ में तो आया, तू न मेरी तू न तू भी, मैं तेरे सपना तू मेरा आधा, हाय मैं मर ही जाऊँ जो तुझको ना पाऊँ, बातों में तेरी में बातें बिताऊं, होठों पे लम्हा लम्हा हे नाम तेरा है, तुझको ही गाऊं मैं तुझको पुकारूं,
മധുവായി മാറിയതാരേ അവളുടെ മിഴിയിൽ കരിമഷിയാലെ കനവുകൾ എഴുതിയതാരേ നിലവുകൾ എഴുതിയതാരേ അവളെ പ്രണയിനിയാക്കിയതാരേ വരമഞ്ഞളാടിയ രാവിൻ്റെ മാറിൽ ഒരു മഞ്ഞു തുള്ളി ഉറങ്ങി നിമിനേരമെന്തിനു തേങ്ങി നിലാവിൽ വിരഹമെന്നാലും മയങ്ങി
दवा भी लगे ना मुझे दवा भी लगे ना मुझे जब से दिल को मेरे डोला है नींद रातों की मेरी चाँद बातों की मेरी चैन को भी मेरी तूने उड़ाई जब सांसें भरूं मैं बंद आगे करूं मैं नजर तोड़िया आया दिल को करार आया तुझ पे प्यार आया पहले पहले भार आया ओ यारा दिल को करार आया तुझ पे प्यार आया पहले पहले बार आया ओ यारा ओ आ ओ आ ओ
இன்னும் கொஞ்சம் நேரம் இருந்தாதா என்ன ஏ அவசரம் என்ன அவசரம் இல்ல பொன்னே இன்னும் கொஞ்சம் நேரம் இருந்தாதா என்ன ஏ அவசரம் என்ன அவசரம் இல்ல பொன்னே இன்னும் பேசக்கூட தொடங்கலையே நெஞ்சம் கொஞ்சமும் நிறையல இப்போ என்ன விட்டு போகாது என்ன விட்டு போகாது இன்னும் பேசக்கூட தொடங்கலையே நெஞ்சம் கொஞ்சமும் நிறையல இப்போ மழை போல நீ வந்த கடல் போல நான் இரவே இன்னும் கொஞ்சம் நேரம் இருந்தாதா என்ன ஏ அவசரம் என்ன அவசரம் இல்ல பொன்னே இதுவரைக்கும் தனியாக என் மனசு அலைய விட்டு அலைய விட்டு அலைய விட்டாயே எதிர்பார நேரத்தில இதயத்தில வலைய விட்டு வலைய விட்டு வலைய விட்டாயே நீ வந்து வந்து போய் அந்த அலைகளை போல வந்து உன் கையில மாட்டிக்குவே அலையல போல உன் கண்ணு கேத்து அழகவரே காத்திரடா கொஞ்சம் உன்னை இப்படியே தந்தாலும் தித்திக்குமே நெஞ்சம் இன்னும் கொஞ்சம் நேரம் இருந்தாதா என்ன ஏ அவசரம் என்ன அவசரம் சொல்லு கண்ணே இன்னும் கொஞ்சம் காலம் பொறுத்தாதா என்ன ஏ அவசரம் என்ன அவசரம் சொல்லு கண்ணே
For the beautiful rendition, it's truly set the tone for the evening. Moving on to our next performance, we have a song by Leo from the MSc first year class. Let us encourage him with a warm round of applause.
here, I come from Burundi. I don't know if everybody know where I come from. My name is Leomir, but here they call me Leo. Short name. Today, my friend told me to sing for you, and I tell him I'm gonna sing. I'm gonna sing for you for God. He's a gospel guy, gospel singer. So I'm not a good singer, but I'll try. I'll try. Yeah. Doesn't make so much repetition. So I don't know what's going on. I tried. Yeah, the song is in English. Creator.